All right, so let's just go ahead and get it started to kick off the 6th annual summit for the Center of Responsible Machine Learning. And today we are extremely happy to have the first joint summit between the Center for Responsible Machine Learning and Quantum Foundry. So this year's theme is AI and materials. And we have a day full of exciting talks and panel discussions. And we also provide lunch to the students, everyone, so we can have more free time to discuss ideas, collaboration opportunities during this time. But before that, let me introduce Dean Umesh Mishra, Dean of College of Engineering. So Umesh will give us an opening remark.
Thank you, William. I appreciate it. Thank you all for coming, and I'm sure people will start straggling in. It's a little early for students here. So, first of all, I think this is very near and dear to UCSB. I think this is a differentiator, a killer differentiator for AI as a campus, along with I'm not saying the differentiator, but is a differentiator, because I think that as Ambuj and I were just talking a couple of minutes ago, and Tressa, it just seems like when you look at the AI landscape, it's so crowded right now. And of course, you know, with the Nobels, it's gotten like super hot. And it was hot, but it's become scalding hot at the moment. So I think finding our niche in such a vibrant space is important. And I think you all have found it. I think this AI applied to science of various types, I think is where we at UCSB can do a phenomenal job. I mean, Sam's put something together for AI, for an AI NSF AI thing. There are many proposals coming out of campus which all look very good. Of course, it's competitive, but all I can say is the College of Engineering, at least speaking for the college, I'll do whatever I can to support this with the resources I have. We can also go and gather more resources, but this is for us, AI, the NLP work that William is doing and others at NCS, coupled with the quantum materials work in the Quantum Foundry and material science in general. And I'd like to actually even extend it, even though this is not part of the summit. I think even we have a chance of developing new hardware for AI, which I think is going to be an important part of the energy-efficient AI of the future, because I think there'll be many things for us to do. I think UCSB can find its groove very quickly. So thank you all for doing this. We are, of course, very proud of the work that is being done in both the Mind and Machine Intelligence Center, the Quantum Foundry, and the Center for Responsible Machine Learning. And of course, Megagon Labs is part of this whole endeavor. We are very proud of the work being done here. And all I can do is say, you know, the campus is fully behind it. I think you guys are onto it. Thank you.
Thank you, Umesh. All right, and thanks for Dean Mishra for the kind words. Let's continue the opening session. I want to say a few words about Center for Responsible Machine Learning, so people have a little bit more context, and we can also have Stephen to introduce Quantum Foundry in just a second. So the Center for Responsible Machine Learning, we started in the spring of 2019, right? This is like way before ChatGPT, you know, GPT-3, 4, whatsoever. So like Umesh said, the campus invested in AI long before it was cool. And then we, you know, had a lot of emphasis on different topics and programs this year, right? The first year we're looking at fairness, and then we look at social good, AI and health, and a variety of cutting edge topics. And what's unique about UCSB in this context is that I think we don't work alone. So over the past 5 years, we work with so many different, you know, collaborative centers, institute initiatives on the campus to, you know, trying to understand AI from the interdisciplinary, you know, avenue that I think think is very critical, and especially looking for funding opportunities to support students. I think there are a lot more opportunity in the space where collaborative opportunities are present rather than a single call, right, from CS or engineering directly from NSF. Okay, so we also want to mention that, engaging with the campus is very critical mission for the center. So we started 5 years ago. Now we have 60 faculty affiliates from more than 20 departments. We hold regular distinguished lectures, annual summits. We organize, multi-institutional research, proposal writing efforts related to AI. There are also a lot of engagements with industries, particularly, for example, this afternoon, right? You're gonna hear, two amazing talks, right, from POSCO and Google executives who are very well established and very well known for their AI materials research in this area. So being also engaging with different industry partners, we're trying to, get funding to support students, especially supporting the underrepresented students, first-generation students. Definitely let us know if you'd like to get it engaged. Just a quick overview, right, from the things we did in the last few years. Like I said, the first year was AI and fairness. At that time, we recognized this would be very important topics. We had a lot of industry engagement, and then COVID hits, right? So in 2020, so we started turning these events into virtual events, and then we focus on solutions or research topics related to COVID at the time, and also engage with, nonprofit and government officials and trying to see how we can help, right, in the, solutions. And then the year after, we did AI for social good. Again, this was virtual, but then in 2022, we finally turned it back to in-person events, and we focus on UCSB's key emphasis, right, on the showcase of the UCSB AI Machine Learning Day. And then we had also a lot of interest from the campus, amazing speakers, 270 plus registered participants attended throughout the day. And last year, we did a collaboration with the NSF Action Institute, which is $20 million funding support from the National Science Foundation to support this, AI and Cybersecurity Institute on campus. So we were focusing on responsible generative AI at the time about security risk and how we use AI to mitigate, right, the security risk. It was also a lot of fun. And that was last year. So all of the videos, they were recorded. If you're interested, you can also go to our website and take a look at the videos on YouTube. Distinguished lectures also has been a key theme for the center. So we actually have an upcoming distinguished lecture coming up in a few weeks. We invited Professor Stefano Soeto, Vice President at Amazon AWS Lab, who is also professor at UCLA. So this is a joint event with the Control Center, CCDC, on campus. So this should also be fun in a few weeks. I do want to acknowledge a lot of people because with all of your support, it wouldn't be possible to continue the events into the 6th year. So I want to particularly thank all of the speakers coming to today. We want to thank, of course, Stephen for his generous support and working with me on the program. It took us, I think, half a year for the planning and execution. Also want to thank Michael Ray for really helping us doing the organization as a staff representative. Also, we want to thank, of course, Quantum Foundry, the Megagon Lab for their support. So Megagon Lab is a AI research lab for the Japanese company called Recruit. But we've been lucky to always get their support for the UCSB campus activities. And of course, the chancellor himself also expressed a lot of support in our AI initiatives on campus throughout the years. Of course, the dean and other campus leadership, the Mind and Machine Intelligence Initiative, and other supporters for making today's program possible. Before we dive into the agenda, I do want to invite Professor Stephen Wilson, the co-director of the UCSB National Science Foundation Quantum Foundry, to give us an introduction about the Foundry. Yep.
Great. Thank you, William. So first of all, yeah, I'm listed as a co-chair, but this is, William has really done a great effort putting all this together. I think for those of you who know him, William's awesome. So this is a real boon to be able to run these workshops every year. So the Foundry is interested and engaged with this particular workshop because it's a center which is focused on the development of materials for quantum information, but in particular, kind of the accelerated development of those materials. And I think as time goes on, we all realize that in order to have this sort of accelerated development, then one needs to really couple into this sort of AI, computer-guided exploration of the large phase space of inorganic materials. And so, the center, just as some background, is we're entering our 6th year, sort of entering sort of the renewal period, trying to go for that. But we've had the good fortune of interfacing at first with Linda Petzold and her group, and more recently with William Wang and his group. And in trying to incorporate some of these new AI tools, not only for the prediction of new materials based on for instance, ab initio models of electronic properties, but also trying to harness experimental data and synthetic pathways to try and accelerate the development of a new targeted material. So basically, I think Eric and I were just mentioning a second ago, like one of the major roadblocks in materials development is the computational tools for predicting new materials have really come a long way. And we're at the point where actually making a predicted material is the challenge. And so trying to to minimize the number of like repetitions or iterations that a student has to do to try and make a new material would have a great impact. And so I just want to mention one of the great things that I've learned and from sitting for these workshops that William has organized is that the tools for impacting the material domain seem to already exist. It's just a question of someone using them. and that really requires, I think, as William mentioned, sort of a collaborative, a true collaboration between AI experts and material scientists, because you really need both. You need to motivate the computer scientists because it's not really pushing the boundary of AI, because if you keep doing that, then you're not really applying it. But at the same time, in order to apply it meaningfully, you need to actually interact with someone who's making materials. And so I think that's a really, like I say, a target-rich environment for major impacts coming in the coming years. And so I'm excited to see what happens at the workshop today. And am I introducing Eric next? Okay. Oh, okay. And then I'll give it back to William. Thanks.
Thank you. Thank you, Stephen, for the introduction about the Quantum Foundry. I want to give a little bit of context, right? I mean, I think the timing for today's summit is perfect because I think many of us, we saw the news that the Nobel Prize in Physics awarded to John Hockfield and Jeff Hinton. I think the first reaction from computer scientists was like, wait, can computer scientists also win Nobel Prize? I think that was the reaction that we got. But as you know, of course, they are really early figures in neural networks and fundamental algorithms. For example, restricted Boltzmann machine, Hockfield network, which is an early version of recurrent neural network. So of course, I think they did amazing, achievements in the field. And also want to mention that Jeff Hinton is not the first person who have won a Turing Award and also a Nobel Prize, right? There was Herb Simon before that who also won the Turing Award and the Nobel Prize, but it was in economics. Okay, so that's that. But then the second day, everybody was stunned that for some reason that the Nobel Prize that week just continued to given to sort of AI research in science engineering. So I think AlphaFold was a very good collaborative effort. Like Stephen mentioned, I was hoping that we can actually see the version of AlphaFold, but for material science, really to make fundamental breakthrough. I think, like Stephen said, that's not very easy because you have to really motivate CS, AI, E students, right, to focus on really solving the real problems, right, in materials. That itself is not very easy. And then in materials, you also need to understand the property. You need to do simulation. You need to do all these different experiments to make sure, right, that there is a real breakthrough, real impact. But I think the good news is that we're already seeing something, right, in protein folding, in protein structure prediction, which is pretty awesome. So I think we're becoming more and more confident in the next 5 to 10 years. There may be very significant breakthrough in this area. Actually, this afternoon, I think some of our colleagues in really trying to pushing AI in battery, in other areas, they will tell us the amazing breakthrough at Possible and at Google in the afternoon. Okay, so what is the structure? I'll try to be very brief. I think this might be my only 2 slides left. So one thing I want to mention is that the structure of today's summit is that we're going to have some morning talk. We'll have the morning keynote, and then we'll transition into a panel to have more discussion so people have those questions in mind throughout the day. Then we're going to have lunch around 11:30. And after that, we have the industry keynotes in the afternoon. And then we have some UCSB research highlight showcase, and we'll close that with the closing keynote. This is what I'm thinking about the main goal of today's workshop. So we're not trying to like really get everybody on campus to sit here and listen about AI material. I think the goal is to really get this very focused group, right? That we want to really understand what are the real challenges, right, in AI and materials. Because even the problem definition, I think it wasn't always like clear, right? So understanding the challenges, understanding the emergent research problems, in some sense, are more important than solution because the area is so new, right? That before talking about solution, we need to validate whether this is a real problem, right? So, and then I think the second part of today's goal is to have collaborative, of discussions, collaboration discussions, see whether there are some exciting new avenues of research that maybe multiple PIs and students, they're interested, so we can look for, potential opportunities to collaborate, right, across the campus to really push this area forward. Because UCSB is very well known, right, for materials research, and we also believe that, with the increasing, presence of our AI research on campus and globally, we are very well positioned, right, to lead in AI materials research. The logistics, I think this is the last slide before I hand it over back to Stephen again. So please silence your cell phone. So we are doing the recording, so everybody will be able to, review the today's agenda, and it's also live stream on YouTube. The lunch will be provided. Right now, we haven't. I think we need to take a closer look whether it's outside or inside because there's also the IE directors meeting next door. Just to make sure you eat the correct lunch because there could be 2 lunch set up. But we'll guide you to make sure that we go to our correct station. The schedule is live on ml.ucsb.edu. You click on it, and then you'll be able to see the summit, and then go to the 2024 summit. You'll be able to see, right, all of today's agenda. So let me know if you see anything. Okay, with all that, I will hand it back to Stephen, who will introduce today's first keynote speaker.
All right. So while Eric sets up, I will. It's my pleasure to welcome Eric Toberer here, who's our first keynote speaker of the day. So Eric is a professor of physics at the Colorado School of Mines. So Eric is actually homegrown. He's got his PhD from UCSB in 2006 with Ram Seshadri in the materials department. And from there, he went and did a Beckman Fellowship at Caltech with Jeff Snyder and Sasina Hale. And then from there was a professor at the Colorado School of Mines. And he's also the director of the materials program there. He's won many awards. Most notably, he's a PCASE recipient. So, and his research has, I think, okay, so from the outside, it seems like starting with Ram, he's basically harnessing data for new materials predictions, but now moving into even using AI tools. But Eric does the full spectrum. He also makes the materials and tries to test and evaluate. So it's a great pleasure to have him here, and I'm excited to see what he talks to us about. And so with that, I'll turn it over to you, Eric. Thank you.
All right. Good morning, folks. Let's make sure this works. Hey, it does. Miracles. All right. Yeah. So I have a rather generic title here, Transforming the Design Cycle, which you'll inevitably hear more than enough about. So indeed, I'm started out as an experimentalist. I'm still predominantly an experimentalist, but as I've sort of, the last couple of years, I've sort of gone from collaborating with computational folks to actually trying to be their graduate advisor, which, you know, that's a step. So most of my experience is in energy materials. I went to the Colorado School of Mines predominantly initially because of the proximity to the National Renewable Energy Lab over there. And so I was interested in thermoelectrics, I'm interested in optoelectronics, but I think in my heart of hearts, I'm basically a solid state chemist who likes really weird materials, right? This is a single, unit cell of this crazy crystal structure that has like 104 atoms in the primitive unit cell. I mean, that's too many atoms. But that sort of complexity I'm like really drawn to. So when I sort of think about my transition from being like a sort of Edisonian solid state chemist in Shoshader's group, which actually was sort of predating Ron being interested in data, actually. Like, we're talking way long ago. There were still dinosaurs roaming. Honestly, it probably first began with a series of DMREF awards from NSF starting in 2013. And when you think about what these, the DMREF program was about, it was generally asking the question of how do we interweave computational material scientists and experimentalists together in some way that had like better synergy than sort of historically there was, which was to say pretty thin. And then specifically, that was me working with a lot of density functional theory groups to screen thermoelectric materials and predict defects therein. And sort of back in the day, right, it was sort of the tyranny of funnels for a lot of research groups in material science, right? Where the sort of general goal was there's a giant search space and how do we accelerate discovery with some sort of like down selection process, or you go after sort of like the simple physics-based down selection sort of descriptors, and then you sort of pass that on to to expensive first principles calculations, and then that just sort of like flows off to the experimentalist. And that's a rough place to be as an experimentalist, frankly, which is the role I found myself in, because most of the time this is grossly wrong, and you end up getting served a lot of materials that simply lead to sort of grad student angst. And so there sort of had to be a better way. And so I was really excited, really excited to successfely submit this institute proposal sort of right in the COVID times. A great time to be submitting an institute proposal. And specifically, that asks us a broader question, right? How do we strengthen the connection between material science and computer science? And so this is a huge institute. We've got 17 research groups spread across the country. Giant shout out to my co-director, Ryan Adams. His is the group that originally produced AutoGrad, which is now JAX. Elif Erdogan is at UIUC. She's also phenomenal. She's my other co-director. And this is an institute that's basically an even split between experimental folks, computational folks, and computer scientists. So we sort of really get this like cool blending of different disciplines and different viewpoints and different vocabularies. You can imagine it's not always the easiest, but that's kind of the fun of it. So we're interested in discovering new mechanisms, and I use the word mechanism fairly loosely here. So that could be, as Stephen sort of like wonderfully alluded to a minute ago, right? That could be new synthetic pathways, that could be new material functionalities, or even like new ways of sort of connecting the dots between synthesis and functionality, which is how do we reveal structure, right? And unless you're operating at 0 Kelvin, the odds are good that anything that you're looking at involves dynamical properties, right? And so we're interested in the time domain. And I think when I compare what we're interested in our institute here versus a lot of the sort of original DMREF work, one of the things that really strikes me about this is the addition of time. It's really hard to think about like a funnel type process as a dynamical thing, right? And so this really motivates us to think deeply about ways in which we discover new mechanisms, right? Rather than new materials. So I'm going to start by analogy because I love a good analogy. So how do we discover things? Imagine, for example, you had knowledge of some swimming strokes, but you didn't know about all of the available strokes. And you want to discover the butterfly stroke, which is an insane stroke, right? I mean, you're like kicking your legs like a dolphin. Michael Phelps is making the arm motion look good, but still, who would have thought that that's the way to do it, right? And it took till 1935 for this to be like a stroke that was ever present in a competition, right? I mean, people have been thrashing around in the water for a long time, and I don't think, let's just say this was a divergent stroke compared to prior strokes. So what's my point? All right, if you were going to go discover this as a dynamical mechanism, you darn well better think about this as a search problem, right? And you probably want to think about it as a search problem where you're paying attention to things like, what is my ultimate loss function? Is it speed? Is it energy efficiency, right? Then maybe the backstroke's better for you. Or is it, are you thinking about like prioritizing diversity? For example, you don't want to just find incremental like modifications to the backstroke. You're trying to find something exciting and different, right? And so when you think about search, you want to be thinking about things sort of in the space, but also it's a huge space, right? Okay, technically swimming's not that huge of a space, but it's still a pretty big space. There's a lot of nuance in it. And so you probably want to have some simulation, but those simulations are going to require surrogate models, right? You want to model fluid dynamics, but you sure don't want to do fluid dynamics at a high level, right? You want fluid dynamics as some sort of like cheap proxy. You also need to think about biomechanics. Humans are, in fact, constrained, objects. And then throughout this, and probably a phrase I use too many times in this talk, is you want to be like thinking about uncertainty quantification, right? How certain are you about the surrogate model, and what does that say about the quality of your predictions? Of course, some things you're not going to want to simulate. You're going to want to measure costly parameters. You're also going to want to validate the surrogate model. So we can't like not have people swimming. And then, people have been swimming for a while. And so it probably makes sense to bring in that expertise of, say, hey, Michael Phelps, what's cracking? And get that feedback. But you also probably want to visualize your results from some high dimensional space into some lower dimensional space and actually have a way for that expert feedback to connect to your simulations. So, look, I wouldn't be talking about this if this wasn't pertinent to material science. And indeed, it's this very same design cycle that we follow when we think about designing materials. And so when I think about what my institute is up to, we're a little bit hard to pin down because it turns out the design cycle is the sort of thing where you kind of need to do it all, and you need to do it all pretty well. Otherwise, it's not really much of a cycle, is it? So we have activities on the search side. We have activities on the simulation side. We have a pretty heavy effort in surrogate models and uncertainty quantification with a little bit in rare events. I'm personally super excited as an experimentalist about thinking about like new ways of modeling experimental data. There's been a lot of work over the years in automated data analysis. Of course, that remains super pertinent. And then, as Stephen alluded to, like experiment is the process of sequential decision making. And so, how we do that well, that's essentially a design problem in its own right, right? So, and again, I've sort of acknowledged these components of expertise, but underneath all of this is a sea of data, and I think this is the last time I will acknowledge the fact that there's data, right? I kind of feel like that by itself is probably not the interesting part here. Data is sort of the epiphenomena of all of this and not the actual phenomena. So I also sort of broadly note that I think a lot of people, when they think AI plus materials, they think surrogate models. I want to train a thing that's cheap and efficient to ask some very particular question. But I would argue that there are ways of applying things that we could loosely define as AI across this entire design cycle. Okay, so how this talk works is basically, that looks like 2 slides forward. All right, I'm going to start with an example actually in the mechanical engineering space in auto differentiation, because I think it's just a ton of fun, and I'm so proud of my team's work in this space. Then I'm going to think specifically about how do we sort of intersect search and simulation with some physics-informed search. Then we're going to connect between surrogate models and enhanced data modeling. And then finally, I'm going to talk about visualization and leveraging the literature corpus. So these are sort of 4 vignettes. If you get lost in one of them, no big deal. There's going to be conclusions at the end of every one of them rather than like a massive conclusion at the end. Okay, so let's take this one away. We're talking about auto differentiation. I just maybe like show of hands. How many people like have heard of auto differentiation before? Who's my audience? Okay, cool. So auto differentiation is mathematical techniques that like reveals gradients that emerge from sequential mathematical operations. And really in terms of where have they been absolutely useful to the world, right, has been, where has this technique been extremely useful to the world is in navigating extremely high dimensional spaces, right? So if you think about a neural net, right, you've got millions or billions of free parameters that you are trying to tune all of them simultaneously to improve your loss function. And that is insane, right? We can't take derivatives in a million dimensional space. Like a numerical derivative just dies, right? We don't have anything close to the precision for something like that, and it's just incredibly expensive. So with autodiff, you get to do this cleanly through what's called backpropagation, and that allows you to get like a quantitatively precise derivative. Also the second derivative too, if for those of you who are particularly excited about second derivatives. And so this allows for optimization. For those of you who like Python, you literally just wrap NumPy with a JAX wrapper, and you still write JAX code, or sorry, NumPy code. So it's not even that hard to implement. So point being is that we can use auto differentiation to find local minima in both static and dynamical systems. And people have been doing this for a while, but I think the application to doing this into dynamical systems is where I get personally very excited. So again, Ryan Adams is a guy who sort of subsequently got to JAX existing, so he's pretty amazing. And if you happen to be on a faculty hiring committee, I would give a huge shout out to Giovanni. He's going on the search right now, and oh man, phenomenal. So basically the work I'm showing is his. So the premise here is that metamaterials historically have been pretty much periodic, specifically mechanical metamaterials. And they give us some function, but it would be hard to argue that mechanical metamaterials have fully transformed our world. And part of that, ooh, we got a vibration going on, maybe look away, is that dynamical tasks require perhaps something more like quasi-periodic designs. But quasi-periodic designs sound hard. But let's think about what we might want to do in a mechanical metamaterial. We might think about having some sort of force on the outside of a material, leading to that force or energy ultimately arriving at some spot. You might think about mechanical signal processing. Things like soft robotics might find this useful. You might think about protection and mitigation, right? I'll show an astronaut later where the astronaut's standing here, and the question is, can we stop the energy that's coming through here from hitting the astronaut? Or you might want to hide things. I like hiding things. Let's hide things such that if I put a signal over here, you can't tell that there was a thing here, and the signal comes out looking as though there wasn't anything there. That's pretty wild. Or reprogrammability. Can we change the external environment of this metamaterial and give it distinct function where, for example, it moves where it puts its energy, right? So when I talk about quasi-periodic metamaterials, I'm thinking, let's say, for example, we start with a periodic arrangement of flexible blocks that are fixed in geometry, and we ask from a design point of view, well, what about this option? Or what about this option? Or what about this option? Or this option? Or this option? This is an enormous space, right? For this particular picture, if you only change the shape of these little like cubey boys, you're looking at about 10 to the 4 dimensions. So we clearly need a compass. We're not in full like neural net backprop mode here, but we're getting close even with something as mechanically simple as this. And that compass is, as you probably figured out, is JAX and the ability to take perfect derivatives. So in this particular case, I'm going to show the simplest thing, like literally basically figure 1 of this new Nature Materials that Giovanni just published, where the goal is to whack your metamaterial over here and have the energy show up over here, right? And we can define an objective as such and give it a design space where each one of these guys is independently designable, as I've sort of alluded to. From there, and you're not expected to necessarily pick up the slide unless you're sort of solid in the world of maths, but basically you say, okay, here's my real space design space. I'm going to push the mechanics of this space through a Lagrangian and get myself to this Q state space, where Q depends on the geometric parameters, bond parameters, things like damping, and even the initial conditions, right? We can forward solve that and then take advantage of auto differentiation. And in this particular example, I'm going to say, well, let's evolve this state in terms of the geometric parameters and just the geometric parameters alone. I'm not going to mess with any of the other ones. So we start with this particular material, and we're going to ask the question is, this is iteration number here. And there's a little bit fuzzy about like energy focused at target region. So how successful are we in terms of our objective function? And then we have 2 constraints that we would prefer to have go to 0. So let's start doing design. This is design in a world without that much human involvement other than sort of establishing what you want, right? And if I've got the skills, this should bring me to the end. There we go. So let's take a look at this. This is a 10,000 dimensional space. I took 1, 2, 3, 20 steps Technically, Giovanni did, I didn't. I've pretty much already optimized my energy focusing, and I've dealt with my constraints in 20 steps in a 10,000 dimensional space. I mean, that's absurd, right? So Giovanni's going to argue that this is a local minimum of geometry, and it's kind of fun for the material scientists in the room, right? You're like, ooh, that looks like a little nanocrystalline domain of one thing that must serve some particular role, and this guy has a sort of another sort of nanocrystalline domain of something else that serves a different role. Like, it's getting close to like what we might call like more traditional material science. Come on, there we go. Oh, and of course, because this Harvard team is phenomenal at also making physical metamaterials, this is their embodiment. It's on the order of, say, yay big, and they have realized it experimentally, such that I can show an image like this, where this is the experimental thing that I just showed, and this is what we have simulated it to do. And indeed, you'll see that it behaves effectively identically, which is stunning. So this is, in a sense, the simplest example. I think most, if not all, of the examples I showed at the beginning are also in this Nature Materials paper. So you can imagine then there's a heck of a lot of complexity you can do as you evolve your target function to something more interesting than simply, oh, I'd like to get my energy here. Okay, so that's AutoDiff. I think it's super cool. I think this falls in the category that Stephen was talking about a minute ago of like, there are these things from other fields that we should just be pulling in to material science because they're amazing. Right? If you have a high dimensional deterministic space, let's do inverse design of dynamics. That's rad. Okay, so of course you can think about this on other link scales. We've got another member of the team that is in the civil/architectural community. They build buildings, like literally they win like prizes for these sorts of things. And so what they think about like inverse design, they think they have some sort of target shape. Say, for example, as architects, they think, ooh, this particular football stadium is going to look good with some target geometry. They encode that structure as, and then basically use AutoDiff here to figure out the scaffolding, right? But what we don't have going on in our institute, I'd love to do more work in this space, is think about, well, at the nanoscale, what are the sort of like dynamical materials one could design that are still sort of in a fairly deterministic space? What is not being talked a lot about, at least within our community, is search diversity, right? We're using AutoDiff for finding like the minima of a given basin of attraction, but there's this open question in terms of thinking about other basins of attraction and how to navigate that well. Okay, here's my astronaut. You can also think about multitask optimization, right? It doesn't have to be a simple loss function. You could, for example, say, I would like to focus my energy and knock my poor astronaut over, given some external constraints, say, for example, how much static pressure is being applied over here, or by changing the environment, I now have a second task that I'm optimizing for. Now I'm trying to protect my astronaut and have him not fall over when this thing on the right pulses. So multitask optimization, totally available. It just requires writing down more math. This lends itself also to building even bigger differentiable workflows. Things can get more complicated. I think in sort of traditional material science, there's a lot of opportunities for using AutoDiff to rethink how we analyze our data, right? You get some expensive, complicated data. How do you want to analyze it? There are, of course, existing software packages, but they were almost guaranteed to be developed in a world where the author of the software package was not thinking about AutoDiff. And so what are the opportunities that this sort of engenders when you have access to navigating high dimensional spaces really cleanly? In general, there's questions, I think, and this almost like is as close to ethics as I get in this talk. There's questions about robustness, uncertainty, and sort of taking advantage of the Hessian, right? So we would like to come up with mechanical solutions in this case that are going to be somewhat robust against errors in manufacturing, let's say. The Hessian is the second derivative in the high dimensional space, and so you can basically get a sense of the shape of that local minima from looking at the Hessian. So that's I think also super cool. One of the things that remains, I think, an open question is, where does this technique sort of fail us in terms of as we go from deterministic to stochastic systems? And so if you have sort of a chaotic space, being able to follow, even if it is differentiable, it's going to be so sensitive to initial conditions that it doesn't actually matter what comes out of that. So I think that's like a really open, interesting question. Okay, so that was number one. The second thing I wanted to bring up was, or the second vignette, is going to basically say, if you start with auto-differentiation to find local minima, and you can do that, like I just discussed, you should do it. But there are a lot of problems that are either global in nature, such that the local minima is not necessarily what you're actually searching for, or they're not differentiable. And a simple example of a not differentiable type problem is I have rock salt, and I sequentially replace one of my atoms with a different atom, right? Sort of hard to push a derivative through that. So in the second example, I'm thinking about how you can develop Bayesian learning approaches that are physics aware to explore really massive spaces. There's going to be some vocabulary required in this. Let me just do like an ultra short course on this vocabulary. So I have two crystal structures, alpha and beta, distinct crystal structures. Here's composition, here's free energy. And each one of these crystal structures, as their composition changes, is going to have a different energy. We ultimately would like to minimize the global energy of our system. And as a product of that, if I have alpha at this composition, it makes sense to partition alpha and beta to these two phases, right? So when we teach material science to undergrads, we tend to call this like the common tangent sort of view of the world. When you go to higher dimensions, rather than thinking about it in terms of a common tangent, it's sort of like a little bit cleaner to think about it in terms of a convex hull. And this is just you have some high dimensional free energy surface or surfaces in plural, and you wrap them effectively with high dimensional saran wrap. And you ask, is the saran wrap tight or is it loose? And if it's loose, then that classifies you to, I have a composition that is unstable. So hopefully that works for you. So our goal in the end is to learn the convex hull. So that's where I'm going with this. All right, so those are sort of the definitional things. What are we doing with these definitions? We would like to learn the hull. In particular, we'd like to learn it as a probabilistic object because as an experimentalist, I'm really tired of being told that things are stable when they're not. All right, that's a poor use of my students' time. So unfortunately, learning the hull is not trivial. What we learn about when we make computational measurements is our computational measurements will give us free energy values. They won't reveal the hull itself. So what we're learning about is indirect. Okay, well, that's already mildly awkward. But it's also a global object, which is to say, if I have not thought about my gamma phase, and I've evolved my understanding of the hull with a lot of measurements, and I'm like, oh, by the way, maybe I should go look at the gamma phase, I have made a lot of poor decisions about understanding alpha and beta before that, right? So I end up with this situation where a local observation can have a far-reaching impact in the space. I think this is cool. And I think the computer scientists, when I first pitched this to them, thought it was pretty cool too. Fun fact, I did it with, what is that game? Battleship. I was like, you can imagine a world where Battleship isn't just a single point, but it has the ability to expand laterally. Like, how do you play Battleship if there's some breadth to your bomb? And then from there, we went off into holes, and it was a ton of fun. So again, humans are the best part of this whole endeavor. The science is great, but getting to talk to computer scientists is like fantastic. So we have a global object that we're trying to learn indirectly, and that's just a non-traditional challenge when you talk to the people in active learning. So with that said, we should always use the simplest tools we can get away with. So if you're working with a low-dimensional space, let me introduce my friend grid sampling, or if you're feeling fancy, farthest point sampling, which is to say, don't build complicated algorithms if you can just brute force it. If it gets a little bit nastier, maybe you should just try to learn the energy surface. So here, for example, I've got a Gaussian process that is sequentially sampling the energy surface in blue, or in the black points. Now I'm going to use the word sampling in a slightly different way. And then from that GP, we sample hypothetical energy surfaces that might emerge from that. And in gray, we've got the affiliated holes for each one of those samples. There's a lot of words. I'll show a second version of this that's not animated and maybe be a little easier to see. In the end, after 5 iterations, we actually still have a lot of uncertainty in the hull. Here's us having drawn a bunch of samples, and indeed in gray, the holes are all over the place. So that's not exactly ideal. But nevertheless, it would probably still work if you're in a low-dimensional space. But what we're working on experimentally in my group right now are compositions of this form. And so we have 3 cations, we have 3 anions, and we're in the rock salt structure. And in particular, heck, we can even look at the specific stoichiometry. This forms a hyperprism, for those of you who like phase diagrams, where the sulfide triangle is shown in here, selenide on the top, tellurium on the bottom. And you might ask the question, well, why can't we just grid sample this too? I mean, this doesn't look that much worse than a traditional quaternary phase diagram, except it really is. And the reason for that is this is a 3-dimensional representation of a true 4-dimensional space. And so even if we took 10% steps computationally, that leads to 4,500-ish compositions for this particular space. Those 4,500 points are shown here. And if you want to do something a little more accurate, a little more interesting, like 5% steps, you're looking at like too many steps. Right? I mean, 4,000 steps is already too many steps. Let me be clear here. These are not cheap calculations because the structure itself is horrible, right? If you sort of consider the complexity of all those local interactions and can you actually get those energies right? So what we might think about then instead is developing an active learning approach that's convex hull aware in terms of what its objective is. And so here, for example, you can see us evolve over our 5 steps. And because it's thinking about minimizing the overall entropy of the hull, as I'll get into in a second, it ends up really locking the hull down and leaves regions of the energy surface that are sort of irrelevant totally untouched. So again, here's my GP. I'm drawing samples from my Gaussian process. I'm applying hulls to each one of them. And then this lets me get to this notion of a probabilistic workflow, right? In the sense that I can do this repeatedly, and then I can ask, what are the tight points on the hull? These are shown in purple. And then now I have some probability of being on the hull, right? So I can start to ask, as I evolve my sampling, what is the likelihood of this being true? And it allows me to sort of set like criteria in an automated way for calling it a day or passing that probability on to other things. For those of you who are like, whoa, what did you do to do this? Let me just quickly talk about this. So we're interested in the Shannon entropy of the hull. We got that by basically calculating a bunch of hulls from a GP and looking at the covariance matrix. You just take the term of that and off you go. And then you can basically sort of fantasize about making observations at other compositions. And because you have a GP, you can guess in a probabilistic way what the answer you will get is, right? And so here, for example, we had this initial region over here that was hugely uncertain. And you can see that observations at the pink point are distinct from observations at the yellow point in terms of their impact on the hull. And so we can basically ask where in composition space do we want to sample such that our entropy change of the hull will be different. Here it is, sorry. And indeed, the pink point, as you might expect, is a pretty good point to measure at. This is sort of obvious in a 1-dimensional space, but if you try to do this in a 4-dimensional space, your brain rapidly turns into putty. So here's another example that I think we'll sort of end on for this particular section. Here we have 3 energy surfaces, a barycentric coordinate system for A, B, and C. And if we just look at like the true positive rate, for example, farthest point sampling, you basically have to sample every grid point before you have it figured out. Whereas if you use this convex hull-based active learning search, you very rapidly figure it out, and then you're sort of good to go from there. And if you focus on the energy surface, it ends up being sort of a compromise in between. So this is shown for a space that you can imagine is sort of human readable, but as you go to higher dimensions, these improvements like basically continuously grow. Okay, so look, this was a fairly detailed dive into this, but I wanted to highlight how in general, oh boy, custom loss functions give us a way to embed physics in search processes. And I think that's super awesome, right? Where it's not exactly inverse design, but at least you're trying to bring physics to bear on a problem that you're trying to optimize. And that when you ultimately make predictions, and we're never going to sample all 50,000 points in that hyperprism, we're going to be able to turn around to our experimental colleagues and say, I think this phase is stable with some uncertainty, or perhaps even more interestingly, I think this phase is right on the edge of stability. Let's see how it decomposes and use that to refine our understanding. So this one really sets us up for probabilistic workflows. I'll talk about uncertainty-aware energies in a minute. Here, we now have a GP that's looking at the uncertainty in the convex hull. But convex holes are cool objects. You can turn a convex hull into elemental chemical potentials. If you have a probabilistic view of your convex hull, then you have a probabilistic view of your chemical potentials. If you have a convex view of your chemical potentials, you have now, like, you can explicitly speak to some synthetic conditions that are chemical potential sort of aware. That's fun. Or at least in my world, that's fun. I don't know. Some people have different views of what fun is. Okay, cool. So I think there's still a lot of opportunities in this space though, right? I mean, GPs are amazing when it comes to search, but hyperparameters is a persistent, and hyperparameters basically tells you how you basically interpolate between your observations. And we really need to think about how do we bring physical constraints into our hyperparameters. This is a thing that has at least some traction already out there, sort of broadly in GPs, but I think there's real opportunities in material science for that. And then just for the material scientists in the room, holes span all those thermodynamic state variables. Here, for example, energy and volume gets you to pressure. And so you can imagine changing phases of the pressure. So you can do searches not just in composition space, right? You can think about it in terms of electrochemistry too, right? You say, in a battery, how does my convex hull evolve, right? There is one sort of, I put this under the opportunities category because I didn't want to make a new category, but this gets a bright red in the sense that your unknowns are in fact unknown. And so you can do this till the cows come home, but if there's a phase down here that you're not aware of, you really need an experimentalist to come in and say, you forgot something. And so these have to be like tight couplings when you do stuff like this. Okay, vignette 3, let's take a quick look. So I suspect many of you are aware that machine learned interatomic potentials or machine learned force fields, whatever you want to call them, have come out in the last couple of years, and they are sort of taking the world by storm. They barely existed when we started our institute, so you can imagine that we've had to do a little rejiggering of what our priorities are to sort of think about that. The good news is that Boris Kaczynski, who's the developer of Nequip and Allegro, is part of our team, and so that certainly gave us like a good position to like sort of be responsive to this changing world. But let's start with some definitions. So first, surrogate models. These are like these are computationally efficient, flexible models that approximate more complex things, right? And in particular, the surrogate models that I think are taking material science by storm right now, as I alluded to, are these ability to calculate interatomic forces and energies, specifically, usually for molecular dynamics. So we're interested in how do atoms evolve in time in a pseudo-Newtonian world by the time you're done with a surrogate model. So just to sort of keep the continuity here, let's start with thinking about surrogate models for the forces inside of high entropy alloys. This is a good example, I think, because it is extremely hard to imagine some of the other approaches applying well to high entropy alloys. But we'd be interested in energies to think about phase transitions, but we'd also be interested in all the dynamical things that you'd find inside of a solid, lattice dynamics, phase transitions, reactions, et cetera, right? Okay, so machine learned force fields, typically these are graph neural nets trained from density functional theory data, and I would just contrast them to ab initio molecular dynamics, where you're directly evolving the structure within DFT. And if you sort of think about the compute comparison, if this is a classical potential that you're just going to write down by hand, and here's the compute cost of AIMD, machine learned interatomic potentials or force fields are somewhere in the middle on a log scale. But this is actually not a terrible place to be. We have access to something like, 1,000 atoms out into the nanoseconds, like easily, or let's say 1 million atoms easily for structural relaxation. So we have a lot of like opportunities here nonetheless. The reason as an experimentalist I love these things is that you can make them very quickly because in principle the training is not that bad and doesn't require that much human involvement. And further, the amount of training data they require is quite small because the GNNs that you're using are equivariant in nature. And by that, I mean that we can show a crystal in a particular geometry, and the GNN surrogate learns that geometry regardless of rotation, translation, anything like that. And so that's a big deal. So it allows us to get away with sort of stunningly small training data set sizes. Honestly, the whole thing seems just like a miracle that it works as well as it does. So if we're interested, for example, in continuing that workflow of from before of high entropy alloys, we might think about what are the costs of individual observations, and can we use machine learned force fields to provide that cheaply. So here, for example, I show in the same space the delta H mixing for DFT or NEQUIP. And now this is interesting, I think, in particular, because what we're testing on is not just here's a structure, here's another structure, but more like I'm going to start a structure at high energy here, watch it wiggle its way down. Where does it end up? Start the same structure here, but now I'm in NEQUIP, and does it end up at the same spot, or does it wiggle itself over somewhere else? Right, and so it's really lovely that we're able to not only say like apples to apples, but like dynamic apples to apples. That's a ridiculous statement. Okay, so we are excited about using these guys ultimately to predict delta G so that we can think about energy as a function of temperature and using the partition function and the usual canonical ensemble approaches. So we might be interested, for example, in building up a thermodynamic density of states in energy, and then Boltzmann weighing all of these states to get to a delta G. But you can imagine that in a world where you want to propagate uncertainty, that it makes sense to think about, well, there were there's basically a combinatorial explosion of ways in which you could tile this high entropy alloy. And so this is just like a fun aside, but I love talking to my computer science colleagues because they tell me about words that I've barely know how to pronounce, let alone have ever run into before. And so, for example, if you're thinking about like weighted die, you want to think about the Dirichlet distribution, because that basically will allow you to basically allow you to make a guess at the true weight of a die. Like let's assume it's not a fair die, right? And so what we're doing here is binning our density of states into essentially sides on this high dimensional die and saying, okay, what are the weights of this density of states based on the data that we have today, and then drawing possible, or basically sampling TDOSs from that and calculating Gibbs free energy over and over again, which ultimately allows us to propagate the uncertainty through this step. And so there's sort of these like cool math tricks that you can use to push uncertainty through things that maybe it wasn't obvious you could push uncertainty through. So that's sort of like the broad point there. So as an experimentalist, I remain excited about these machine learning force fields, partly because they give us access to things that are really hard to measure experimentally. So for example, you can imagine taking a high entropy alloy of this flavor and asking the question, well, what are the bond length distributions for all of these elements? And good luck, frankly, as an experimentalist. Like, this is just hard, right? So this is at the centroid composition, which is technically an unstable composition. And indeed, you get these broad ranges of bond lengths. Because it's an MD, it doesn't have the opportunity to phase separate. And so, like, germanium sulfides here just going, oh God, what have you done to me? So super hard to measure experimentally. But even more so, learning about the dynamics inside of something this complicated is even more hard to measure experimentally, right? And so we're still trying to wrap our heads around what's going on inside of this big boy. So I have no actual analysis data here, but I'll show another example of some dynamics in a second. Indeed, here. So Ella Fertikin, one of the co-directors, recently put out a paper on looking at hybrid perovskites and looking at dynamics inside of them. This work was inspired by some X-ray and neutron single crystal diffraction, where there was a bunch of diffuse scattering suggesting there was some sort of either static or dynamical motion. Elif came in with MD and basically found that there's the domains of local tilting inside of these perovskites that not only form, but they move around in time within these materials. And so this is on the left side is the experiment, on the right side is the diffuse scattering that you would get from this molecular dynamic simulation. So I think this is a really nice example of, here's a case where experiment sort of led the charge and said, there's something cool to be found here, please go look for it. I think the reverse problem of here is our dynamics is there anything interesting going on in here? Is in a sense actually like a little bit harder of a problem. All right, so what's the punchline here? So we're thinking about the sort of interaction in this AI space of simulation, surrogate models, and experiment. So just again, I think these interatomic potentials are wildly transformative. They allow really like custom specificity in terms of your chemistry and the bonding environments, right? So we're training models right now looking at like ion transport and complex alloys. And they're fairly inexpensive to train, use, and like learn. So I think this is just a tool that's now in our toolkit, and it's like time to embrace that. And I think as an experimentalist, we have access to energetics and dynamics that we just didn't have before, which is awesome. Okay, so this business about training though, this is in my mind sort of where the field still needs to put a serious amount of effort. We have some tools, for example, Flare, that give you some level of uncertainty-informed automatic addition of training data, but it's, I think, not optimal, right? There's, again, tons of opportunities there. And part of this is that the field has yet to develop anything that looks like a good testing standard that I'm aware of. Please let me know if I'm wrong. And I think from the perspective of computer science, and this probably goes throughout the whole talk, when you look at how computer scientists can engage, benchmark challenges are really important. And so what we don't have in the space that I'm aware of are good benchmarking challenges for these machine learned force fields that we can ask, you know, how should we train on this? What is our efficient training methods, etc. So opportunities there. And then finally, when you're looking at dynamics, sometimes it's kind of this needle in a haystack where, it is not obvious how to extract insight. So for example, I was looking at this germanium telluride supercell a couple of days ago. It's a 300 atom cell. Germanium telluride is a sort of a pseudo layered structure, and what we found is that it oscillates at the temperature we were looking at it between being rock salt and layered on sort of a fairly short time scale. Here's the bond length going from 3 angstroms to splitting into 2.8 and about 3.1 or so. And you can see this is like an oscillatory behavior. So this is like a collective oscillation. These sort of collective features are super cool. In this case, it sort of fell right out of the data, but there's no guarantee that it would fall out of the data, right? And so how do you find these sort of collective phenomena on long time scales that are not sort of visually obvious? This, I think, there's a lot of opportunity there. Okay, getting close. Expertise. So I'm going to do 2 super short vignettes. One is focused in on how do we leverage the literature corpus, right? And then the other sort of follows off of that into how do we bring in present day domain expertise and not sort of the past that is the literature corpus. So, but to start this off, I got to lead with the problem that is latent spaces. So latent spaces are these abstracted dimensions into which we project, we place some sort of complex data, right? Back in the day, we might call that a feature space, but that sort of suggests that you know what your axes actually are. So in a perfect world, we would like our latent space to keep all of our critical features. We'd like it to be a compact space in terms of its dimensionality, although maybe less so these days in terms of how important that is. We'd like it to be a space that is generalizable and diverse, which is to say that I can throw new data into this and not like break the space. We'd like to be able to go from that latent space back into whatever our original space was, and we'd like to capture both local and global structure. For example, it'd be nice to have a latent space that like retained notions of symmetry. That'd be cool. So this is a real wish list here. I say these are challenging to construct for 3D chemical objects, but it's like more than that. It's awful. So if there's one thing to the computer scientists I'd ask you to think about, it's how do we go from 3-dimensional objects to latent spaces in a way that checks at least most of these boxes. So to sort of highlight this point, can you build a common latent space for silicon with 2 atoms in the primitive cell, cobalt antimonide with 12 atoms in the primitive cell in different flavors and different symmetries, and then this ytterbium-14 manganese 11 with 104 atoms in the cell, right? You might think, oh, well, maybe I can just like one-hot encode my atoms and think about sort of a 3n dimensional space where n is the number of atoms. but then the number of dimensions that exist in these spaces is different. So that's already problematic. And then the order of the dimensions matters. So this is terrible. You can think about connectivity without distance, for example, things like crystal graphs and stuff like that, but doing this in a way that is comprehensive, it really doesn't exist today. So what I'm about to show you is a kludge. I'm going to fully own that. And then we thought to ourselves, this is like, we started this work back in 2022, I think. And so this is sort of right as LLMs were rising. And again, this is a kludge. Feels sort of even awkward talking about this publicly. But step one, we were like, okay, well, we don't have a good latent space that spans the entire suite of known crystal structures that we like. So we're going to use RoboCrystallographer to automatically encode the text of all known crystal structures. Sorry, encode all known crystal structures into text. Great. Then we're going to use a pre-trained LLM transformer to push those crystal structures into this sort of latent language space, which is kind of cool, right? Because that space is sort of infused with domain knowledge, which I think is kind of fun. We can also do some multitask learning that leverages the space. I'm not going to talk about that now. But in the end, right, we can also take all of our crystals that are known to date and project that down into a two-dimensional object, which kind of looks like, I don't know, somebody spilled a plate of, fettuccine or something. And we can then manually map, and this is going to be sort of one of the points here, we can manually map properties onto that space. That's cool. Right? And in fact, we found a couple of sort of areas of crystal structures that warranted further investigation for the things that we were interested in. In this case, it was thermoelectrics, but it's sort of irrelevant here. So I will say that manually heat mapping projections is just so 1990s, right? I mean, really? Yes, you get to apply a little bit of domain expertise, but I don't know, I'm sort of not impressed. So one of our team members, Remco Chang, and his students have been building interactive viz tools that let you bridge between the latent and the projected space. And I think this is really fun. And so I'm going to end on a bunch of pictures of cats because it seems as appropriate as any way to end a talk. So imagine, for example, you've encoded a bunch of feline data and you've done a projection off of that. And you say, okay, well, step one, I just like to be able to ask what my clusters are in a trivial way, such that I have a view of the predicate space that led to this cluster forming. So basically, there were a bunch of features about these cats, and it turns out this cluster formed because there was a tendency for these guys to all have long whiskers, large body sizes, and they aren't particularly spotted. And then just over here is the SPLOM view, where you basically take the most important features that led to this cluster, and you ask, how are they interrelated? We could move to another cluster. Turns out, we were at lions before, and now we're at cats. Turns out they're not as big. They've got smaller ears, but they still have big whiskers. So reasonably, that should be its own separate cluster. And then, wow, that video goes really quickly. So then as a user, you can sweep through particular regions, and then as I move through this cluster space, what are the most important variables that built this cluster, and how are they evolving in time? And by time, I really mean along this trajectory. Right, so for example, you can see we started over here with tigers, and by the time we're done over here, we ended up with cheetahs. This sort of stuff, I think, is really helpful in a world where we are trying to bring human expertise to the problem. So indeed, that is my second bullet point here. Expert feedback in these really complicated data spaces can be hard to get, but it's, we are experts nominally. We should take advantage of that. And so we need tools to do that. Going back to the LLM business, I think it's super cool that they can capture this sort of contextual knowledge without the need for explicit ontologies. That probably opens up a whole can of worms depending on who's in the office or in this room. But yeah, to me, that's very delightful because explicit ontologies in material science has been a real challenge. So there's a ton of opportunities here, but I'm just going to try to highlight two of them just to sort of bake a seed. I'm just going to repeat again, if we had latent spaces that were robust, which I don't think we really have, that would be amazing, in particular because then we could think about time evolution of dynamical structures inside of those latent spaces. And we would love to have projection techniques that handle both time and length scales gracefully. And to my knowledge, those don't really exist. So if you're thinking about multi-scale modeling, how do you do good projections? Okay, so I'm really almost done. So for the students in the room, you are getting your PhDs or your postdocs at like one of the coolest times in the history of material science, in my mind. There's so many opportunities to take advantage of the sort of AI plus ML revolution. I think it really is sincerely a revolution. It is. I think there's a couple different sort of broad embodiments, right? There's all these existing tools out there that you can go over to your friends in computer science and get weird with existing tools. You can think about new methods and how you can bake physics into them, or you can think about integrating things together to make workflows. I think this is one of the things that when I look back at the 2010s, we really weren't talking enough about. So I would say in general, like now is the time for courage, right? There's a lot of like high risk, high reward things, but it's also the time for partnerships. Right? Doing this alone is really not recommended. And when I think about, this is like my top 4 list of lessons I've learned from trying to manage a group of 60-ish computer scientists plus material scientists, is step 1, you really want to teach people your challenges, but you want to be aware that as you're teaching them your challenges, the language barriers are real. Many of the people on my team do not have a beyond high school knowledge of chemistry and had not heard of what material science was before this institute, right? Like, whoa. So some patience is required. And sort of part and parcel with this is, it's not, I say language barrier here, but you actually have to like put the work in to learn about each other, right? You need more than just knowing what words kind of sort of mean, right? Like I sat down and like coded my own Gaussian process because I was like, man, Gaussian processes are a big deal for this particular paper. I got to write my own. And like, that was a pain in the butt. Thank God for ChatGPT. But that allows me to actually have a meaningful conversation with my computer science colleagues. Okay, I've only used the word inductive biases once here. When I talked with Ryan, when I was prepping this talk, he was like, the one thing you should tell grad students is like, don't let go of your inductive biases. They are so helpful here. So what an inductive bias is in sort of general, it's the set of assumptions a model makes about data to generalize beyond the training set, right? An inductive bias might be physics, right? Newtonian mechanics is a perfectly valid inductive bias. So I think that's where the material scientists, to a great degree, in terms of both, like, okay, identifying challenges is a huge deal, but also like making sure that your solutions take advantage of your inductive biases. How do you think about symmetry, for example? Things like this. And long-term, and Stephen alluded to this very briefly, but long-term, these relationships need to be mutually beneficial. What constitutes a computer science degree is not a co-authorship in, chemistry of materials, right? So with that, you've seen all of these people before. They have been a fantastic group of people to work with. I haven't even had a chance to mention the work from these other research groups spread throughout the US. And so huge acknowledgments to them. And I should have put the NSF slide symbol on here, but also NSF has been an incredibly gracious funding agency because they basically let us follow our nose in terms of what is actually relevant as this field evolves very rapidly, rather than sort of tying us to what we originally wrote. So with that, I have no idea where I am time-wise. Hopefully I'm not too late. But yeah, if you have any questions, happy to take them. Yeah.
You talk about relative differences in computational
Yeah.
expense. Can you put that in like in absolute terms? Like what were the costs, a few years ago, and what are you seeing today, and what are the implications of that, like in industrial? Like what are some like layman like applications that would result from this improvement in computation?
Are you thinking in particular for the machine learning potentials?
The second part of your presentation.
You're talking about within the convex hull stuff and things like that? Yeah, so I think of it as sort of, ultimately you want to make good decisions about what calculations you choose to make, but then you also want to make, so I'm not going to be able to give you good quantitative answers, so don't get your hopes up. But in general, I think, right, you want to make good good decisions that are sort of based on reasoning about where to measure, and at the same time, you want to make sure that any time you're doing a calculation, you want it to be cheap, right? And so I think in many cases, the answer was effectively not worth the trouble, and so the computational cost was infinite. For example, doing these high entropy alloys and trying to get energetics off that. I mean, well, let me actually back that one up. Trying to get local structure and dynamics off of high entropy alloys is insane. And so there's this sort of like whole space of you probably just shouldn't do it because it's not worth your time. It's better to go into the lab. So I almost think about this almost more as a qualitative, like, should computation be involved or not question? Because I think industrially, oftentimes, it's a decision between empiricism and computation. And so I'm really excited about the things that pull us away from experimental empiricism to computation qualitatively. Again, sorry for like not having like a numerical answer for you. Yeah, yeah.
You mentioned that benchmarking is one of the challenges
Yeah.
now in ML plus material science. So I was wondering, what is the current state of that? Like you mentioned, you lab is still embed, materials in latent state. And so I was wondering, how do you measure whether it's doing a good job?
Yeah, so in terms, okay, I don't have a 2 for 2 for I don't have a good answer for you. I don't have a great answer for you on that. I know that between my institute and several other NSF institutes that we have what are called ML challenges, and some of those have material science questions baked into them. But I think in general, one way of actually thinking about this is it doesn't even really have to be material science. Having challenges that are generally in the physical sciences is probably enough. So for example, there's a challenge in looking for rare events in electrical measurements of the brain, right? Developing good techniques for that has, I think, pretty good transferability to some of the time domain rare events things we'd be thinking about in material science, right? So that would be sort of one thing that immediately comes to mind when I think about challenges. I think in terms, and to do this, we have a community of people, both from computer science, who have experience in challenge development, and domain experts, be it in astronomy or neuroscience or material science. And I think like to build these challenges, you actually need to have like input from both sides. Otherwise, the challenge is sort of ill-constructed and not particularly credible and won't draw anybody's attention. So sort of the generic answer is build them with teams. And I think these sorts of questions will sort of get answered. Yeah, yeah. Yeah.
So thanks for an excellent
Absolutely.
talk, Eric.
Yeah.
You've been at this for a while, and you talked a little bit about discovery, design with materials, dynamics.
Yeah.
Kind of alluded to structure at the end.
Yeah.
If you sort of look across those domains, where do you, having been through these exercises, feel like the AI is going to impact the field of materials
Yeah.
most?
Yeah. Okay, these questions just get harder and harder. It probably depends on the time scale. I mean, I think in the short time scale, the ability of these machine learned interatomic potentials is phenomenal. Because for example, I've got a colleague who is asking in excited state chemistry. So we're not even close to the ground state, but properly like photoexcited chemistry. Can we train machine learned potentials that learn how molecules evolve post photoexcitation, right? The quantum mechanics is going to be a little different than the ground state because you now got an electron in a different orbital that it shouldn't be in, right? But nothing stops us from doing that, right? And so that willingness to get weird with these things and just the breadth to me is stunning, right? And I think in general that sort of goes back to really what Stephen said a while ago, which was synthesis is hard, right? And so my hope is that the synthetic side of material science will sort of feel the similar impact that the rise of DFT in the 90s and 2000s brought to properties, right? Because when I look at your average synthetic group today, it really kind of still looks like 1970. I just came back from the MGI annual meeting, and there was a lot of discussion. I love having this on YouTube right now, so hi NSF. There was a lot of discussion about automated labs and things in that space. And I think these sorts of sequential decision-making things certainly have a role to play there. Whether or not automated labs are all they're cracked up to be is an entirely another discussion, given the long tail of actual number of material science labs. But at least for some people with the resources to have an automated lab, it almost feels like the less interesting part is the robotics, and a lot more is the how do you make decisions and on evolving data sets that you, by definition, did not know what they would look like beforehand. Because if you knew what they would look like beforehand, you wouldn't bother making the experiment, right? And so how do you have like automated labs that handle extrapolation well, right, in terms of decision making? That sounds hard, but if you could do it, it'd be cool.
Automated labs might keep you from making extrapolation.
Well, I think this, indeed, right? This is my real fear. Like in 2016 to 2018, we had a bunch of ARPA-E funding to build like a ceramics-focused automated lab. And building something that allows synthetic generalizability is really hard, right? It's all well and good to build a bread factory that only makes Wonder Bread over and over again, right? We're great at that sort of automation. But if you say, I want to build a bread factory that can make anything out of flour and yeast, that's a whole nother factory in terms of what that factory looks like, right? Where you say, today's croissant day, and suddenly it spits out croissants, and tomorrow's baguette day, like, and you want that in every one of my labs across the nation? Good luck. So no, I hear you.
Maybe building from that
Yeah.
point, like, is there any, since you were just at this meeting,
Yeah.
is there any discussion, like, if you look at the I guess the history where people try and predict now, you have a phenomenon, you're trying to explore material phase space to try and optimize that or something, right? And
Yeah.
at least in every situation I'm aware of, like when people do that, they sort of fail to best the already best in class in most cases, right? Because people are pretty good at exploring these phase spaces, right, over time, and there's many of us, and we're all independently trained and
Right.
So how do you? Is there any recognition of that, perhaps?
Yeah, and I think part of that recognition is simply trying to move away from an AI plus ML sort of perspective, like moving away from I want to directly beat that which is best in class, right? When I think about sort of DemRef over the 2010s, most of those proposals said, here's the state of the art. DemRef was built as a program that went from discovery all the way to deployment, and so in principle, most of the DemRef awards had some metric that they were trying to improve, right? And you're right. Most people, in a sense, failed. Myself, certainly, we failed, right? So I think the way around that, in a sense, is to not think of this as humans versus computers, right? But to think, where can computers, or where can AI, whatever you want to call it, give humans the insight that they need to do what you just said, right? And so, this used to be called sort of centaur science. I still think it's kind of a cute word in the sense that you should have humans and computers sort of merged together. Probably should be called cyborg science instead, right? I don't know why horses had to get involved. Yeah, this business about not being directly metric focused, but rather thinking about how do we make materials, or alternatively, how do we understand the properties that they currently have better, and using that in concert with experts to make good collective decisions, I think it's got to be the way. Well, got to is a strong word, but yeah. Is there somebody in the back over there? No? Okay. Cool. Should we shut down?
Oh, I have
One more. What you got?
The last one.
Yeah, yeah.
So on the inverse design problem that you started with, I guess I saw a talk recently on optical metamaterials.
Sweet.
Which is sort of inverse design problem, and this person had built their own sort of custom machine learning model to try and predict functionality in those cases. But then they just took it and they just went to GPT and just fed the same information in, and
Yeah.
GPT was better. So how do you deal with that? If these large language models can do some this emergent behavior that comes out, sometimes they can just beat these sort of tailored things.
Yeah, I think the answer to that one's actually fairly clean. Look for systems that are nonlinear, highly coupled, and complex, right? And language models, would never be able to give me the solution. And I think I can say that sort of categorically. It will never be able to give me the solution that is actually backpropagating out of that loss function to, in one case, protect that astronaut, and the other case, focus all that energy toward the astronaut, right? I mean, that's talk about, sort of the extremes of coupled systems, right? I mean, they're literally coupled. So I think, but this is a good test, right? Like, I mean, when we write homework problems, we now ask, can ChatGPT solve this? And then it's like, oh, is this a good homework problem, right? Yeah, cool.
Thank you.
Yeah, cheers.
And with that, we'll thank you.
Still hot.
So let's take a quick 10-minute break. We'll come back at 10:15 for the panel. Thank you. Test, test.
Okay, I think we're ready to begin our panel discussion. So if I could ask the panelists to find a seat up here. I'm Teresa Pollock. I'm on the materials side of the discussion today. And who is our last panelist? I think we should have, yeah, okay. So as William said at the start, this session is really meant to bring people together and talk about the opportunities And I think, from a materials perspective, opportunities look very different depending on where you sit. As academics, we inevitably are tempted by discovery. I'm happy to see that we'll have an industry talk later today because that's a completely different perspective. As Stephen and Eric mentioned, a lot of the synthesis challenges remain unaddressed so far. And so, from my perspective, there's much to do on all fronts. And so we have a distinguished group of panelists. And so I'd just like to first start by having them quickly introduce themselves. And then we are going to circulate back through the panelists and maybe have them spend 5-ish minutes talking about what they see as the challenges and opportunities. I sent them a list of questions, so they may want to be more specific. And then as we go, the audience should certainly jump in with questions and comments. We really want this to be a discussion first and foremost. So let's start with introductions.
Hi, I'm Una Kim. I'm a quantum many-body theorist in physics department at Cornell. And I've been mostly interested in trying to leverage ML for better understanding properties and being able to predict in quantum materials and quantum many-body physics sphere.
Morning, I'm Bud Singh. I'm mostly in AI ML, but with my colleagues, trying to understand materials. Just as a pointer, to me, DFT meant something else till 2 years ago. So it was a complete change of terms that I had to learn that no, DFT means something else now. Okay.
I'm Anton van der Ven in the materials department here at UCSB. My area of research is in first principles statistical mechanics. We try to predict materials properties from the electronic structure.
Hi everyone, I'm Murphy New from CS department. I actually recently joined, so I'm extremely honored to be on this panel. As if I have anything to contribute. No, I have things to say. Because I have worked a lot on using machine learning to improve different, level of the stack of the quantum computing, and lowest level in regard to how do we design better coupling between qubits, right, in regard to the coupling graph, to how do we improve or realize quantum gate better, to how can we design quantum circuit better, to how can we design better decoding for quantum error correction code. And recently I'm also looking at what type of applications quantum computing can have in regard to material science when we combine that with machine learning.
Welcome to Santa Barbara.
I'm Sam Daly. I'm in the mechanical engineering department. I do experimental mechanics of materials, and at the intersection with data science, machine learning, for a variety of things, ranging from something a little bit as straightforward as like high throughput experimentation, image segmentation in terms of like the way we're using it is fairly straightforward, and going up more and more in complexity in terms of multimodal data sets with my colleagues and trying to figure out multimodal data sets, spatial, temporal, and how you handle and utilize all this data at different resolutions and different modalities.
Okay, thanks to all of you. Would anyone in particular like to start, or should I pick someone to start? Ambush.
No, I said you should pick. No, I didn't put
I did pick.
Thank you. I just have some notes. I want to make sure that I stay true to what I'm saying. So for me, from looking at the field from the AI ML side and then trying to understand what are the questions that I find of challenge, I'm going to name two of them. One is trying to understand symmetry, and the next thing is to try to be doing reasoning in such systems. So I feel that trying to understand the kind of symmetry and how it evolves as you start from the lower scale to the higher scale, and what are the couplings that are allowed between the different kinds of symmetry. I mean, Eric pointed out this question about the latent spaces and how do you encode the kind of symmetry that will possibly show up in the latent spaces, and how do you define it? Do you, as a scientist trying to build a system, do you say that this system you're trying to build will have this kind of symmetry, or do you allow for the symmetry to be learned based upon the data which is out there? Or do you go somewhere in the middle? So do you design a variational method that will look at you define that these are the possible symmetries and let that be learned based upon the data which is out there? And then we heard about this question about the dynamics, and it is possible that over time the underlying system you're trying to study goes through a phase change. And how do you allow for the fact that the symmetry itself is going to be changing over time? And you have built a latent space. Will the same latent space be useful over time when the symmetry has changed? And there was this question that Eric asked, what's the number of dimensions that you would have in this latent spaces? If it's 3n, as the value of n is changing, would you? So I do think that there will be different kinds of latent spaces based upon the kind of symmetry that is being allowed in the latent spaces. But at the same time, there will be mappings between the different latent spaces that if the system that you're trying to study goes through a phase change, there will be some kind of the smallest edit distance that you'll have in terms of the system that had one kind of symmetry, that it would be going to different kinds of symmetry. So, and then this question about how do you couple systems that are across multiple scales? How do you look at the crystal structures? They will have, I'm told by my colleagues, I hope I have my numbers right, some 256 different space groups, something like that. It's between 200 and 300. So and then you go to a microstructures, and they would have their own symmetries. And how do you couple the kinds of symmetries that show up across scales? Then this question about reasoning, right? So I think we have done really well in terms of building what are called System 1. Well, they will take all the data and they will have an outcome, but reasoning is always very difficult. And for these systems that are very complex, how do you build the factual and counterfactual reasoning systems? How do you explain why the system you have has this property, or ask a question if you were to make a change, if you wanted this system to have slightly different behavior, what is it that you wanted to change? So we saw a unit cell with, what was it, 60, 100 different atoms. And if I were to ask, why does this structure have this property, and what is it that if I wanted to change, which atom would I need to change for it to have a different property? So the reasoning is where I think there is a lot of work that needs to be done. And then this question about jointly trying to develop a reasoning system along with a predictive system. I think it's much more difficult to do your reasoning in a post hoc manner. It needs to be done at the same time that this system is being designed. And then going back to this question about symmetry, your reasoning has to be aware of the underlying symmetry that is in the system. So you have to be able to explain the reasons, do your counterfactual or factual reasoning that understands the symmetry in the system, right? So you can't say that if you rotate, if it's got a rotational symmetry, you can't be saying that if I rotate this crystal, it will have a different property. It has to be aware of the underlying symmetry. and the language models, right? I just wanted to end with this idea of the language models. It's very difficult for us to be doing reasoning using language models, and reasoning using symmetry. It's difficult. So we are right now seeing, to the extent we are trying to do some work in, to what extent can you get a language model to understand symmetry? And we are seeing if it is possible to teach them symmetry, because you may see some paper that has been published that has a figure somewhere in there, and then it says what is the symmetric group of the crystal structure. You want the language model to understand that text where the symmetric group has been described and the specific figure or the specific measurements that have been made, and be able to reason that if you were to rotate or reflect that crystal structure, it would have the same outcome. So how do you actually do it? How do you build these aspects of equivariance and symmetry as a part of the reasoning about language models? So my last thought is, how do we train students that can do all of these? So it's clear that these will not be students that will likely be just in materials or just be in AI. They'll have to be taught things at the junction of the two disciplines, and it's not clear how to do that.
Okay, so thank you, Ambuj. The topics are symmetry, linked scales, reasoning, and education. That's a big landscape. It warms my heart to hear a computer scientist talking about symmetry and phase changes and crystallography. So we want the audience to comment, engage, question. So do we have any questions or comments at this point? Yeah.
Thank you, Ambuj. I am one of Ambuj's PhD students. My name is Madeline. I'm in the computer science department, but I collaborate with a lot of mechanical engineers as well. On your last point about education and the question of how to train students, in the past when I've worked on interdisciplinary collaborations as the, bringing the machine learning element to the team and the domain scientists, everyone meeting in the middle, there seems to be an imbalance in accessible resources for people who'd like to study up on machine learning versus people who'd like to study up on insert your domain science of choice. For example, there are plenty of resources online that explain transformer models with making very little assumptions about, prerequisite educational background. In my experience, that doesn't really exist in a lot of the interesting domain sciences. I'm curious if the domain experts could weigh in. Do those resources exist somewhere for your field? Are they in, are you desperately in need of those? What do you see as the path forward there?
That's a really interesting question. This is something that I'm working on, that I care deeply about. I think before the age of LLMs, we kind of gave up. We resigned that unless you went through so many years I'm a physicist, okay? And unless you went through so many years of math and physics education, you simply are not going to understand me. And we live in a different tribe, and we speak different languages, and we're going to just accept that, right? And people go to the extent of saying, my physicist colleagues like to say things like, physics is what physicists do. So then you have to define who physicists are. Then you start to kind of draw the line. I'm a physicist, my friend is a physicist, you're not a physicist, you won't understand me, but that's not my problem, right? And I didn't know how to change that. I would like to be able to change that. I didn't know how to change that. I think with LLMs, we are entering different way of learning. Right? Why is it hard to learn from other human beings? it is in a way nice that you have a human interaction, but it also puts you in this position of insecurity. Like people can be judgmental, and you don't feel like you can ask them every single level of questions going back down to high school physics. If you haven't taken high school physics, and if you have to go back down to high school physics, you don't think you have time, some experts' time to do that, right? I think the reason why for machine learning there are a lot of resources is because there are many open source codes, and codes follow clear rules. Codes sit squarely in one language. But science ultimately do not sit in one language. And that's becoming clearer as we try to use LLMs to study science. For physics, which I understand the best, physics sits in mathematics and language as in English, because we use words like energy, momentum, but we have very specific meanings to them. And you need to be able to use them interchangeably. And in addition to that, there's also a notion of measurement and how data is presented. So we need to be able to, as a physicist, you need to be able to kind of work with all three of those kind of interchangeably. And when somebody wants to learn physics, they have to not learn one language and one syntax and one set of rules, but they have to learn like 3 languages all at once and become trilingual and be able to communicate and turn around, speak real-time translate. It's hard. But I think with LLMs, which allows you to keep asking questions and surface examples, surface videos of talks, we can kind of relax a little bit and recognize ultimately it's sort of a form of language. Like the domain-specific terminology and concepts are sort of language. But there's in physics, in mathematics, there is a kind of very stringent backbone that gives us structure, which allows us to be efficient in calculations and predictions. And those, you kind of have to learn that. But I think a lot of it can be actually learned through immersion, because that's how we were trained. We learned through immersion and doing a lot of exercises. But you don't have time to do that for 20 different domains, right? But with what I'm working on right now, developing, is the kind of tool that allows you to ask questions and answer the questions grounded by factual citations and factual evidences in experiments, in literature. So I think this is an important problem that we have to overcome, and we cannot stay in the modality where we had been because we have opportunity, but it's not a solved problem. However, I'm very optimistic that we can address this problem.
Okay, other questions around those topics? Okay, good.
Yeah, thank you both to the question and the answer. And I also have some thought along this line because I'm teaching this undergrad class on quantum computing, introduction to quantum computing, to students of zero background. That's what I told the students. And while I teach that class, I realized, so I am a physicist by training, but I work at CS department. And so this Nobel Prize this year really made me think about, the boundary between the two. But also this question made me think about what's the advantage of having this type of interdisciplinary approach of both teaching and research and, the categorization of impact. So when I teach, I realize as a physicist, I have a lot of assumptions, like this trilingual type of background that I assume that students in some sense share. And not until I start teaching, I realize it's very, very different type of language that we're using, but also different level of abstraction. Like I feel like physicists, they do abstraction, but they also are very grounded in numerics, in calculations. But in CS, we might want to kind of abstract that away a little bit at the beginning, at least, And I have seen this happening in industry. So I come from Google. I have been Google Quantum for 4 years before I joined academia. And I noticed that in industry, a lot of hires, people who get hired into the team, they are not trained physicists. But they were able to learn the part of the physics that is bare minimum to be useful. So that if you're a problem-oriented learner and you first define the problem you want to solve and then try to learn what is needed, then in that sense, we might be able to unite different type of approach because the problem is well defined. Right, and as a researcher, as a student, if we, that's the temp I'm trying to think, which is maybe we can orient our type of teaching and interdisciplinary preparation with problem. And I think this gathering here is a great opportunity because people are here to think about problem. What kind of problem that we cannot solve without machine learning? What kind of problem that we cannot solve without also deeper understanding from physics and combining that with machine learning? So that's my short take on this.
Okay, thank you. And speaking of teaching, I'd like to introduce our next panelist, or I guess have him introduce himself and maybe say a few words about what you think is important at the moment.
All right, hello everybody. Sorry I'm late. I'm teaching and it's midterm season, so I was harassed by my students. I couldn't leave. So my name is Frédéric Gibou. I'm a faculty in mechanical engineering and computer science. I'm one of those people who've been working with a lot of people from different domains. So I definitely do get you in it's hard sometimes to figure out, what exactly is the crux of a field. In terms of people are talking about LLM, not surprisingly, the thing I would add is, so LLMs in general are extremely big. They have hundreds of billions of parameters. They cost quite a lot of energy to run. There's an opportunity to build smaller models. I think Stanford has done something like this. They did an LLM that has, I think it's 2.7 billion parameters for the biomedical research. And not only it's something that's smaller, more specialized, but it does a better job. And so that brings me to the idea of in science, LLM can be very useful to search literature, etc. But if you want to predict something, I believe there's a big opportunity in building those foundation model and building them in such a way that they follow the science, right? It's in LLM where you look at the vast amount of data that exists, and LLM is going to be trained to find something that does exist. When you want to predict something, you want to predict something that has maybe some non-equations, some non-symmetries, etc., and you want to be able to do that in the language. And so I really think there's an opportunity to build smaller, specialized model that are tuned to do the task that you want to do. And it might be something that we can build from the ground up, not start from LLM and then try to tune it, fine-tune it a certain way, but really build from the ground up. And the last thing I would say is, machine learning is a new tool, is a new period of discovery. It's not something that should replace what has happened in the past. And by this, I mean there's a wealth of information that exists that should be used to train other model, not just do things blindly. Like for LLM, if you give an answer 3 different ways as a language, somebody is going to understand. If in science, on the other hand, there's a precise equation, there's a precise answer, and if you off by a little bit, you're just wrong. And so I think it's quite important to be able to put the real science, the real equations, when you train the model. You train the model not to fit something input-output, but also in such a way that the symmetries are conserved, the equation are conserved, etc. That would be my 2 cents.
Okay, thank you, Frédéric. Any questions, comments before we move on to the next panelist? Okay.
Hi, I'm a computer science student working on large language models. So the larger model, the generative AI is like currently the hottest topic. And when we think about how we use the larger model for the material science, so I'm thinking like what's the advantage of using larger model for material science, and what's the most suitable task for larger model, and what task the current larger model can also, and is text the only modality we need to handle the material science task?
So when Teresa asked us what was, some of the real challenges that we saw, the first thing that sprung to mind was no text is not the only modality, which for me, the first thing that sprung to mind was how we have all this information out there. So especially coming as an experimental mechanician, experiments are expensive and we need them to understand materials. But they're really time and cost expensive to do. We have relatively few experiments, but we have a lot of data on them, right? But all the data is kind of scattered. Some of it's in text, like you get and I'll talk a little bit about it in my presentation today. And when I was talking about the different modalities, I just pulled up a couple of our papers and it was super easy to find. Some of the text was in a table, some of it was in a plot, some of it was in an image, some of it was in language, some of it was just in a single paper. Like I just really rapidly pulled out examples of all these modalities that are describing, problems and that are really critical. Like a materials paper may say, this composite is this type of interface. Hey, it's a weak interface, and then it may have a picture of something. And it may have a picture of that interface, and it may have some damage. And in order to understand the entire forest of knowledge, you have to put all the trees together, right? And so for me, that is the biggest challenge that we have. Is no, text is not enough in material science, right? And in most CRML, it's not enough, right? You need to figure out a way to put together all these modalities, and not only that, but let's say you have a picture, I talk about this in my presentation, but a picture of a dislocation, right? Which is a kind of an atomistic mistake, and it drives like how materials permanently deform, right? So you've got something happening at the nanometer scale, and maybe you take a picture of it using a transmission electron microscope, and then you've got the deformation happening, like you yank it and it deforms a certain way, right? How do you take those two papers? How do you take those two pieces of information, and maybe there's a textual description of how it's plastically deforming, and you have a image of the disc. How do you connect those, right? And how do you inform the model, that these are important? And I mean, there are some pieces of information that, by all means, from a computer standpoint, look like they should be connected, but if you connect those pieces of information in material science, you're going to go down a completely wrong path. It's a complete red herring, right? You change the percentage of nickel and nickel titanium stents, biomedical stents in people's bodies by 0.1%, and all of a sudden you have a completely different, don't put that person in an MRI because you formed a ferromagnetic layer and you're going to kill them. So you some of the extrapolation that you do when the mechanisms change, extrapolation becomes extremely dangerous in mechanics of materials and in material science. And so there are just a whole host of challenges, but combining modalities is one of the best ways that we can address that, right? And I do think we're going to have to figure out on a larger scale energy efficient AI to be able, we need it, right? To be able to look at all these, really use all the literature and explore these spaces. We need to figure out a way to do better AI, more energy efficient AI. Yeah, and that's not my field at all, but.
Okay.
Yeah.
Follow-up questions on that? Comments? Go ahead.
I also really like your comment about interpolation or dangerous interpolation. So one kind of material that quantum people care about is, what you use inside the superconducting qubit, the Joseph junction, aluminum oxide, or maybe you want to have other material. And the problem with that is it's an insulator, and there's a lot of defect where one atom got stripped away and creating a local dipole moment, which can couple to the qubit, which also have dipole moment. And same thing with solid state qubit that other people also have in UCSB. And so it's a mystery of, how these two-level defect got created. And there's different physical theory about that. And But the problem is to fully understand them and about their dynamics, we need like huge amount of data and models, like better models. Otherwise, we can't afford to just brute force simulate their interaction. And so when we did that back in 2019, we were trying to like come up with better way to use machine learning to predict the parameters of these models. But the problem is these models also change with time. Moreover, they change differently. Like there are like different type of defects that we're trying to understand. But just looking at those data, and also those data come in very different modality, or the simpler version of modality is you have finer grained data and coarse grained data, and it's very hard to translate or use them on the same level. And moreover, if you don't have a model, if you don't have a physical model, just using data to predict their movement doesn't really give experimentalists any confidence, because why do I believe in our machine learning model? But if we can come up with or extract or the interpretability of that model to build a physics description of that system that actually help advance our knowledge of material science, then it completes the full circle, because we start from data, we end in model, and then with model we can predict better data and without like large machine learning model. And I'm hopeful that combining like traditional machine learning model with LLM can potentially help us to increase the interpretability of this type of model. And but I do think it takes a lot of this interdisciplinary effort between physicists who actually interact with this process to think about the model definition space, what's the model space, and with machine learning experts to come up with more efficient machine learning method.
Okay, Sam, and then Anton, who hasn't said anything yet.
Just that you make such a good point about like a lot of the iteration and experimental design and everything. That's all built. That's going to be built off the backs of being able to interpret data and being able to handle it and manage it, right? And so again, it's this combining modalities, energy efficient AI, all these things that we need as a to me a fundamental base in order to do these really interesting kind of iterative designs, things like that. You have these fundamental pillars that you need.
Anton.
Yeah, to come back to the large language models, I think it's very impressive that it works. So the algorithmic structure of it is kind of impressive, and instead of just using it for language, I think there are many opportunities to adapt that algorithm to other situations. So, for example, something that is aware of the periodic table, all the different elements. If you take, for example, silicon, and you mix it with a metal, you dissolve it in a metal, it behaves completely differently than if you let it react with other silicon or germanium, because it forms covalent bonds in one case and other kinds of bonds in the other case. So the interactions of this atom are very context dependent on what other atoms are around it. And I'm sure there's a lot of activity in that area, but I think there's a lot of opportunities there of adapting the large language model algorithms to kind of learn this context awareness, right? Give it that kind of awareness.
Make a remark about. So this idea that I think it's good if you can solve something by fine-tuning a language model, but in some ways, the most useful thing about these language models is they are able to combine lots of different sources of data. So there is something that emerges at scale. And you may lose that if all that you're doing is fine-tuning. I would rather build a foundational model for a specific domain than take a general purpose language model and then try to tune it with no matter how many examples you can find, but still that will not let any new ideas emerge. That's what I think in terms of trying to develop a foundational model versus trying to fine-tune something that already exists.
So I kind of resonate with that point of view. Whether you're going to develop like from ground up, from scratch, develop a model for a specific problem, or take some generic LLM, what seems to be really important is reducing the space of search through imposing constraints. Symmetry is a constraint, but that's not the only constraint. There are laws of nature that we figured out. How do we figure them out? You know, history of human history, through our experiences, we've seen something happen over and over again. If I throw a ball up, it falls down. And that kind of led to the understanding of the principle of mechanics. If you give LLM lots of images of the trajectory of ball going up and down, and then say what would happen if you throw the ball sideways, right? If it doesn't know that ball going up and down, if I throw it and falls it down, that there is the law of mechanics, that there is gravitational force, and if it just extrapolates, it will say if I throw it sideways, it's also going to come back, but it won't, right? So if we don't constrain, if we don't impose, if we don't inject human knowledge and the understandings of laws and constraints, then LLM ends up having to waste, or any model, any ML model, ends up having to waste a lot of energy in totally useless space where things are just not physical. Something that that even 3-year-old would know to be nonsense, just because 3-year-old had 3 years life experience. So I think that's kind of really critical, whether we can utilize our knowledge and make that part of the model, and perhaps building from ground up is more natural for that purpose. But there is a challenge of like if you try to build up one model for each problem. So there maybe is sort of a balance between whether you start from ground up or whether you start from something generic. But the problem, the challenge that we have to address is, can we put in, how much can we leverage the principles and constraints that we know must hold so that we don't get nonsense? Like hallucination is just laughable, with language, because we post-select. You ask a question to ChatGPT, it says something, it can hallucinate, so we post-select. But it's not acceptable for science, right? So that's really challenging. I think that's one of the challenges.
Thank you. I totally agree with Professor Kim. I think it's really important to look at constraints, and because one of the things we learned in the past is that language model, they don't follow rules very well. So if you have very complicated rules, they don't follow it very well. But I think in the recent months, there's a big advances in the area is OpenAI's O1 model. In the past, when people were looking at chain of thought reasoning, they were doing it in the inference time. But now we hypothesize that they did massive scaling of, maybe annotation of this chain of thought reasoning, and maybe they fine-tune it in a way that if you try, O1 model from ChatGPT, it gave very detailed reasoning paths about what's going on in that space. So we actually created some benchmark in variety of domains about how language model following constraints and rules. In the past, for 4.0 model, it did horrible. Like you said, it just didn't work. But we were also very surprised if you run the O1 model, it dramatically improve over the prior approach. So then my question to the panel is, maybe there's a way forward that if we can invest, let's say really $20 million doing all this annotation about, materials, physics, quantum physics, annotations about the processes. If we do that, if we scale and we fine tune, would that make any difference? But of course, resource is one thing that I think is a completely different topic. But I'm just questioning about the, if we do things really at a bigger scale, would anything change in the target domain?
The panel chair does not want to talk about resources, just what's possible. So, what is possible?
I think it's feasible that we could have a foundational model for AI for science, which would allow us to bring in, based upon the domain, the specific knowledge, specific rules, if you're going from physics to chemistry to optics, you can bring in. So it should be feasible. I don't know if one can do it for. You mentioned a term which our panel chair doesn't want. I think that...
You could guess about who would do it, but not how much it would cost.
I mean, that guess is, I think, is going to be much higher than the number that you said. That's...
So how do you build it in pieces?
I mean, my thought is that it's something that has to integrate information from many different domains, many different scientific domains. Just as, and I think trying to train this model, we'll have to look at published papers, we'll have to look at data that is in the different labs. I think the kind of knowledge that this would need to be trained on, it will be much harder to find than what the GPT-4 and all that entire family has been trained on. But if the scientists are willing to open up their vaults and their data collection, I think for the scientific good, I think it is possible to train these kinds of models.
The Google person has something to say.
Yeah, so I think that's a really good question, which is, if we have the access to bigger set of data, more fine-grained labeled data, what can we do? So I have one example where this scenario actually played out. So we had this project on trying to build better quantum decoders, so decoding error-correcting codes of quantum computer. And it's a very challenging task because we're really trying to infer is how quantum dynamic play out, right? How different states propagate outside of computational space and keep propagating around. And so in the end of the day, you really have to simulate the whole quantum system in an imperfect sense to know the true answer. So it's a very hard, challenging task, and we're trying to decode the state-of-art size of system. We're talking about distance 5, which is 5 times 5, 25 physical qubit, but 50 total qubit with coupler. So the 2 to the 50, it's gigantic, and you don't want to deal with that type of system. So at the beginning, we only have access to very small LLM, like a simple transformer of a couple million parameters. And I was just working on this on the side, and it seemed to work for a small system. But whenever you try like real small system, like experimental data for a small system, it just stopped working. And then so that project was just progressing, but kind of slowly until Google DeepMind coming, and so Google DeepMind team, actually from the AlphaFold team, they decided, okay, this sounds like a sequential problem, right? We're trying to see the bits are coming out of the quantum computer, predict what's the actual logical state given this sequence of bits. It's a little bit like protein folding. You just fold one by another, and then you decide when it's ready. And so what happened is we just threw an AlphaFold model at this problem. But then you have a giant model, right? The giant model, we're talking about 1 to 2 magnitudes more parameters. But we don't have 1 to 2 magnitude more data. How can we solve this problem? So I think there are ways forward if you do understand physics, or if you do have both certain level experiments and physics. So the way we tackle this issue is we know that we have access to a small amount of data from real experiment, but we also know the correlation among those data. So in regard to large language model, you can think about like attention spans. And we can prove for like realistic errors, the attention span for this type of experiment that we will do is no larger than say 8 or 9. Then we will just basically build a parameterized probability of these possible attention span and fit those parameters from real experiment. But once I fit that from real experiment, I can produce infinite amount of samples from this empirical distribution that's a combination of our physical understanding of what could happen with finite amount of data set. And so that's really a turning point. So then once we have this access to infinite amount of data, this AlphaFold just like become like a killer app in that even we train it on a small size system, say distance 5, like 50 qubits, it can still work for distance 17 system without changing the size of the ML model. So I think this type of thing needs to happen for broader application of material science, right? Where how can we understand the feature of the data so deeply that we can produce new fake data, but without losing the physical property that we want to capture about the data.
So if I can make a remark, that's almost like building a digital twin of the actual material system, and you're using the digital twin to try to generate all the data you need.
Yeah, I mean, I just maybe somewhat provocative. I don't know. Like, there's always this conversation about needing more data, and that and so I find your comment interesting, right? That you can actually generate new data, because I think a lot of times the experimentalists get blamed for failing to provide their data, but in my experience, most people are open to sharing their data in the fundamental research domain, but it's largely an unfunded mandate. So people kind of don't want to share garbage data, right? So then the next question is, okay, well, why don't you annotate it and make it, make the metadata cleaner, et cetera, et cetera. So then, at least from my perspective, this always just rolls down to, isn't that what's in the paper, right? Isn't that the distilled analysis? So why can't we just learn from that in a broadly context rather than demanding more raw data per se? Yeah.
Something that's really interesting is human experiments are expensive, right? And indeed, there is the literature that reflects all the experimentation that human history, that we have done. Why can't we learn more from it, right? When there is an open problem, some challenging problem in a field, what that ends up doing is that if there's so-called long-standing problem, means there's a long-standing pile of literature, and it's often very hard. It becomes harder and harder as generation moves on. One of the really important problems in my field of strongly correlated systems is high TC superconductivity. It was discovered in 1986, and people who have aged with the system, with the time of the field, kind of know what happened. But if somebody just enters now 9,000 papers, you cannot read 9,000 papers. Now, maybe LLM should help, but the problem is, so I interact with LLMs often a lot like how I interact with my kids or my students, which are kind of similar. So, when I ask questions, so when I ask my students to read a paper, so I want LM to be able to read the paper and process and boil it down for me like a good student, right? Not the entering student, a good student. So entering student and good student are different in the following way. Good students who are ready to leave and start their own group know if I've been keep telling the student, you don't read the text. You don't read the words, because words are agenda of the author, which you kind of need to know. You need to know what the author wanted to make of it. But what might be much more meaningful is what the data had. So you want to look at the data visualization. So we say, look at the figure, don't read the text. Can LLMs, so you really need to be multimodal. You need to, multimodal not in a way recognizing a picture of a cat as a cat. If scientific plots, you have scale, you need to know the axis. Is it log scale, linear scale? What is the unit? So you need to be able to understand those numbers. You need to be able to understand the ticks. You need to be able to understand when there's a whole bunch of data points in the plot, what would an experienced researcher look at? Like, experienced researcher might be interested in only some part of that plot for really good reason, but it may not be said because it's all known in the field. So I think there is clearly a need to make data sharing and standardization really happen so that it is easy for researchers to share data. But also there is a lot of need to figure out how to better make use of the literature. And how can we extract more of the experience in the lab of the author who eventually published the paper, not just the words in the paper.
So if I may follow up to reinforce your message. So we recently tried an experiment on ourselves, which was, wow, we have this big set, multimodal set of data, and we should share it. And so we embarked on writing a paper for Scientific Data, the journal. And it was the most painful paper we've ever written, partly because the journal doesn't care what you think, really. It just cares that you present all of the information in a way which leaves no doubt as to what you meant and what you did and how you got it. And so I think that's the difference between making the literature useful for some other purpose down the line versus the normal paper that we write. And so as journal editors, which probably every single one of you are, is there something we can do, at least in the supplemental parts of the papers, to at least let us leverage some of the data and to follow enough standards so that it can all be used or reused in some way.
It's so painful, right? I mean, okay, I made the mistake of using this Dryad service once, right?
Yes, we used Dryad in that process.
It's curated, right?
Yes.
So there's a human being that looks at it and comes back to you and says, this is insufficient annotation. And then, you have to sit and spend another few hours doing this.
Yeah,
right?
yeah.
And
yeah, are we willing to do that when nobody's covering our time to do it? Right, it's the time factor. So maybe if there are tools to do that better, but I don't know how we take some of the human out of that loop.
I mean, I think some of this has to do with the scientific process itself, and that needs to become more open. I mean, I think there has been a sea change in terms of the CS venues, because there is the open review system where you not only have access to the papers, but you also have access to the reviews of the papers. I think I personally find as much nugget reading what others thought of it, and it's published. So I think in the same sense, going back to what is the author's text, I not only want to read the author's text, but I want to read the reviews, what they thought about the paper, and where is the paper going to contribute. If there was some way to make that entire process more open, perhaps it will be much easier for a language model to understand what is the impact of the paper. One does not have to just look at the text as written by the authors, but also what did the field think about what was the important aspect. And I think that could be useful information in terms of trying to understand the paper itself.
Okay. Then I'll come back to you, William.
Thank you. I'm just going to follow up on that. I mean, it's really interesting, right? Like, what is the future of knowledge in the age of LLMs? Like, why write a paper at all, right? Like, why don't just put a bunch of figures and then just render a paper that is personalized to my gaps in knowledge or not? And I mean, why waste your students' time writing? How much time do they spend doing the narrative part of a paper? And is that like, are we just playing some sort of social game instead of discovering new stuff?
I have an answer to that. So like, I just did a group meeting with my student, and the student just presented a whole bunch of plots. You know what I asked? I was seeing like 12 different plots, right? And I asked, what do you draw from this? Because plots are very hard to remember if there's a whole collection of it. But I think the reason why it is important to go through the exercise of writing the narrative is because human brain is very trained on stories. So even before written letters existed, the communities without the written letters passed on their history through telling stories from generation to generation. It's just so deeply in our brain. So when something becomes a story, we can remember the story, but we cannot remember the plots. But only when we can remember something, that knowledge can become part of something that we can build on. So I think the exercise of writing the narrative is important. Now, should we have to spend as much time as we are doing, can the paper be reduced to 140 characters? Maybe. Maybe we don't have to spend as much time, tightening up every line. And in a way, when we use, Grammarly or whatever else, we now can save time in, putting together a sentence while owning the message, right? But I do think turning into a narrative is important, because once it was an important training for my student, because she had some message that she drew, but she never spelled it out. She never typed it up. She also did not specify what was her reasoning for coming up with that message. So I had to press her on this. So once I pressed her and saying, what are your reasonings? What are you looking at in this plot to draw your message? It realized that what became clearer was that her wishes got kind of mixed in her thinking process. And when you look at two plots that look somewhat similar, you can say they look similar, or you can say they look different, right? It's kind of in between. My job is to be a devil's advocate. I said, no, there's important differences, right? But until that is spelled out, you cannot tell what you're looking at. So I do think narrative is important.
Yeah, I was going to say essentially the same thing. I totally agree with you. I think the process of writing a paper is very important to kind of help evolve ideas and kind of make them more robust. And then the fact that you're going to have a review process where someone's going to potentially tear it apart it also disciplines you. So I think the review process is important in that sense, because we could just put things up on archives and have people comment on it. But I think the fact that there's a review process disciplines you to think logically and structured and defend your arguments and so forth. So I think it's very important. And often, I know from my own experience, when we write papers, as we're writing it, new ideas come and it evolves and it gets better and so forth, right? And then the other thing is, if I look at papers in your field, for example, if it's just graphs and plots, I'm not going to understand it. I need that narrative to help me understand it.
Can you honestly foresee that your grad students won't be mostly using ChatGPT moving forward, though?
I think that's a bad idea. I think that's a bad idea, because I think the ideas come from the attempt to express your ideas, and if you have all these crutches to do that, you're just going to regurgitate ideas that are out there. ChatGPT is kind of like a better search engine, but it shouldn't replace the creative process of formulating ideas.
And also, I could not agree more with you in terms of the importance of writing a paper and also putting it in context. Like, a lot of the value of the paper is, okay, this is what's been, and so it's not, writing what's been done in the field so far and how yours is an advancement or what you've been doing or what you see is different. It's not a laundry list like ChatGPT would do. You go and you think about the prior work and you're not just laundry listing it out. You're talking really about where you stand in terms of innovation, and you're not just filling in known manifold at that point, right? And so I think in terms of context and in terms of ideas and in terms of hypotheses that haven't been tested yet and all of this stuff, ChatGPT would be a very, very poor substitute for that.
Okay, so I just want to go back maybe to Ambu's question about better processes. So one thing we learned in the AI venues and AI conferences is that people realize that nobody talk about limitations of their paper. So it's all good things about them, but then when you actually use them in many circumstances, it didn't work very well. I think that also occurs in different scientific domains. So then I think starting a few years ago, then there's this requirement from, I think, NeurIPS, ACL, and some other venues. They ask authors, you should or you must have a limitation session, right? And then people starting to put limitations. So some of our students, they are very honest. They put their biggest limitation in the limitation section. And you know what happens next is that reviewer pick that up, citing that, immediately reject that paper. So then our students now learns that not to put your real limitations that will kill the paper, but to come up with some, side limitations that wouldn't kill the paper because they need to graduate, right? So it's ongoing battle between like better processes and student wanting to graduate. It's not very easy. It's an evolving process, I feel like.
Yeah, I think I want to, that's something I was just thinking also regard to your previous question, which is, I think the difference between an LLM reader and a human reader is human have doubt and uncertainty when they read things, right? But LLM will literally take things at surface level. So does every single machine learning model to date, which is it never think about, am I wrong? Like, to what extent I could be wrong? Or how can I be wrong? But as a human, we can do that. We can understand our uncertainty, our limitation, or what we haven't really thought too much about. And that type of thing we normally don't ever write about it. And I feel like that's something wrong about the definition of a paper, right? You only write the flashy new things, good things. You never write about what's missing or how you arrived into this flashy new things. Maybe you went through a lot of detour and you actually abandoned some of the potential directions that could be better. And so I think this is like the type of limitation in our language and the limitation of our communication, which will necessarily affect LLM, right? Because LLM only take language as input. And I would encourage ML people to think harder on how can you build in that uncertainty into your model to really tell what you don't know or what part you think makes sense or what part you need to do more reading into other paper. And I actually tried using LLM to read paper once, and I noticed they're not good at reading references of the paper. So obviously that takes too much computation. So they probably don't want the user to have that access to say, oh, go read reference 19 and come back and answer my question again. And that type of functionality would be important because fundamentally speaking, you want LLM to read all the references and the references of the references and before it answer any question. Because otherwise, all the answers are superficial. Why do I need LLM? I just literally Control F whatever things I want to search for.
Yeah, I just hope that Murphy, you not only train the LLMs, but recognize that we have to train the human scientists. So I think that's where, in terms of what is the job of writing a paper, is not just to communicate an idea, but we have to train the scientists so that they will be out there and they will be the next gen scientists out there. So we have to train them. We have to train their thinking process, and that is essential to what our task is.
Oh, well, I guess I have a question for people developing large language models. I have kind of a very superficial understanding of it, but it seems more looking at correlations and probabilities, a probabilistic approach for context, very fancy algorithms. But what are the prospects of building in kind of guardrails of known physics? What kind of algorithmic changes are necessary, and are those feasible, or is it just give it more data so that it actually just learns it? Is there some way to adapt the algorithms to learn about gravity, for example, or maybe
yeah.
looking at you?
Yeah.
Oh, okay. Okay.
Yeah. Thanks all the folks. Actually, this is advertisement. I'm going to actually tell you about the actual limitations and benefits and use cases of LLM in industry. Yeah. So in the afternoon. So yeah, it will be fun.
Okay. Yeah. So to answer Anton's question, I think the training of large language model right now is incredibly simple. That's why it can actually scale. There's really not much going on in publicistic modeling space. It's mostly just predicting the next token, right? So given the context, the previous token, you're predicting the next token. So this is autoregressive. I mean, our student, they came out all this very complicated approaches, trying to improve the decoding process, trying to improve the fine-tuning process, but still, I think what people found the most useful is just very simple autoregress pre-training, right? Predict the next token. And then together with some fine-tuning. And finally, integrating human feedback, right? The other big part is what they call RLHF, or reinforcement learning with human feedback. Not much about reinforcement learning, but really taking human feedback. For example, what OpenAI did was they spent, again, massive resources hiring people, in the Philippines and looking at age between like 18 to 60. They have them look at the output, right? And pick and rank all of the output. And you integrate that in the generation process so that it's not only understanding English text, but also understand, okay, what output is actually preferred by human. So that significantly improves the performance. I think the challenge in the scientific domain is that they didn't have enough annotation, right, from a specific domain experts, right? Getting material scientists really to annotate, okay, is this recipe, does this make sense? Does it not making sense? So I think I also want to advertise, I think, our POSCO and Google colleagues' afternoon's industry talk. They will, they already, I think, went through that process to actually see what actually works when you're creating new battery or when you, trying to come up with new materials. So, yeah. Mm-hmm.
So I'd like to ask a follow-up question there because the topic of annotation comes up a lot. Mm-hmm. And Stephen and I were just talking about the pain of doing it. But I guess I'm wondering from the perspective of the room here, in what area is annotation going to have the highest payoff? Is it in processes? Is it in images? Is it in, characterization? Where are the big payoffs for the effort that goes into it? And if nobody knows, that's part of our problem then.
I mean, my opinion is in processes. I think I talked to you about this because because that's one thing that unifies. So quantum materials is kind of behind on this and thinking of a material as a process. I know this because I think I was talking to you or Sam, and I was like, "Oh yeah, we should think of it as material as a process." And you were like, "Yeah, no shit." There's the structural materials people have thought about this for a long time, right? And so, in quantum materials, I think physicists in general don't want to think of a material like that. We like to think of it as a perfect unit cell. But there's all sorts of examples where the process properties fundamentally change for subtle differences in how you process a material, how you make it, and
And that is largely language that we report that in.
Yeah,
and
right.
So that is
so if you can
temptation
annotate
of the language model to have it processes better annotated so that we can learn from that. Well, that brought up a couple of things, but somebody here. Keep the audience engaged.
Thanks. I always tried. I'm doing a PhD in computer science, but I started as a physics student at UCSB. I was doing research in neuroscience, and when I started my PhD in computer science, I hadn't taken a single computer science class in my life. So I really agree with what you said before about curiosity and pursuing and learning by yourself. And my professors, what they did was kind of help my intellectual curiosity, but they didn't teach me anything. They just taught me how to be curious. But anyways, when I try to think of the only AI that basically really works is their LLMs. They're in general enough to be useful in wide array of applications. And what they did well was that maybe for each task that they wanted to train the LLM on, there wasn't enough data. But if you think about each language task, there's a certain overlap between each task. So if you find a way to train one system on all these tasks to learn the individual information for each task, but also to learn the overlapping information, you know. So when you're learning about one task, you're learning a little bit about another task too. So anyways, my question is, like, what would be the equivalent of building a language for material science that then you could train a large model on a bunch of tasks that maybe you have limited data for each one, but when you put everything together, you have a larger model that actually leverages the overlapping information to learn the underlying physics and all of that. So I think that's the real AlphaFold, thing for material science, in my opinion. Yeah.
Excellent question. Who's going to answer it?
Well, I'm not going to answer it, but I am going to tell you what might be needed. I mean, if you look at the multimodal data sets, I think what CLIP could do, it was a very small model, but was well trained, and it was able to link image and text. It was not a huge, but someone did it. Once it's been done, one can use that in multiple different contexts. So I think one needs something like that, a small, well-studied, crafted model that links text with material properties or the properties of from chemistry and so on. Something and then one can just piggyback on that and to produce a lot more, right? So the CLIP itself is a very small work, and it didn't require millions of dollars, right? Someone did it, but it has had a huge impact. Where can we find something similar to do in the case of materials?
Can you pass it down? Of course.
I wanted to go back to the question that you were posing to everyone just right before the last question. But would you mind repeating, just so I can frame some actually responding to your question, not something totally tangential, about the benefit of annotation on specific...
The question was, as Sam said earlier, we have lots of different kinds of data and materials. Atomistic data. Oh, thank you. We have lots of different kinds of data, ranging from atomistic data to workflows that describe how you actually make something, to images that quantify the structure, and importantly, all the defects, because those are usually the things that affect properties. And so there's lots of batches of information, all of it not unannotated for the most part. And the question I was trying to get at is where is the benefit of annotation going to show up the most, have the greatest impact?
Thank you. So I'll give my opinion on that from a machine learning methods perspective, not necessarily from a domain impact perspective. But I think there is a large opportunity in the field of developing new concept-based architectures that can be more explainable. The problem with generalizing those, if you're just trying to break down ImageNet into concepts, you can say, well, this is a dog and this is a straight line, and there's even with images, there's a complex ontology of features that exists, and with certain material science domains, there is like a very there's a written down that if you're looking at electron microscopy images of certain material, if it looks this way, that is this specific type of structural feature, and that means that a human scientist who is looking at that to annotate it would draw certain conclusions from that. So the lack of annotation of concepts in scientific data is a barrier to developing concept-based domain-specific architectures for those domains. So I don't know if that specifically goes to which part of the workflow, but that is my take.
Well, it is. I mean, I think that's an important comment because if there is one thing that material science is about many different things, and you know, the applications take you to different domains in terms of types of materials and behaviors. But the one thing we almost always have in common is that somewhere in the workflow there's a microscope, and that when we look through that microscope, we have a context for interpreting what we see, and that context is not necessarily encoded anywhere. So that's a good remark. By the way, speaking of cats, I would just like to say that for the first time in my life, I come from a place that everyone knows about now, cats and dogs, Springfield, Ohio. And so, yeah, go figure, anything could happen. So, so we are getting to the end of our time, and I believe lunch is outside. So no? Oh, William's going to make an on-the-fly change in the
Yeah,
schedule.
so the lunch is actually inside. That was my bad. And if I may, I also want to make a comment that I think Kelsey from the Quantum Foundry is going to take a picture for us as a good picture outside. So
Okay. So lunch will be here.
Yes.
Are we going to stay inside, or are we going to go
stay
outside?
inside, but
Okay.
of
They
course
get
we
the
can-
outside. Okay. And so I'd like to finish this session by thanking all of our panelists for their insightful comments and the audience for your participation. So thank you, all of you.
Thank you so much. You did great. And thanks for hosting it. I think you're the perfect host. Okay, so I think we should just go ahead and get it started for the afternoon session. So in the afternoon session, we have two industry keynote. The first industry keynote is by Dr. Wusong Lin. So Wusong is currently a corporate vice president and head of AI research at POSCO Holdings. And for those computer scientists you don't know about POSCO, it's one of the biggest steel making companies in the world. Wu Song has an amazing academic and industry experience. So he, before POSCO, he was leading some of the AI machine learning effort at Apple and then Microsoft and Apple. So Wu Song had a lot of wonderful work in pushing the boundary of AI and machine learning research. And I was very impressed that Wusong decided to actually, really dive very deep and work on with the domain experts in materials and really trying to move it beyond, what we have in the academic domain, but to really make, them useful, right, in really advancing the new materials in the industry setting. So that is amazing, and that's why we have the industry setting keynotes in the afternoon to bridge the gap. So with all that, let's welcome Wu Song for the keynote today.
Yeah, thanks, Professor William, and it's very honored to present here. So thanks for the invitation. Today, I'm going to talk about AI-assisted advancement in industry, actually to develop the second battery materials. I will not present my company's perspective, but I will share my experience and perspective and also experiences. So before diving into details, in addition to the introduction from Professor William, so let me introduce myself, my background a little bit more. So since 2011, I researched machine learning and then received a Google PhD fellow in machine learning for model compression. And then I moved to multi-view learning and multimodal learning since 2016, and then worked on search system at Apple and also advertising system at Microsoft. And then I moved back to Korea to help the country during this fast AI transition by also leading the generative AI research and its applications to help companies' business. So within that perspective, I'm going to talk about what's the problem to help the development of material and also overall business side. And then I'll break down the problems for material property prediction and simulation, and then material candidate generation and material synthesis, and also overall information processing overall. So this is a more detailed table. So I'm going to dive one by one, and also we'll share interesting perspective along with the actual benefits and limitation of LLMs too. So this is just like the well-known like the figure. So current area is here. So now for accelerated material or discovery, scientific discovery, we are currently heavily using the AI more than before. So previously we used computational science, but there is a limitation. And then we leveraged larger data set, but that was not enough. And then we are leveraging all of these things, computational science and larger data set, and also advanced AI models. So this is another perspective. All of this kind of cycle, actually, we can leverage the AI, all the component. So for example, so here, this is a famous paper from Google and UC Berkeley. So was published last year at Nature. So for developing material process, actually, we can consider material candidate, and we can consider material property prediction to reduce the candidate. And then we also leverage the AI for extracting the information and also suggesting recipe, and then actual synthesis, and then there will be data, and then we can cycle here. And then all this part actually AI can be helpful. So, and this is another example from the MPJ Computational Materials Journal 2 years ago. So from the candidate, actually we can simulate the AI simulated thing, and then getting some property, and then actually can get another actually the reduced candidate or simulate on additional properties. And we can circle back here, and then as this figure, we can leverage all this part. So and then with all this kind of perspective, industry and academia, in my opinion, are trying to move to the autonomous lab too. So like the CMU or Berkeley or other university in Europe, and also famous research institute and the company also moved to here in long-term perspective. So this is figure from IBM, actually RoboRxN. So I'm going to share a little bit details, though I will not represent IBM. So let's dive into material property prediction and simulation. So because we have a lot of candidates, but we don't have enough money and time to actually do actual synthesis. So that's why we need to actually leverage the AI. And then one powerful tool is material property simulation through the material properties simulation through the GNN-based model or any other AI model. So I really look for the next presentation from Google DeepMind. So so this is figure from Microsoft. Actually, they leverage a lot of elements to train the model, and then suppose that they have actually candidate, and then reduce the candidate through the machine learning property prediction, for high throughput screening perspective. And then they leverage DFT and then molecular dynamics further, and then with experts and additional AI models, and then they try to find the new electrolyte. I also try to leverage all of this part to find the next generation of solid electrolyte too. So the reason of a powerful like the machine learning interatomic potential to actually simulate the material properties, that they actually quite well approximate the DFT. So recently, actually, error became smaller and smaller. So by actually approximating DFT well, very quickly, so we can actually do more things compared to the previous approach, DFT plus molecular dynamics. So with a larger scale perspective, and also a longer perspective for the simulation side. So then we can find unobserved property from the previous approaches. So this is just diagram from the Google's paper Nature. So we can leverage actually GNN-based property prediction here to predict the crystal structure property. So here are compositional and structures, but for developing second battery material, predicting and simulating crystals property is very important, and not just compositional. So that's why we are going to a little bit deep dive into the structure or simulation side in the next topic. But I'm not going to deep dive in the method very details, but I'm going to cover. So this is this was the table from the several months ago. So I kept monitoring this benchmark. So previously Google actually was nominated in the first first table. So, but this actually model was a proprietary, so was not open. So that's why for such like our company actually, it was impossible to leverage this kind of model. But we could leverage Maze or Netkeep or 7net, such like things which were open. But this actually effort is keep going on. So there are more models in recently. So from the Microsoft there was MetaSim, and then this month actually there was ORB took the top place. So the one thing I would like to mention is that this kind of effort to improve the GNN capability to predict the machine learning potential perspective, like the predicting force field, has been increased again. So, and then, but our experiment, we leverage this kind of actually model with these performances. But it was good. I'm going to share some details later. So we actually recently published the new paper at Advanced Energy Material. I'm going to cover this one. So this was actually to simulate the ionic conductivity of the crystal structure by leveraging GNN-based simulation. So let me briefly explain about the predicting ionic conductivity pattern with the anti-site defect. So there can be crystal structure, and then the lithium ion actually can jump like the double leg perspective or intra-cage within the same cage perspective, or inter-cage perspective with a different crystal. So this kind of lithium jump is highly related with the higher ionic conductivity. So usually the two things are important for like the solid electrolyte development. One part is high ionic conductivity, and then second one is stability. So we wanted to actually develop the new method to simulate the ionic conductivity pattern from the crystal structure by leveraging the GNN-based simulation. So, but here I'd like to share additional the information. We found the anti-site defect with some proportional, like the relationship, actually highly related with the proportional relationships to the diffusivity and the ionic conductivity. So anti-site defect means suppose that this is azurite, like the compositional formula. So Li6P(S5Cl). So S and sulfur and chlorine can change their locations. So usually sulfur can locate it here within the OH cage, but it was revealed that the sulfur can also sometimes hinder the lithium jump. So that's why we try to focus on the some potential by replacing the sulfur with chlorine or other atom more. So, and then that is related with anti-site defect, changing the actually location. And then we define the corridor cage. And this cage actually can be defined with the OH cage. So there can be another OH, and between this we can define the corridor cage. So to find the new rules and new pattern, we try to leverage the machine learning potential. Initially, our collaboration team leveraged BPNN method, but that was not good enough. So, and then our team actually tried to leverage the state-of-the-art GNN-based model, and then it performs much better than this. And then we simulated this, and then this figure I would like to introduce. So, so this box is about the 400K, like the experiments at 400K. And then we found that the anti-site defect actually ratio, which is denoted RS, actually heavily affects the overall diffusivity. Diffusivity actually is highly related with ionic conductivity. So, and then we found that the compared to 0 or 1 anti-site defect ratio, 0.5 was almost optimal point. And then we simulate and found this kind of behavior through the such like machine learning potential-based simulation. This is another figure to explain it. So here, actually, if within the OH cage, if we increase the anti-site defect ratio, it provides the faster escape. But usually, previously, before our paper, actually, most of previous research only focused on this. But we suggested considering corridor cage effects too. So if we increase the anti-site defect ratio, lithium's escape became slow. So that's why one side actually, if we increase anti-site defect, it provides a fast escape. But if we increase further, but it provides the slower escape for the corridor cage. So that's why by considering two different cage effects, we developed this kind of equation. So diffusivity is proportional with anti-site defect times 1 minus anti-site defect. So that's why 0.5 was the optimal point. So this provides some very critical like the insight and information to develop doping material. So usually doping actually material, we use that concept to improve the material property further for desired property we are looking for. So, and then by leveraging this kind of equation, actually, we further actually try to dive the potential probability of increasing the diffusivity further by increasing the corridor cage anti-site effect and also OH cage anti-site defect together with the doping mechanism. So without doping mechanism, we cannot increase further. So that's why 0.25 was actually the upper limit of the previous equation. But with the doping actually mechanism, we can also explore higher than 2.05. So and then we simulated this kind of property with various of candidate of the crystal structure. With the actual this kind of compositional of the azurite variance, and then this is our simulation result, and then it almost same with the actual pattern from the actual synthesis experiment. So these results came from all the well-known journals. We actually mapped their data into this figure. So without using this was very helpful because for training GNN model or any other this kind of simulation, we have not used any data or any pattern from the actual experiment. So that's purely actually from the power of the quantum mechanics with the DFT generated data, but also AI power. So So this kind of machine learning potential-based simulation with molecular dynamics actually provided such like very efficient mechanism to actually simulate the ionic conductivity. So we are actually extending such simulation to the simulation of the stability of the material. So we already get some success here in high diffusivity pattern, depending on the actually compositional or structure pattern. And then we are currently extending the also stability with multiple perspective. Stability, there can be multiple perspective, like the associated with the formation energy or reaction with the oxygen or reaction with the hydrogen, such thing. So there can be multiple actually stable perspective. We are actually extending this work to find the optimal composition but also structure together. So this is related things from another journal about the actually disorder and the lower ionic conductivity and also formation energy. So that means we can, by also such like known fact and our simulation, actually we can find overlap area. So by considering higher ionic conductivity, but also better stability, we can think this kind of overlapped area. But we can reduce further and further by considering more aspects. Now, this can be helpful to develop further the composition of actual solid electrolyte, but also structure perspective too, crystal structure perspective too. One thing I'd like to share about the additional challenge of this kind of thing approach is that we are still remain the problem, definitely along with the performance and the data set. But I'm very happy to see that recent achievement from the Google and Microsoft and the this orbital materials. So the performance kept improved. So and then with smaller amount of data set, also model architecture, model performance improved, but also with a larger size data set, larger model, the performance improved further and further. So, but also main challenge, remained challenging is improving this kind of GNN-based simulation efficiency and scalability further, because our problem spaces is too large. There are a lot of potential combination of different location of atom, even for the same composition. So that's why we cannot actually simulate it even with the machine learning based simulation approach. So that's current actually the problem we are facing. So that's why we are also considering recent approach Bayesian optimization to efficiently explore the problem space. So I introduced two remain critical problem on this. The first one is improving the efficiency of the GNN or machine learning based simulation, and then this actually orbital materials work I think is very good compared to maze, and efficiency improved hugely. So like the almost 3 times throughput and 5 times more scalable. So then we can simulate a larger size of like the crystal, but also simulate with longer, or we can simulate more candidate within the limited time. For example, for ionic conductivity with one Hopper 100 GPU, it took a week for our one candidate simulation. So so that's took too long. So we had to actually we need to actually improve the efficiency too. So even also for stability test, actually we have a lot of different dopant candidate with a lot of various of crystal structures, not the compositional. Definitely compositional space is large, but the structure space is much more large. So that's why we have a huge candidate for simulating stability. So that's why this kind of approach also is required. And also, I would like to share one interesting approach too. So when I attended this year ICML, I actually saw some interesting work. By generative approach, it tried to actually replace the molecular dynamics simulation part, so directly. But I think that's not feasible to apply at this moment, but that's interesting approach. So I don't remember that paper name, but yeah, I think that's an interesting approach in academia perspective and also long term. So and then also I would like to mention that this kind of actually orbital materials approach actually leverage by considering messaging passing network approach along with diffusion based like the model. So they combined it together. So and then they beat the Google and Microsoft in the leaderboard. So I'm going to actually introduce chemical language model too. So this part is more related with the LLM space. So we have another accepted paper, EMNLP. I'm going to share some this kind of perspective. So there can be two different approaches to predict the materials, actually, like the machine learning internal atomic potential based actual simulation or predicting the property directly. But though we get acceptance of this paper, actually we cannot leverage this approach to our actual development of second battery material. There are two reasons. We don't have actually enough data from the actually experiments. So but this approach does not rely on such thing, but it try to learn the experimental result from a lot of paper. But this second different thing is for molecule, not the crystal actually predicting the property of a crystal structure. So there is a gap. So one thing I would like to clarify. But I would like to share some such like just interesting ideas. So a molecular, as you know, it can convert into the string with the SMILES format, and also it can represent a selfie and so on. But we try to leverage the actually graph fingerprint, which is the subgraph structure, can represent the molecule. So we try to actually leverage the relationship between this subgraph structures between the different molecule. Suppose if they have a similar substructure, then we think they may have some similar sub-property, such thing. So we try to infuse graph knowledge into the language model, and then we by leveraging some embedding mechanism of the fingerprint, and we can define the similarity between the molecules, and then we can define the constructive loss, and then we can apply the entire loss function, and then we try to improve the chemical language model, which was based on kind of a BERT-based model. So and then we achieved the state-of-the-art result in both classification and regression side, but also the quantum mechanical property regression task too. So and then this kind of we did the ovulation study too. So and then but this is not a quite population study. There are other figures, but based on the backbone model, more formal Excel from the probably IBM. So we improved the performance further, as I mentioned, by leveraging the graph substructure relationship between the molecules and infusing them into the language model. And we could extending this idea to another model to leverage the different masking mechanism by leveraging the graph substructure. And then there is another work. This is not work from our research, but there is a approach to leverage the large language model, actually decoder-based T5 encoder model, to extract the information and predict the performance, like the property too. And then I think LLM-based model can be extended further to predict the molecule property, but I'm not sure the current approach and performance are enough to predict the crystal structures property. So so that's why I would like to explore further its potential as a next work of our one of a great work collaborated with Professor William group. So, and I would like to share another our work. So far I introduced the material property prediction and simulation perspective in the industrial and also academia perspective together. There some of approach there is a gap. But the GNN-based simulation we are heavily using already. So that already proved some good result. So, but beyond this kind of material property prediction and simulation, for second battery material, crystal structure is very important. And, so that's why. As I mentioned, exploring crystal structures candidate space is too large. So that's why we would like to generate the promising and stable crystal structure candidate. So that's why this problem actually was popular within last 2 years, I think. So this part I mentioned. So we may have more than this kind of number for potential crystal structure candidate, even for developing our actual next generation of solid electrolyte with the specified idea and the formula. So. So that's why we need to reduce the problem space further with the promising crystal structure candidate, but also the efficient exploration mechanism. The previous work actually includes some kind of like the VAE-based or graph-based, like the generative approach to generate the molecular candidate. But also there were graph-based approach and diffusion-based approach for generating the crystal structure candidate. But last year, actually, Meta and New York University actually released their work, and LLM-based approach achieved the state-of-the-art performance in terms of generating the stable crystal structure. So after reading this, actually, I was inspired. So it's very interesting paper. So it was presented AI for materials last year, and then published at the main conference ICLEAR this year. So it generated crystal structure actually vector directly. So this is the rough description of the architecture. So I would like to share great work between our collaboration in high level. So after reading that, I would like to improve this kind of mechanism further. And then we thought, because we were surprised at large language models' capability and power. So we thought maybe we can, if we increase further of power of a large language model with multimodal learning fashion, by learning the more knowledge in the high quality journal, and then maybe we can improve the power of large language model for scientific perspective with very efficiently but effectively together. And then we wanted to leverage its capability for material actually generation task too. So this was the previous actually approach and architecture and description from the Meta and your university paper. So there are three tasks like the unconditional generation and conditional generation and infilling task. So there were multiple tasks. And then previous CDVA approach and diffusion-based approach and performance here. So there are multiple metrics associated with it, measuring this kind of a crystal structure generation. One part is validity, second part is coverage, third part is property. But I would like to emphasize the stability metric more. So and then this was the previous state-of-the-art approach from the CDVAE. So that's stability rate was actually 1.56. So there is a trick to denote this kind of performance, but we need to multiply this factor and this factor together. Actually, this 5.4% came from the just past candidate from here. So that's why this, even though we use this kind of approach, the only 1.5 actually candidate was stable from the DFT-based evaluation. But the previous actually state-of-the-art performance from the Meta and New York University based on Llama 2 model actually achieved 5.3%. Still small, but they improved a lot. So, and then we, as I mentioned, we wanted to improve further by leveraging the high-quality multimodal data set from the high-quality journal, actually Nature Communication Journal. So, and then amazing student Zekun actually construct all the high-quality data and the benchmark data set with this kind of 72 diverse subjective and a lot of article. And this is a description for data set. And if you are interested, you can check our paper. So and then our actually benchmark and the data set actually consists of like the grounded figure captioning and this kind of example, but also question answering task. And then we wanted to improve the model capability by actually pre-training or fine-tuning this kind on our constructive data set. And also we wanted to also improve the large language model with multimodal setting with by leveraging the this kind of Villa model architecture too. So I'm not going to dive in very details due to the limited time. So I have 135 pages to present. So yeah. So here we achieved the state-of-the-art result, which is comparable with GPT-4V on our constructed actually benchmark. Probably we have less than 1% actually parameter compared to the GPT-4V. So and quite effective but efficient model capability. And then by leveraging this, actually we wanted to test the crystal material generation task. So here we actually constructed the interleaved data from the journal data Zekun constructed, and then we pre-trained the model. And then we only use the llama model part from this kind of multimodal training. So and then we also added some multitask fine-tuning on top of it. So and then we achieved the 8% to final stability from the DFT. But also with the M3GNet evaluation, we also achieved much higher than the previous state-of-the-art result. So like the 30% relative improvement in terms of metastability, but also almost more than 45% in terms of stability measure that was rigorously measured by DFT. So for this measure, actually computational scientists and our team member double check all of this and also replicate all of this result too. So yeah, this is a correct evaluation, but the surprise result. So, but one thing I would like to mention that we just leveraged Llama 2 architecture. That can be improved further. I'm going to explain in the later slide. But also multimodal data set also was to improve further on this kind of multiple metrics on the material generation task. Yeah, this is similar perspective. So yes, so from this kind of good result, actually, we wanted to actually extend this work further. So since we just leveraged the Llama 2, actually we can leverage the more latest open source model like the QN2VL, and I think we were busy, so we could not test. But with this kind of improved model, I think we can get higher performance on the stability further. So yeah, this was very good result from Professor Williams' group. Yeah, so I'd like to thank you. So and then next topic is material synthesis. So how many minutes I remain? Okay, roughly 20 minutes. So for developing actually material, next generation material or material tuning of our short-term projects. So material synthesis is very important. So the first two parts, actually, material property prediction and simulation and material candidate generation, actually were helpful to actually providing the insight but reducing the time of actual experiments, because all of our material scientists complain about their lack of time and budget and such things. So that's why these two helpful. But also material synthesis, what I heard is that they are relying their own knowledge, but they don't know exactly why this works, why actually final performance of this actually sample cell actually shows such like performances. So they don't know actually what's the exact structure and what's the inside mechanism. So that's why they also rely on just empirical knowledge or some of knowledge from the PhD or during the live days at the company. But I would like to mention that the AI can also assist their actually material synthesis, as you know. So there are many great actually not many recent work on helping material synthesis with machine learning and the LLM-based approach. So the other part I would like to also mention that in the company perspective, it's very critical to evaluate and also evaluate the risk between the IP, intellectual, IP side. So, so that's why we also would like to analyze what's other companies' current patent or technology with a very efficient manner. But the lawyer or the scientists do not have enough time to checking all the things. So that's why we wanted to make an automated system with. Oh my God. Okay. Yeah, I have. Yeah.
Yeah, it's gonna be a little hard to plug in.
Yeah, maybe here.
Okay.
Yeah. So okay. So here to help the actually material synthesis side, but also to help our legal team or the research team. Actually, we wanted to leverage the language model power and also the existing knowledge document like the paper. So there was work 2 years ago, MPJ computation material, made SCI BERT. It also tried to leverage the knowledge in the science papers, and then they wanted to fine-tune, train the actually BERT-based model to actually use it for various of downstream tasks. And then this kind of example of extracting entity, but also extracting the relationships too. But this was helpful, but just 2 years ago approach. So recently, Nature Communications, definitely there is a actually decoder-based approach to extract the information and relationship all together with the JSON format. So and then it was published. So and then they actually tune the large language model and then generating like the pseudo label and then they actually correct the further with the human expert and then enrich the data and then they with more data set they fine tune the large language model and then actually to actually provide the formatted information. So this kind of things are very, very actually practically helpful for the company. So because suppose that we deploy this model to process all the patent or papers automatically, and then I already built information reporting system for the company. I'm going to share as last topic, but but based on this kind of things, actually we can update our DB, and then for some specific interest, we can also set up some alert system, and also we can actually leverage this power to improve the risk estimator between the similar patent. So yeah. So that's why I also look at this kind of paper together in recent days, though this is not our work. So and then performance is not perfect, but the performance is increased further and further too. So with the decoder-based approach compared to the encoder-decoder-based approach. So and then there is another work, chemical science, with a similar perspective. Try to extract related information, useful information from the all the text papers automatically. So from my experience with this kind of corrected the extracted information, our classification model improved actually precision-wise improved very, very meaningfully. So I cannot tell that our performance for auto classification on the patent is such thing, but there was definitely gain from this kind of well extracted information. So one thing I would like to mention that, as I mentioned, compared to the such like BERT-based variant model, there was a work 2 years ago, 3 years ago, but the recent actually decoder-based model also shows some potentials to get more higher performance on this kind of information extraction task. So you can check this paper, but this is not my paper. But I'm also interested in this thing. So like the agent system. So even for autonomous lab. So and also to actually help actual chemists actually. We would like to assist well. We don't want to solve their problem directly or at once. That's impossible at this moment. But we wanted to break down the problem, and then I already explained break down the problem. So, but if we suppose that if we already built some useful models and systems for each component, and then we can also orchestrating together with the agent system. So this is interesting work published Nature Machine Intelligence this year. So they probably IBM. I don't remember. So but they actually set up the automated system with such like agent perspective. So suppose that there is actually query. So find and synthesize. Blah 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 blah. I don't know this word. Sorry. So, sorry. So and then they actually they provide the planning through the such like agent mechanism. So there is a planner too, and also executor too, and such thing, and plan the actions with multiple steps, and then they conduct steps with automatical fashion, but also but also they can incorporate actually collaborate with the humans too. So from the such like query, and then they break down the actions, and then they can provide the next action to the human with this kind of suggestion. So each system actually assisted synthesize recipe too. So and then, as I mentioned, there is a limited knowledge for each chemist, but this kind of thing actually can help enlarge their knowledge by leveraging the embedded knowledge from the paper and its large language model. So and then we can also orchestrate this kind of flow together. So yeah, so that was third topic. And then in terms of company perspective, so it's very critical to follow the recent innovation and the strategies, and also strategies from the competitors or collaborators or government, such things together in addition to follow latest technology. So this is a little bit different topic, but actually this is very helpful for our entire company's system. So what we heard is that the strategist team and the research team actually they complained daily, because part of daily job is they try to read paper or search the news for specified technique or some domain or companies. So they don't have enough time. So that's why the leveraging large language model power is very good for this kind of problem. So like they automatically, they're sorry for some Koreans. This is actual capture of our system. So they wanted to catch the global news, but also they do not actually want to get all the news, because even the tens of keyword things, there are more than 10K, 10,000 articles from the actually crawler. So that's why we need to build the actually recommendation engine by following their actual interests and needs, and then also the researchers and strategists do not have time to click the translator or translation. So they just wanted to all the things translated in Korean. So, and also they wanted to spend just 10 seconds to check the daily top trending topic and also weekly topic. So, and then, but if they are interested in some specified topic, they wanted to see the related also article together. So after joining actually this postdoc group, actually I built this system within 2 months. It's just very quickly. So, and then we launched it. This is architecture. Sorry for Korean. So, and then yeah, and this is the example naive for one example of model development of actually for making a summary of top actually trend. So naive approach with LLM was not good. Definitely we need to do prompt engineering, but also before my actually joined, team was here, unfortunately, and then a little bit here, and then I applied machine learning method, multiple method and ranking, and enhanced something, and then we get better top trending report, and then we provide this thing in the web page, but also provide the related article. But also we provide the auto email reporting system daily and weekly wise. So more than 10 affiliates receive this kind of auto report. So I forgot to mention, postdoc group consisting of more than 30 affiliates. We have a steel company, we have a second battery material company, we have an IT company, we have a construction company, we have a trading company, so on. Yeah. So So. And also, this is an example of daily report with a different area, like this is second battery, and this is hydro, another area. So and also this is weekly report by providing very well written. Sorry for Korean. I don't want to spend more time. Anyway, the quality is very good. So actually, employees shows more than 90% satisfaction of this system. So and then we also break down the domestic report, America and China too. China is very powerful. Yeah, has very powerful industry for developing a second battery material. United States too. So that's why it's very important to follow global news together. So and then this is not very fun in these days. Just because I actually work on such like recommendation system or advertising system too. That was easy for me, but we wanted to extend it further with actually Q&A system like based on advanced RAG. So in the morning session, the professor mentioned that we can find the relevant information with this search or such thing. So recently, based on advanced RAG, actually we can find very highly related things, and also we can get the analysis or reporting instantly. So with the Q&A system, so we built such thing to analyze the global trend by leveraging this kind of RAG and LLM power, and this is the video of actual working system. So it provides the very comprehensive actually information from multiple different sources from the United States and Korean news, but also there can be example from the China or Europe news together. So okay. Oh yeah. So but yeah, but yeah, I would like to mention that this kind of system may be a little bit different to the today's interest, but very, very important for company perspective too. So, and this system actually helps to provide a very comprehensive but corrected information compared to even the commercial LLM actually services. So, because we store the very high quality and related article, and we stored more than 100K article, but also we built a very high performing advanced RAG. And also we tuned the LLM not to have hallucinations. So we tested very rigorously. We have less than 2% actually hallucination. So with over 91% accuracy on the Q&A, search and Q&A. So and then this is the example. Actually, Copilot provided some hallucination with the different domain, and also Anthropic Claude and GPT-4 all of these provided the hallucinations. So and this is an example to cover different areas. So to actually build this system, actually, it's very critical to construct a high-performing algorithm and system by leveraging the state-of-the-art approach. So simple RAG is not enough. So last year, OpenAI shared this kind of information last year, November. But before seeing this, I already built a high-performing advanced system, perform higher than 91%. Yeah, but the power of techniques were similar. So to construct a high-performing actually RAG system or LLM-based application system, we need to actually almost do the production quality, and to help the even this kind of easy or simple problem compared to the material discovery. So that's why our advanced RAG, modular RAG, we tackle all the things. And all of these components we tackled, like the documented processing with multiple fashion and retrieval, many different technique, embedding an agent or enriching the data, such thing. Yeah. So like this is the one example of actually retrieval technique, but we develop much more high performing and fancy this kind of chunking strategy. Or we also constructed a multi-stage, definitely include the re-ranking, but our own multi-stage architecture. So and we are extending with the LLM-based agent and function calling together. So I also collaborated with UC Berkeley. So and then we submitted to this paper to top tier conference, and also by leveraging this kind of knowledge and techniques, we are extending the company's information system further. And then with this kind of related technique, actually we have a plan to apply analyzing the video data to provide better safety in the manufacturing site, but also analyzing better alert or report system of manufacturing process, such things together with LLM-based agent. So, yeah, all of these are critical topics to actually develop the materials in the industry. So I would like to recap. So material property prediction and simulation definitely very, very important. We are highly leveraging GNN-based simulation along with the computational science and such things. And also there is a potential large language model to predict the property, but still a long way to go predicting the crystal structure property. But I think there is a potential by leveraging this kind of actually experiences. So as I mentioned, the material structure generation is very, very important also too, to reduce the development time, but also increase the efficiency. So, but this kind of approach also can be extended further to predict the crystal structure property together. We discussed some idea. Sorry, I heard my voice. Okay, that's weird. My tone looks lower when I hear my voice. Yeah, and pronunciation is not good. So anyway, so material synthesis wise, also practical wise, we can also there is a huge potential to leverage LLM-based agent system over for autonomous lab, but also actually realistic automating system for classifying all the patents or papers to provide the auto reporting for the company is very, very useful. And then this kind of leveraging LLM power for analyzing over a trend or Q&A, building the agent or Q&A system, already we did. So this is very useful too. So all of these are important for developing and boosting the process of the materials in industry. Thank you.
So thank you much, Woo-sung, for a wonderful presentation. Due to time, maybe we can just have time for like one quick question.
Well, thank you for your presentation, and the knowledge search system it looks very, very helpful, and I can only imagine how much time it saves for the employees. But for instance, I mean, you said it's like very high accuracy, but when I use like ChatGPT, I once tried ask ChatGPT, I mean, who's the like leading group or scholar for blah 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 area, and it spits out false name, does not even exist, first group does not exist. And I mean, I imagine that will happen in the knowledge search system. So the employees, do they track the answers? Like
Yes,
every answer?
and yeah.
They need to do that, right?
We definitely provide, our RAG system actually provide the original source together, right? So
it like scrapes.
It provides the link of the URL or actually page of the PDF or document together. So and then it display together. They can actually double check with the fact very
that's
efficiently.
really cool.
Yeah.
Thank
We
you.
already built such system. And then as I mentioned, normal like this just solely answer from sole LLM model provide a lot of hallucination, but the RAG system help such like reducing hallucination hugely, but also with some additional mechanism to reduce the hallucination. Yeah. So
Sorry, but then what do you mean by fail? I mean, you said like, accuracy is like 90. Then there's like failure. What do you mean by failure?
Because we need to find the relevant information very together. So like the retrieval augmented generation, basically we need to retrieve the relevant source first, and then that's almost 95% success, and then such like 4% decreasement actually came from the LLMs like the hallucination and failure of finding needle in haystack, such thing. Yeah.
So when you cannot find the source, then it's failure.
Yeah, definitely failed. So also we provide the correct source. Even GPT and Gemini failed to find the answer within that document. Yeah.
Thank you so much.
Yeah. But we are currently leveraging Gemini. Yeah.
Yeah. Let's thank Woo-sung again for the very comprehensive, wonderful talk.
Yeah. Thank you.
And then I'll hand it over to Stephen.
you're pronouncing your last name. Is it Chubuk? Chubuk. All right. While he's getting set up, I'll introduce the next speaker, Douglas Chubuk, who is at Google DeepMind, and he's done a lot of seminal work in sort of new materials prediction and a lot of AI tools for new materials development and prediction. So it's a great honor to have him here. And I'll just say personally, it's awesome to work with him because he interacts with experimentalists and he's like willing to listen to feedback. So this is great. And so I'm excited to hear his talk. So I'll let you take it away whenever you're ready.
Thank you. So I don't need this, right? And can I use this?
Yes, I think it's more. It is Eric's, but it should work.
All right, let's see. Okay. How's my voice? Too loud, too quiet? Okay, good. Hello everyone. My name is Doğuş, which is my middle name. I lead a team of chemists and material scientists at Google DeepMind. Here are the people who contributed to GNOME. So I'll mostly talk about our paper GNOME. Here are the amazing people. Almost all of them have PhDs in material science or applied physics, except for Amil, who's currently getting his PhD at Stanford. Yeah, and we have other members who are not on the slides because they weren't in the GNOME paper, but they work on other things. And I'm afraid that I'll disappoint Woo-Sang for the second time now because I won't talk about A-Lab. A-Lab isn't really our work. I wish it was. I am a co-author on the paper because I did some DFT on it, but we don't actually do any experiments. We don't do any characterization. So you'll see that I'll only talk about simulations. But we really appreciate working with experimentalists. So whenever we get a chance, we do that. Okay, so William was talking about the pre-ChatGPT deep learning. I started working on this even pre-ImageNet. So imagine what a hipster I am. And back then there was no deep learning that was quite popular. It was just SVMs and logistic regression. But one thing that was clear even back then to me is I think machine learning and science have very fundamentally different goals at their core. And I think that that contradiction actually leads to a lot of confusion. Because I would take these machine learning theory classes. One of them is pack learning that tries to explain why machine learning works. And when I go to those classes, like one thing I realize is the only thing they care about, at least in pack learning framework, is IID generalization. So your training set and test set comes from the same distribution. And I feel like in science, that's boring, right? What we really care about is when they don't come from the same distribution. So IID means independent, identically distributed. When the training set and test set have the same kind of distribution. OOD is out of domain. It's a little different. And so even though I have a PhD in material science, applied physics, I have spent a lot of time doing deep learning research at Google. And back then, we were interested in looking if models trained on ImageNet can generalize to other images, or like a Waymo car trained on daytime streets can generalize to nighttime. And it's quite interesting. Sometimes there is out-of-domain generalization, but it's not guaranteed. And it's usually not intentional. It just happens and then you measure it. Whereas science is quite different, right? So in sciences, like what makes Galileo and Newton really incredible for us is their predictions that worked completely outside of where they got observations. And I think this is true for both theoretical sciences, where you try to understand the scientific phenomenon, but it's also true for technological applications. Like if you're trying to discover a material, nobody wants to discover a material that has the same properties that a material they already have, right? They want to find something that's better in some dimension or multiple dimensions. Okay, so to get a bit more specific, because I'm a material scientist, I spend a lot of time training and using force fields. And this is quite a common plot I see whenever I go to MRS or APS. I'm sure you've seen it too. The promise is that there is this very fast but inaccurate empirical force fields, and then there's this more accurate but slow DFT, and then you can have your cake and eat it too if you're using a machine learning force field. And I think this is quite misleading because in reality, depending on what you train your force field on and what you use it on, the accuracy can often actually be worse than empirical force fields. So I don't know what you do for fun on weekends, but I sometimes take the BKS potential or the Stillinger-Weber potential and just try it on things that it wasn't trained on. And honestly, it fails much more gracefully than machine learning potentials trained on just silicon or silicon dioxide. And part of the reason I think is, when you think about an empirical force field, I think it's defined by its functional form. So like, let's talk about Stillinger-Weber, if you're familiar. It's a 2-body term and a 3-body term. The 3-body term tries to capture this tetrahedral bonding silicon has, and then it punishes any angle that's different than the angle crystalline silicon should have. So if I were to describe this potential to an alien that just came on Earth, I would just give them the equation and just explain, like, this is why it works well on crystalline silicon, it may not work well on beta thin phase, and how well it works on amorphous phase will depend on how much weight you put in on the 3-body term. Okay, machine learning force fields are very different. So in machine learning force fields, even the simplest, earliest ones like the Baylor-Parry neural network, is just a fully connected neural network. There's basically no physical understanding you can get, especially at the chemical bonding level, from the neural network itself. There is although inductive bias, like Ryan was pointing out. Well, we heard that Ryan was pointing out in the morning, because, for example, the Baylor-Parry neural network was for each atom, and then it would present the total energy as a sum of energies on each atom. So there's an inductive bias, but there's nothing really in the weights of the neural network you can infer the actual properties from. So this is why I feel like we as physicists have to move away from how we do things with pre-deep learning models and start doing things a bit differently. So one thing I think we should do differently is to define models not by their functional form, but by their training data and what they should be used for, their target data. So honestly, for a deep learning model, that should be the only or the most important thing. So, it seems like I've been seeing some nods. So this is going better than it usually does. Machine learning needs to generalize auto domain. But now I'm going to go a step further. By the way, if you have any questions or you want to say something, feel free to interrupt me. If you run out of time, I'll say, okay, no more questions. But I think it's not just machine learning. I think this is also true for simulations in general. So let's talk about DFT. So DFT is supposed to be ab initio, right? But if you've been using DFT, you know that first of all, it has exchange correlation functional, which is purely empirical. But actually, it's not just that. There's actually so many parts of it that's empirical, like what smearing you use, what exchange correlation function you use, what k-point sampling you use. Like, there are all these decisions, like whether you include spin-orbit coupling. And once you made all these decisions, it's basically like a machine learning model. And then the issue is, if you just focus on reproducing experimental data, you can always succeed. But whether that's actually useful is a different question. And this is more so, I think, for GW. So I've been trying to get into GW. And if you look at some papers, it seems like it has an error of 100 MeV or 200 MeV for bandgap prediction, which sounds amazing. But then you look at the paper, for one system, they say, oh, this is like strong correlation, so we're going to start its pre-training the charge density from a hybrid functional. This one, we're going to use spin-orbit coupling. This one. So once you make all these individual decisions for its systems, no wonder you get a good result. But it doesn't mean that if I take that model and try to run a new system, it will give such good results. So this is why I think useful generalization should be the goal. And I think this is why I really appreciate efforts like Materials Project and OQMD, because they're putting themselves out there, and it's a big risk because they say, okay, we're going to do DFT on all these systems with the same settings. And what that means is, for each of those systems, the settings are probably not perfect. Like, I'm sure an expert could take that system and find better settings. But it's actually unclear to me if what the specific expert would do is more predict than what MP and OQMD do. So this is why I really appreciate them. They probably get a lot of flack for it. So I'll show you some of our research. But one thing that I want to say is, you can tell that we've been prioritizing auto-domain generalization over IID explanations. So instead of trying to explain what's been experimentally done, we hope to predict what might happen in the future, which is quite hard. And then one other kind of philosophical choice we made is, we tried to develop universal and general models. So what that could mean is, we would do a universal, or not in quote marks, we do a force field for the whole periodic table instead of just doing it for one specific system. And the reason for that is, I feel like if you try to do something general, you're in a more difficult state where you're trying to make predictive models, as opposed to if you're in a single system, you probably know a lot about this system, and then you can kind of tune the model parameters to get good results. But we definitely need people who work on specific systems, because that's usually how the field improves. But you're going to see that we usually don't focus on any single system. We try to do something more general. Okay. I think this is my last slide of bad philosophy, and then we're going to go to science. So one thing that I think probably everyone agrees with is computational scientists could benefit from going all the way to the actual application. I think Stephen made a point today in the morning that the tools are there and people have to use it. I think that's true, but I think most of those tools are not the tools we need to get to the place we want to get to. So maybe one personal story I can tell you is, so I'm at Google, and there are a lot of people at Google who are not material scientists or physical scientists, but they're amazing engineers, like coding engineers, what we call engineers in Bay Area, and they want to get involved. So they ask me, okay, can I do, for example, high temperature superconductivity? And I say probably not, because the machine learning or the DFT tools aren't there yet. And then they go back and then find these 10, 20 papers that claim to do high temperature superconductivity prediction. So what I've been telling people is, for every single materials property, there is a tool out there, but probably not very predictive. So that's why I think instead of building tools and hoping that other people use it, I think building tools and try to use it ourselves would probably be really good. The other thing that I think we don't talk enough about is the experimental databases have a really high noise floor. So I think it's commonly thought that DFT has lots of error when you're predicting stability, formation enthalpy, band gap, which is true. But actually the DFT error usually matches the experimental noise floor. So at that point, it's hard to predict something like AlphaFold, where clearly for AlphaFold, the experimental data was orders of magnitude more signal than the best machine learning model back in 2019. So then the machine learning could catch up. Maybe quick question. What do people think is the experimental uncertainty in formation enthalpy databases for inorganic solids? So chemical accuracy, people usually say 1 kilocalorie per mole. 10? Oh, that's quite bad. I think I've prepared you for it to be so bad. So I think the number is 2 kilocalorie per mole. And the reason I think that's the case is because OQMD had a really good paper where they looked at, in the SSUB data set, they looked at targets for which there are multiple entries. And then they looked at the disagreement between those measurements, all experimental. And they found about 70 MeV per atom. And then another reason to think it is as you improve your exchange correlation functional, the prediction improves up to 2 kcal per mole, and then it stops. So to me, I'm convinced that the noise floor is at 2 kcal per mole, which is pretty high. That's what the DFT error is. If you think about band gap, what do you think the experimental uncertainty in band gap data sets is? But for general, if you're trying to do the whole periodic table. Sorry, what did you say? 100 MeV? Yeah, so 100 MeV would be great, I think. My guess is 500. And the reason I say that is there's never been a machine learning model trained to get better than 300 MeV. And a lot of the 300 MeV predictive power is probably just overfitting, because these datasets have very similar training and tested samples. Another thing is as you improve DFT, even if you're fine-tuning to get band gap, like a hybrid functional, on a large enough evaluation benchmark, usually plateaus at half an EV. Again, so it happens to be what DFT gets. So I don't know what it is about inorganic crystals that makes it so much harder than organic molecules and biological systems. But if we could find a way of making experimental databases that are kind of lower noise floor, I think that would be really enabling. And to respond to another point said this morning, again, we don't do any automated labs or experiments. And I can see why I'm quite sympathetic to the idea that they may not be great for discovery, because just like simulations and machine learning, experimental characterization works much better if you already know what you're getting. But they might be good for generating databases, because if you could create 1,000 synthesis attempts under the same conditions with the same set of robots, maybe that's something that DFT could learn from. Okay, all done with bad philosophy. Thanks for sticking with me. So, after all that, I want to talk about materials discovery, because that's kind of what we try to do in GNOME. And before I say that, one reason I really want to get into this was because as I read more about the history, it was quite clear that a lot of materials discovery happens by random trial and error, and it's almost all done by experimentalists. So here is like one great example. Right? There's so much to talk about in this plot, but one of the things is the earlier mentioned LBCO discovery around 1987. I think when Mueller decided to look at COOP rates, I think almost everyone else thought it was crazy, right, for looking at COOP rates for superconductivity. And if you look at his Nobel Prize speech, he was thinking like a conventional superconductor when he was designing COOP rate, which makes sense because until then there was no unconventional superconductivity. So that was kind of like an experimentalist succeeding, not a theorist or simulation person, but also there's a sense in which it was like random chance. But then once that was discovered, you know, people knew how to substitute elements, which I'll also show, we also do that, and then they were able to improve it. And I think there are many examples of this, as we know historically. One of my favorite examples is the diary from Bardeen and his colleague when they were inventing the transistor. And this is what they call the magic month. So this is the mid-November to mid-December in 1947. And they announced this discovery, I think, on 17th of December. And one thing you notice is in the last month, so this is the last month before they discovered this, invent this incredible thing, they're just trying all kinds of materials, just pressing all the buttons. So, you know, they originally thought silicon would be right, but then it didn't work, so they went to germanium. They had to change the metal probe. They had to even change the glue. So here is maybe one of the best solid-state physicists that ever lived. And clearly, like, he knew what he was doing, right? Like, it was a semiconductor here, it's metallic. But even then, like, we're just pretty bad at predicting what will work. It's kind of like a lot of trial. And then the question is, can simulations and machine learning help with this? Maybe. So the task we want to take on, of course, is actually predicting novel materials, but it's quite hard. So we went to a much simpler task, which is finding compounds, materials that are stable at 0 Kelvin according to DFT. So you might think this is easy, but I don't think it is. So let me show you some reasons why it's not. So OQMD had another great paper back in 2015 where they tried to take known stable materials and then substitute elements that are reasonable. Like you take silicon dioxide, substitute germanium for silicon. And then they found that only 1 to 3% of the time the new material would come out as stable at 0 Kelvin. And then more recently, the Marquez group had a really nice paper where they used ICS2 to learn this really complicated bidirectional graph for representing substitutions. If you can't read this, basically what's happening is elements are grouped into subsets, and then there are arrows that tell you if a certain subset can substitute into another subset. And it's not adirectional, so some directions are possible when the opposite is not. So some of this is like pretty obvious, like lithium and sodium can substitute into each other. Some of them are less obvious, unless I guess you've been working with them a lot. I think that's a great question. I think it probably is the frequency of it happening, because like I guess not every substitution is as likely according to ICSD, but it's worth checking. It's been a while. I might be misremembering. And even then, so if you do the all hard work, really good work, you find that only 9% of the time the substitution you make leads to a novel stable crystal, according to DFT. Another thing we noticed is there's a trade-off actually between discovery rate and efficiency, and that makes sense, right? Because if you want to discover a lot of them, you might lower your standards, and now you'll get a lot of incorrect predictions, but some of them will be correct. Whereas if you really wanna improve your efficiency, you'll really tighten your thresholds, and then maybe you'll get 100 of them, but they'll all be stable. So there is this unfortunate trade-off. And then more recently, Chris Bartel from Sader Group published this really nice paper where they took all these graph neural networks that supposedly give really good formation energy predictions, but they weren't actually useful for finding stable materials according to DFT at 0 Kelvin. Okay, so the way we approach this is we kind of took these models, we trained them on all the available data, and then we tried to get new stable materials, and we failed. And then we were trying to understand why. And it became quite clear that this was the problem I was talking about at the beginning, where these models are really good IID, but they're not good OOD. But the word discover, by default implies that you need to do something OOD. So here is a fun set of experiments you can do today on your laptop. You can take materials project as of 2018, which is a data set in a JSON file somewhere, and then you can train on it, and then you can test it on materials project in 2019. And you'll notice that your error drops error goes up quite a bit, even though those are actually pretty similar data sets. Something else you can do is train on 2018 and then test on AIRS crystals. AIRS, you might know, is a ab initio random structure search method where you randomly put atoms in a unit cell and then relax it. So it's quite a different distribution. Or you can do substitutions even, which is what I was mentioning, where you take a crystal, substitute like elements for like elements, and then your error goes from 20 MeV, 28 MeV per atom to 100. So you basically go from chemical accuracy to having no predictive power. Because turns out most crystals, if you look at their distance to convex hull, which I'm glad Eric described this morning, have about 100 MeV per atom random guessing error. So you're basically as bad as random guessing, which is no wonder these models weren't useful for stability prediction. And the good news, though, is even though this point is bad, so this is the auto domain generalization at the size of the data set in 2018, you notice that as you improve the data set size, the result improves as a power law. And if you're from the deep learning side of the school, you're probably very familiar with this, that a lot of machine learning models going from LLMs to speech to vision have shown this property that as you increase the resource you train it with, it gets better as a power law. We don't know why, but it should really excite physicists because power law usually implies some kind of universality. And this is true for like really niche things, like even resolution of ImageNet, if you increase it, the error will go down as a power law. But in this case, we're trying it on crystals, and we're trying it on auto domain error, like on one of these auto domain tasks, and we again see the power law. So long story short, we drew this line 3 years ago, and then we kept, cranking DFT on Google servers when they were empty, so not Black Friday, and we got a result that's even better than what we expected, because I think what happened is, as we were doing this, we were also trying to promote diversity in the crystals. So not just increasing data set size, but also getting like a more diverse set of crystals. But it's just a hypothesis. So now the good thing about this is this number is around 20 MeV, and that's below chemical accuracy, but it's also below the precision you need to discover stable materials at 0 Kelvin. So going back to this number, I think we get about 82%. So it's about an order of magnitude improvement over this. And we got about 380,000, which is like a tenfold improvement over all the 0 Kelvin stable compounds that were discovered by DFT in the last decade. To me, what this really shows is it's really important not to stop here, because on the IID task, you would have gotten 20, and that would be a great NeurIPS paper or Nature Communications paper. Because if you stop there, you don't realize that it's actually not useful for discovery. It's just useful for an IID task. It's an academic paper. Okay, so one last thing. I said no philosophy, but a little bit more bad philosophy. I'd really like to kind of comment on this precision versus recall issue. I think that comes up a lot when people talk about stability. So the reason I care a lot about 0 Kelvin stability is it's the best predictor we can compute high throughput. Of course, it would be better if we could predict finite temperature, and maybe one day we can. But today, it's hard to do that for the whole periodic table. But I think another reason it's a bit unfair the way people talk about DFT is they usually measure its recall ability. So what is the difference between precision and recall? Precision is if a model says something is positive, what's the probability it's actually positive? Recall is if the label is positive, what's the probability that the machine learning algorithm gave it a positive prediction? And the reason that's very important here is the valuable resource is the experiment. So what we should try to make sure is we don't waste experimentalist time. So the way to do that is to maximize precision and not recall, because recall just improves your explanatory power. So it's great for backwards explanations, but precision is what you need for forward-looking predictions. So I think what people usually do is they look at OQMD's, another great paper, where they took ICST compounds and then they measured their stability according to DFT. And if you do this, you realize that while most of them have 0 MeV per atom distance from the convex hull, a lot of them actually have larger numbers, even larger than 100. So if your priority was to maximize your explanatory power, you would put the threshold at 100, or maybe even larger. But that would make your precision basically 0. So that would make it not very useful, but maybe a good explanation tool. Okay, so I think I've been talking for 23 minutes? Okay, nice. Okay, everyone with me? Let's now change gears a bit. So out of all these crystals that came up that are stable at 0 Kelvin, we wanted to look at what kind of properties they might have because we want to work with experimentalists and actually make them. So we did a couple of things. So one of the things we did is we checked for solid lithium-ion conductors. And the reason for that is in 2017, there was a really nice paper by Austin Sandek where they went to Materials Project and filtered all the crystals there in terms of their lithium-ion conductivity, electronic conductivity, right? You want it to be an insulator as an electrolyte. Its chemical stability, so a few other filters like this. And then they saw that the number came from 21,000 stable materials to 21. And actually, more recently at Stanford, they were able to make one of these. So this is similar to the Microsoft paper Wu-Sang mentioned. That was in 2017. So out of 21,000, you end up with 21 DFT promising options, and out of those, experimenters can make one. So we applied the exact same filters as this, and we found 528 of them. Right, so not to say that these are actually going to be good electrolyte materials in experiment, but it's just on an apples-to-apples comparison where we have a lot more candidates. Another thing we did is, again, in 2017, there was another very good paper by Gowon, where she went through Materials Project and found all the potentially layered materials like graphene, MOS2. And at the time, she found 1,000 of them, and our data seems to have 52,000 if you'd like to screen them. Or if you'd like us to screen them. And also, we took this specific class of materials with lithium, manganese, a transition metal, and oxygen. And the main reason was, as I mentioned, Chris Bartel had this really nice paper where they found that machine learning wasn't able to discover any new ones. And there were about, I think, 9 of them before they tried with machine learning. And our database had 20 of them. And one other thing that got us really excited is, when we started this project, we did not look at ICSD at all. We just looked at Materials Project, OQMD, WBM, and basically all the computational databases. But then once we were done with it, we wanted to see what kind of overlap we have with ICSD. So another question, does anyone know what percentage of crystals on ICSD are ordered and what percentage are disordered? Mostly disordered is one prediction. Nice. Okay, so the answer, as far as I know, last I checked, which was a month ago, is 60% ordered, 40% disordered. I think probably more recent editions are more likely to be disordered, but I looked at the whole thing. So out of those 60%, they're ordered, so we can directly compare it with our DFT prediction, because our DFT predictions are by definition ordered because they're 0 Kelvin. And we found about 736 structural matches. So these match our structural prediction exactly, or as much as PyMatGen structure matcher allows. And there's some interesting ones here. So this one clearly, this prototype was known before, but I think this particular composition was discovered more recently, and it had come up in our DFT calculations. This one has thulium, which has F electrons, and of course DFT being better at elements we know better, is unlikely to be as good at F electrons, but we were happy to see that the structure was and the composition was correct. So there are 736 of them. And more recently, I've been looking at them every month. The rate seems to stay about the same. So since we published the paper, it's about, I think, 5 per month, which matches the frequency that would lead to this number, which I guess is good news in the sense that it's continuing, but it's bad news in the sense that experimentalists are not in any way influenced by the DFT predictions, because if they were, the number should go up. So if I can change that by working with you, please let me know. And then one other thing we're very excited is, so there was this set of papers, I think these are independent, one from Marquez group again, and one from Picard group, where they got really excited about this crystal with magnesium iridium hydride that one group thinks might have a superconducting temperature of 160 and one group thinks 80. So they both think it's high, although it has not been experimentally verified. But we looked at our database, and this crystal was in our database with this crystal structure. So that makes me think there are probably other ones, if you want to check, you care about superconductivity, that are potentially superconducting. And actually, we have been getting some really good news from just different groups screening our database and finding things like this. So hopefully they'll be public soon and you can see them. Okay, so far everything I said was theoretical and computational. But we also just had a paper published actually yesterday or 2 days ago in JAX, where we, for the first time, kind of got serious about characterization and kind of like helped with the refinement. We did the disorder calculations. And this is, I guess it's fair to say, the first ever crystal that's ever been made from our database, which is probably very familiar to some of you because you do it every day. But for us, it was very emotional. It's the first time. So it was quite nice to see this. So maybe let me try to quickly explain this. So all the heavy hard work was done by our collaborator Akira Miura, who is at Hokkaido University in Japan, and his collaborators in Japan. And the idea was we want to use our DFT predictions to do exploratory synthesis, because we know from this nice paper by Tony et al. That usually the functional discovery for material comes quite a bit after exploratory synthesis when the crystal is made. So if we can make these structures, put them on ICST, maybe somebody will find a good function for them. So we have like this kind of pretty reasonable pipeline where we go from DFT, we prioritize according to 0 Kelvin stability, and then we do in situ XRD screening, refinement, and then if there is disorder, we try to understand it, and then we deposit to ICST. And what happened is we ended up finding 25 in the cesium quaternary chloride space. And some of them Akira didn't want to make because the precursors weren't available, and maybe for some other reasons too. So we ended up trying about 11 of them. So we started with 280 just based on compositional charge balancing. And then 25 of them were stable according to DFT. Akira tried about 11 of them. 4 of them seems quite successful. 2 of them seems like they have impurities. So this lithium iridium one, I think, hasn't been brought up in literature before. These 2 come up in literature, but it seems like we found a different polymorph. And this one comes up in literature, but it wasn't in ICST, so we thought it would still be useful to add to ICST. And there's an interesting thing here where if you look at you probably couldn't read them, but if you look at these DFT-based candidates, they were all either cesium-2 or cesium-3. And it just turned out that all the ones that we could make are cesium-2, and we couldn't make any of the cesium-3 options. And turns out ICST also doesn't have any. So we also tried high pressure. So it's possible that this is just a bad prediction from DFT, or maybe we need to try a different synthesis method. So if anyone's up for a challenge, I think this could be quite interesting. And then when we look at the failures, I think it's a little interesting. So for the rhodium one, I think it just didn't work out at all. For the iron and vanadium one, you can see the prediction is in there a bit, but there's other impurities. And then for chromium is one of the successes, so it's much better. So this is the synchrotron where the measurements were made. And then we tried to do this thing. This is more expensive, but maybe I can talk through how it works so that you can see why it's much more expensive. So for the chromium structure, we found a polymorph that's different than what was found experimentally. So we want to understand. So experimental previous report had found basically a fully ordered phase, whereas we were seeing this disorder, so we want to understand. So what we did is we took this system and then did about 1,000 DFT calculations to fit a cluster expansion model, to do a Monte Carlo simulation to figure out whether disorder is likely thermodynamically. So this is one reason, right, where 0 Kelvin stability is a lot easier, because 0 Kelvin stability requires only 1 relaxation per material. Finite temperature, just for the configurational entropy, requires hundreds, maybe 1,000. We did 1,000. And then this is not even talking about vibrational entropy yet. But what we did see for this, which is quite exciting to me, is that it turns out it's quite a complicated structure where on these sites, lithium and chromium share 1/4, 3/4 occupation. And I'm not showing chlorine here, and then these are the cesium atoms. So there's this like 3/4 ordering, and then we looked at the neutron diffraction pattern, and that seems to agree quite well. So it was quite exciting to us to be able to predict it with such precision. And then on the ruthenium option, it's interesting that the previous group had found full disorder, whereas we found partial order. So you can kind of see from our Monte Carlo simulation, the result, of course, is very dependent on temperature. So it really depends on thermal history. So it's hard to say if something will be disordered without knowing about its thermal history, which goes back to the great point from the morning that it's not a material, it's a process. Okay, so we're going to shift gears again. But any questions before I do? Yeah. Yeah. Yeah.
I want to ask what kind of advanced machine learning techniques you use and if physics-informed technique is one of them.
Yeah, great question. So for the 9% number, Marquez group had used to find like machine learning to find a really good substitution model, but they didn't use a graph neural network or a force field to predict the energy of the resulting structure. Whereas what we do here is we use a graph neural network trained on a lot of data to predict the energy of the final candidate. And if the graph neural network says this has a low energy, then we send it to DFT. So I think the main differentiator is the fact that we use this energy predictor.
I mean, there could be like a million reasons why success rate is so low, but it could be the case. I mean, it's a data-driven method. So network does not, it only sees data. It does not reflect already well-known physical knowledges. But there's this like physics-informed neural network, PIN, and it's like crossing out all these solution space of the network that is not physically coping well. So that may reduce, like cross out a large portion of solution space so that it could actually be more accurate.
It's possible. You know, I should say I don't exactly understand what the difference is between a PINN and any GNN, because any GNN has physical constraints. Like for example, it thinks that atoms interact with their near neighbors. It has permutational symmetry, rotational symmetry. So I think Baylor Pi neural network was also a PINN in the sense that there was a lot of physics built into it. But I personally try not to think about those labels and just look at the performance. So what is the performance of a GNN in terms of its error metrics, in terms of its discovery acceleration? And then, you know, we these days use equivariant neural networks, which have even more physics in it because it tries to make all the layers equivariant. Yeah, so there's definitely quite a bit of that. Yeah, of course. Yeah.
Just relevant to that, the pure like energy, I guess the question is if you add some like force field or some force, actually the PI will improve the prediction.
Yeah, great question. So I will talk about force fields in the next slide, which is like great timing. One quick comment is a force field is usually a lot more expensive than a static energy predictor. So our static energy predictor is a simple GNN. So we can do millions of predictions in 1 second. Whereas a force field, I think the fastest out there, like orb or mace, I think it's like 100 milliseconds a step. So it really changes how many we can evaluate. But you're right, I think a force field would probably do better, which we can see actually with the MathBench discovery results I'll show later. Yeah. Nice, very good questions. So far, what did we talk about? We talked about discovering 0 Kelvin stable compounds, and we talked about some experimental potential applications. Now I want to talk about force fields, because the good news is we did all this DFT, we have all this data. Can we train a force field on it, and whether is it useful? Okay, so let's talk about like few simple specific systems. So here is one system with this potassium lithium where we do DFT, MD, so we do molecular dynamics at 1000 Kelvin, and then we get this trajectory. And as you can predict, at every time step of the trajectory, there are forces on these atoms, and the task here is to predict the forces. So this is what a force field does. So that's the y-axis in milli electron volts per angstrom. And in the x-axis is the size of our training set. So the point I'm trying to make here is this is quite a different task than what the model and the data was generated for. But even here we see something like a power law, where the more training samples we use from our DFT database, the better we do on this one specific system in terms of predicting its forces. And it's quite funny because this red point is from a completely different data set. This is from Magnet, from Materials Project. But that actually fits in this power law with our data. So this kind of suggests, maybe data is the most dominant factor and not the other aspects. And we can keep doing this, but one other thing we can do is instead of just taking our pre-trained model and evaluating its forces, we can fine-tune it on the system. So here's another specific system, and then we take the pre-trained model and then we fine-tune it on like 10 samples, 100 samples, so very small. And again, we see something like a power law, but I guess the more important outcome is fine-tuning works pretty well if you start from a pre-trained model instead of a randomly initialized model. So, let's say you take one of these universal models like MACE, and it's pretty good on some systems, but not good on your specific system. This is promising because you can just fine-tune it. Here is kind of try to benchmark our model relative to other models. So 7net is a recent model from Korea that looks really good. MACE is MACE MP0, and then there's ChargeNet and M3GNet. And on these different elements, we seem to do well. One thing that's quite interesting to me is nickel is a composition that doesn't exist in our training set because we split data based on composition hash, and nickel just happens to be in our test hash. So even though we've never seen pure nickel, we seem to do really well on it. And so this was our model we trained 2 years ago that we shared in the known paper, and the results have, of course, improved since then. This is another one where it kind of shows how much the field has progressed. So if you take a Baylor-Parnello network, which was the OG, the incredible revolution that we all started with, and train it on 263 structures, you get an error of about 70 MeV per angstrom. And then if you take this universal model, and by universal I mean it can apply to a whole periodic table, even with 0 training frames on nickel, you match the same result. So this is quite, I think, similar to how the LLMs these days, just by pre-training on the internet, can sometimes outperform bespoke, simple systems. Okay, so far we did like a lot of static force predictions. Now we'll do something a lot more complicated. We'll try to predict lithium-ion conductivity through a crystal. And to do that, we will do 50 picosecond simulation of molecular dynamics for crystals that are not in our training set. And let me just get to the result. What we see is, even for this task, which is now completely different from the training objective, where we do a 50,000 step rollout for MD, the error for predicting what DFT will get for lithium-ion conductivity also seems to go down with larger training set. So this one is a NICWIP trained on M3GNet data, and then these points are also a NICWIP but trained on our data as a function of training set size. So this is quite exciting to me because this means that we see these power laws even in places where the test objective and the training objective don't match at all. Okay, and then maybe final results slide, and then maybe it's a good time for questions. So when we trained this model, that was 2 years ago, and then this benchmark came up from Janusz, and it looked pretty interesting. So even though we didn't train our model for it, we tried it and it did quite well. And then since this result, I think there's been a lot of models that are potentially tailored for this task. So we're starting to see the Goodhart law in effect. Are people familiar with the Goodhart law? It's this thing that deep learning people are very familiar with, where whenever you make it a metric, the metric loses effectiveness because people can just work for that metric. So one thing you can do, for example, is remove the force being the derivative of energy, and you just have direct force outputs. So that would improve this result, but it would prevent you from being able to simulate physics. Another thing you can do is you can take your model and fine-tune it on Alexandria or WBM, which is literally the data set that this benchmark was created from. Again, you'll reduce the out-of-domainness and you'll get a better result. So unfortunately, I feel like this benchmark is saturated now, but hopefully there'll be other benchmarks soon. And I was going to talk about this other paper, but I feel like I was too slow, so let me skip. So here's my conclusion. We have these 0 Kelvin stable compounds on GitHub, and we have collabs that you can use to measure their convex hole distance, if you like. And then what I did not talk about today is this amorphous to crystal prediction paper, if you're interested. And we've been publishing generative model papers, Unimat and GenMS, but I think they're at that stage of being like a toy model where it's good as an academic paper, but it's not something I would replace substitutions or errors with yet. but hopefully we'll get there. This one particularly starts from language to output a crystal, if you're interested in trying like a language input. And then from this morning, since JAX was mentioned, we have a molecular dynamics package written in JAX. So if you want to do molecular dynamics and differentiate it with respect to any of the parameters, including temperature or particle distance, all kinds of things, you can try it out. It's on GitHub. Yeah, thanks for listening, and I'm happy to take any more questions.
Mm-hmm. Like take one thing and do all of the symmetry, right? And I think you also mentioned that stuff like MACE and that kind of equivariance is just kind of slow, right, compared to something like that. And so is it just like, where's the comparison here? Like, are you just kind of saying that, yeah, this stuff is nice, the equivariance or something like hard constraints on the model itself, like ingrained, but is it still just like brute force data scale and just straight up like brute force data augmentation? Is that just still just way faster? Like that's still just way better than even if my model is, intelligently designed to incorporate symmetry rigorously or something? It's still
Yeah.
Like data and brute force is faster quite a lot.
Great question. Like I would say, I think the most important thing is evaluation, and that really depends on what you want to do, right? Like I think a force field might be the best fit for you, but not for the next person, because it really depends. So I think the most important thing is evaluating the thing correctly. So like let's try to learn from the vision field, right? So for a long time, people thought CNNs were obviously the right architecture for images, because they were. Like even on ImageNet, the inductive bias that convolutions gave you really good results. But then turns out if you have something that's much bigger than ImageNet, so ImageNet is 1.28 million, if you have like 1 billion images, suddenly you don't need convolutions. Now you just maybe use a transformer. So I honestly personally don't know if equivariance is here to stay. Maybe as we add more data, equivariance will go away. But I also like don't have a dog in that fight. Like I kind of, I just use it as a tool, so I kind of don't mind. But this is why I would encourage, especially physicists in the audience, to not have like strong opinions as they go into deep learning, because usually what really matters is like a pragmatic approach where you just say, what is working best for me? Because your goal, right? Okay, here's the other thing. Our goal at the end of the day is not a deep learning goal. Our goal is a physics goal, right? Like we just want to improve science, and deep learning is only as useful as it helps us improve science. So it's very philosophical again, sorry.
Any other questions? So I may miss it, but maybe you have covered that. So I just want to ask about the details of the machine learning driven substitution.
Yeah, so that's a great question. So there's this slide, which is not our work, right? This is from the Marquez group. But you can read their paper, it's quite nice. They basically used ICSD to find materials that are substitutions away from each other, and then use that to derive probabilities. But this has been done before, right? So materials project, the Codier et al. Had these papers where they would look at ICSD and then look at materials that are identical to each other except for one substitution. So if you go to PyMatGen now, you can get ICSD derived probabilities. So we actually just use that. We just use the PyMatGen model. Excuse me. But turns out you can do better. We did try taking this better substitution model and then on top of that do our GNN stuff. but that didn't improve very much. So we probably already saturated that. Nice, thanks.
So to what extent, I mean, you were talking about local structure and local disorder. To what extent is it a rate limiter in like developing the understanding of that? Actually, the fact that the experimental assessment of that is extremely difficult, right? I mean, that's always, people argue about local structure in many materials for years and years.
Mm-hmm.
So to what extent does that impact sort of like, you think, the sort of the feedback in terms of validating sort of local structure prediction?
Yeah, great question. So you tell me, but my opinion is, like, I guess it only matters as far as it impacts the application. So there are these papers that show that the disorder will impact, for example, lithium-ion conductivity. So in that case, I guess it is important to get it right if you want to simulate the lithium-ion conductivity. But if it doesn't matter for the application you want, then I guess it just becomes an academic exercise where like you publish a paper and then people say, okay, this is correct. But what do you think?
Yeah, I mean, I guess if your only interest is the, whatever the function of the material is, then okay, yeah, maybe it's academic in terms of whether or not it's present or not. But I guess in some cases, I mean, like, I guess one thing's about like colossal magnetoresistance, it's kind of essential to the physics. Like, for a lot of strongly correlated electron systems, people really need to know if that's what's driving the properties or not.
Mm-hmm.
Yeah, okay, so I guess it depends. If you want to design new materials based on some insight versus just predict and test.
Yeah, and maybe I can show one example from there. So, there was this nice paper from, again, OQMD group. I just feel like I'm just becoming an advertisement for OQMD. They had, for example, studied lithium cobalt oxide, and they found that, they would never mix. Like, I think you had to go to 5,000 Kelvin to have them mix. Whereas here we're seeing like mixing at a much lower temperature. And then if you look at ICSD just from a statistical perspective, I think there are some pairs of elements that almost always mix, right? Lanthanum and strontium. And then some elements that never mix. I guess the interesting stuff is kind of in between where it's like it could mix or not. And maybe that actually tells us something about the local bonding and chemistry. I'm personally quite interested in it because it's like a really nice interface between the hardcore force field work and the hardcore kind of thermodynamic work. So there's probably a lot of innovation to be had there because these cluster expansion calculators are very expensive. So, yeah. One more question. Nice.
So, as you pointed out, like right at the very end, like throwing more data at a lot of these, no, those are in the Q&A. Throwing more data at a lot of these problems does sort of a phenomenally good job of solving them.
Yeah.
In that space, a lot of the things that you've talked about here, we can sort of expect that in the 2 to 5 year scale are kind of going to be solved problems in a sense, right? The details will be what they are, but like, in a sense, a lot of what we're both talking about, like, seems tractable. So and you seem willing to philosophize. So in that world, what are you not convinced will be solved in 5 years that you think, oh, if only?
Great question. So, okay, so let's take a step back because as you said, a lot of the improvements here and a lot of the improvements we can predict have already happened in other fields of deep learning. So what has not happened in deep learning? I feel like the thing that hasn't happened in deep learning is kind of like what you might call creativity or kind of trying to find things even though you're not looking for them. So often scientific discovery is a funny thing, right? Because if you knew what you were looking for, it's not really a scientific discovery always. So I think in the RL field, this is sometimes called the open-endedness. Like they want to have these learning systems that don't learn based on a single loss function because that always ends in 2 days, depending on how many GPUs you have. But they want to do something that just learns over a lifetime like humans. And I just don't see any method in deep learning that could even attempt to do that, let alone in physics. So it's unfortunate because I think maybe these methods will get us boring discoveries, like maybe we'll get an NMC cathode that's a little more efficient because we tuned it or something. But I don't see how these methods will get us like the new kind of superconductor that nobody thought about. But it would be nice if somebody could get us there. Yeah.
All right.
Awesome. Yeah, thanks. All the questions.
Okay. Our next speakers are very important. Cool.
Yes, and then Sam, Meng Yang, and Anton. So 20 minutes each. We have a board session. I'll
Okay. All right. So for the next series of talks, we have a series of 20-minute talks with the idea of pooling all of the questions at the end. And so we're going to start with Bolin Liao, who's in the mechanical engineering department here at UCSB. And he's going to talk to us about high throughput search and machine learning for the discovery of new energy materials. Go for it. Yeah.
I'll just take this.
Yeah.
All right. Good afternoon, everyone. I'm Bolin. I'm an associate professor in mechanical engineering. I'm a mechanical engineer pretending to be a material scientist with some basic knowledge about machine learning and AI, and super interested in using these methods in my own research. As Stephen said, today I'm going to talk about some recent work, some of them a little bit naive, I would say, using these methods to discover new energy materials. So just a brief introduction of what I do usually in my lab. So I work on phonon physics. Right, phonons are quantized lattice waves in materials, and they carry heat. Right, so if you're interested in heat conduction, right, in materials, so they are super important. But we're also interested in how phonons interact, right, with other energy carriers like electrons, photons, magnons, right, in magnetic materials, and ions, right, for in solid-state electrolytes. Basically, looking at all the energy conversion processes, right, from a very microscopic level. So some applications, thermoelectrics, right? So where you want high electrical conductivity, low thermal conductivity to convert temperature difference, right? To harvest waste heat, for example, into useful electricity. Solar cells, right? Where you excite charge with light, then you try to collect them as efficiently as possible. And recently, we're also looking at, for example, thermal management for high power devices, right, power electronic devices based on wide bandgap semiconductors, for example, and also cooling, right? So magnetocaloric cooling, right, using magnets, right, to build a thermodynamic cycle to achieve solid-state cooling. So in all of these applications, right, this microscopic interaction, right, between phonons and the electrons, magnons, right, phonons themselves, are super important, right? So we're trying to develop theory and the experiment to really understand these microscopic processes. So what we usually do in the lab, right? So my core expertise is this heat conduction theory and phonon physics, right? We develop theory and computation to understand electron-phonon interaction. For example, recently also spin phonon interactions, right? So these are very detailed, I would say, maybe accurate, somewhat accurate theory and models. We also do experiment where we develop instrumentation like ultrafast electron microscope, some optical spectroscopy methods to probe and understand these processes. Right. So I would say these are all like kind of old-fashioned material science or mechanical engineering research. Right. So we get very detailed understanding of a specific material, but of course the disadvantage is that they are generally very slow, right? So in terms of discovering new materials, for example, for some of the applications I just mentioned. So recently we've been interested in high throughput search and also a little bit of machine learning, right? Trying to really accelerate, right, the process of discovering new materials for these applications. Right? For high throughput search, really the general idea is that we start with a very large amount of candidate materials, but we go through multiple layers of screening, right, based on computational cost, right? We just compute some very simple properties that are very computationally cheap, so we can really narrow down the list of candidate materials. Eventually, right, so maybe we have a few that materials that are very promising, right? Then we can go through some expensive step, more accurate, high order DFT simulation, or even experiments, right? So I think this is a good opportunity, as some of the speakers already mentioned, right? There are large material databases available, for example, the Materials Project and OQMD, and there are very efficient computational methods based on DFT. But there are also challenges, I would say, right? For example, some of the properties we're interested in they're actually very expensive to calculate, right? So you really need to find very efficient descriptors to go through this kind of hierarchy of narrowing down your candidate materials. And also, I think recently, right, with all the LLMs and all the new developments in machine learning and AI, right? So another question is whether we can incorporate, right, these methods. So today I only have 20 minutes, so just three very short stories where we try to use these methods. The first one is to do a high throughput search for low thermal conductivity materials using some chemical bonding descriptor. And the second story is a recent attempt, right, looking for strongly photorestrictive materials, right, meaning the materials they deform a lot, right, under light. We try to kind of develop a simple thermodynamic descriptor, right, that's very easy to compute, right, so we can actually look for new strongly photorestrictive materials. And also, I would say a very naive attempt, right, to use ALM and the machine learning to predict new magnetocaloric cooling materials, in particular for hydrogen liquefaction, right? So, somewhat luckily, we found some very good materials using a very simple process. Okay, so the first story, right, low thermal conductivity, as I mentioned, right, for example, we want thermoelectric materials with low thermal conductivity. Also, you want, for example, materials for thermal insulation. But typically, thermal conductivity is very hard to compute, right? If you want to directly go using DFT, and basically you need to go to high order perturbation theory in DFT framework. So the question is, can we find some very effective descriptor that can be easily evaluated using DFT, right? So really the intuition here comes from this understanding of phonon physics, right? I'm not gonna go into too much details, but really we are looking for materials with this very soft optical phonons, right? So highlighted by the arrows here, right? They're kind of unusual, but they are present in some of the best thermoelectric materials, right? They give rise to anomalous scattering of phonons carrying heat in these materials and lead to very low thermal conductivity. So the question is, how can we systematically find these materials, right? So we really go to chemistry 101, right? Looking at how the bands are formed, right? So typically, if you think about semiconductor, right, the valence band and the conduction band is formed by hybridization of some orbitals, right? So usually the valence band are occupied, right? They are in bonding states, and the conduction band is empty, right? They're in the anti-bonding state, right? The bonding state, right? They're stable, and the anti-bonding state are unstable. Right? This is chemistry 101. But if you look at some of the materials, some of the best thermoelectric materials, we can actually very easily, right, very computationally, very cheaply evaluate their bonding characteristics of the valence band and the conduction band using this so-called COHP method. Right? Again, I'm not going to go into details, but you can just use ground level DFT, right? You can calculate COHP, and it will tell you whether these states are bonding or anti-bonding. Right? If you look at silicon, for example, right? So 0 is the Fermi level, right? The 0 to 1 is the band gap, basically, right? Below the band gap, the valence band is bonding, right? The conduction band is anti-bonding. Right? That's kind of the picture we're familiar with for conventional semiconductor. But if you look at lead telluride, for example, it's a very good thermoelectric material with anomalously low thermal conductivity given its simple crystal structure. We found that its valence band is actually anti-bonding, right? This is quite unusual. Valence band is occupied, is anti-bonding, so it's kind of unstable and leads to kind of low thermal conductivity, right? So we did some kind of verification of this, for example, by removing some electrons from the valence band, right? So the lattice actually become more stable, the optical phonon. Basically, the soft optical phonons are removed, right? We can show that if you remove some electrons, for example, from this anti-bonding valence state, you can actually increase the thermal conductivity theoretically, right, by a few times. So this kind of gave us this idea of doing a high throughput search, because again, this bonding characteristics is very cheap to evaluate, right? You can do a DFT in a few seconds. You can go through this, for example, materials project, a very large database. We can do the COHP calculation. So we just went through about 1,000 binary semiconductors, right? So trying to find semiconductors with anti-bonding valence bands, and we found like a lot of them, right? So and we actually identified this family of interesting materials, right? They're in a kind of sort of unusual valence, right? You have alkaline metals, but in their +1 state, right? Sulfides. So basically, then we can, for these materials, we can do more detailed DFT simulation to calculate the thermal conductivity. As you can see, they have very low thermal conductivity, right? 3 of them are below 1 watt per meter Kelvin. And this one particular compound with 0.15, we thought it was too good to be true, but that's what DFT says, right? So we're now trying to work with experimentalists to really make these materials. So very briefly, right, second story is we're looking at photostriction, right? This is effect where you have when you put material under light, right? There is some deformation, right? You can use this for photo-induced actuation, for example. But we have some recent speculation that this might also be related to good solar cell photovoltaic performance, right? For example, the hybrid perovskites, they have very strong photostriction. So so the idea is, can we do a high throughput search for new materials, right, with very strong photostriction, right? If you want to directly evaluate photostriction, it's actually very expensive. It's very hard to do. But we looked at some thermodynamic relation, right? Very easily using a Maxwell relation, you can actually relate photostriction, here the volume change with photo excitation, to the band gap pressure coefficient. Basically, how the band gap changes with pressure. Right? This is actually a property that can be very easily evaluated using DFT. So we did some kind of verification that shows that these two coefficients actually correlate pretty well in a lot of materials. Right? So we just went down to do this high throughput search, and then we actually ended up finding some very interesting materials. For example, in this case, this tellurium iodide, which actually experimentally has been made before. And our prediction is that its photostriction can be about 100 times stronger than silicon, right? So now we're trying to work with some experimentalists in Oak Ridge National Lab to make this material. Okay, so finally, I want to talk about magnetic refrigeration, right? So basically, in this case, we want to use magnets, right, as a refrigerant to build a magnetic cooling cycle, right? So the basic idea is if you apply a magnetic field or you remove a magnetic field, right, from a magnetic material, its temperature will increase or decrease, right? So based on this phenomena, so-called magnetocaloric effect, you can actually build a cycle, right, to achieve cooling. So for this effect to be strong enough to be useful, right, the most important characteristic is the so-called isothermal entropy change, right? So basically, how much heat can be released or absorbed, right, when you apply or remove a magnetic field to this magnetic refrigerant, right? But unfortunately, this property is also very hard to compute. And if you go to all the online large databases, they don't have this property listed, right? So basically, this is when ChatGPT was out and very went viral, right? So I talked to my students, asked them whether we can use this somehow, use ChatGPT somehow in our research, right? So they came up with this kind of very simple process flow. So basically, the idea is we want to use ChatGPT to read the literature, right? There are a lot of literature about magnetocaloric effect. Actually, just abstracts, right? Let's try to extract, right, the chemical compounds and their isothermal entropy change, right? We can maybe use this method to establish a sizable database, right, with chemical composition and their magnetocaloric properties. Then we use this to train maybe like a neural network, right? So we can use this neural network to efficiently predict, for example, magnetocaloric properties. And then we can use this to go through large databases like the materials project, right? Again, very simple. Sometimes I feel a little bit embarrassed to talk maybe to a computer scientist in this room, but somehow it worked. So basically, this is one example. We just feed this abstract of a paper, right, to ChatGPT and ask it to kind of extract the relevant properties, the chemical composition, right, entropy change, Curie temperature, and additional properties, right? So we actually were able to establish a very simple database with about 8,000. So we went through 8,000 papers, right? I think we ended up having a sizable database, maybe above 1,000 materials. So you can. So this is actually published in this on my GitHub page. You can actually do searches, right? These are all experimental, right? So you can look for different materials. But as previous speaker pointed out, right, the experimental error is actually probably not very small compared to theory and computation. So then we use this to train a very simple just neural network. Like again, I don't really know much about this. My students were just tinkering around. So they kind of use this maybe 1,000 data point, right, to train a simple neural network to predict basically magnetocaloric entropy change from their crystal structure. So I'm just gonna skip all this, right? So then we ended up with, then we use this neural network to go through the large materials project database, and we identified actually, this is a top 11 candidates, right? With 11 candidates, then it's manageable, right? We can run very detailed simulation, in this case called atomistic spin dynamics simulation, right? So we can actually simulate, right, their magnetocaloric properties. This is an expensive process, but we can manage with 11 candidates, right? So we actually ended up finding a few that are pretty promising, right? So this is kind of a summary, right? So the black stars are the materials we found using this very crude process, comparing to some of the best known materials, kind of depending on their Curie temperature, right? So basically, these materials are most efficient around their Curie temperature, right? So this one material we found, we were super excited about, europium hexaboride, right? It's much better than everything known, right, around this 20 Kelvin temperature range. Right? 20 Kelvin is actually quite important because that's the hydrogen liquefaction temperature, right? So this means this material we may be able to use it, right, to build a fridge to liquefy hydrogen, right? I think that can be very useful, right? We're actually working with Stephen right now, trying to make this material and trying to experimentally see whether this is true. Okay, so actually I'm actually ahead of time, so I just want to acknowledge my group. I thank William for inviting me here, and I guess we'll answer questions in the end, right? So altogether, okay. Yeah, thank you.
Thanks, Bolin. Next, I guess it's Sam Daly. Get to call her up. Okay. So Sam is a professor in mechanical engineering. And I don't know the title of your talk.
Lucky enough to have Bolin as a colleague.
Yes.
I'm going to apologize in advance. It's going to take me just a second. My computer decided to stay on and not go to sleep, which means that it is very low on battery, so I need to just plug it in. I just decided to do this on its own. It's fully charged this morning. Is there a plug? That's the only thing I need.
Well, I think there is. Someone plugged in earlier. There's one around the corner, but it must be. Wait. There's got to be power.
I can make this work if needed. I'll just make this work.
Okay.
Yeah, we'll make it work. It was fully charged this morning. I just had an issue. All right.
Do you want to use this?
No, I'm okay. I'll just check.
All right.
Okay. I'll just do that. Sorry. I had to restart. And do I just plug in with?
Yeah, I think so. I've never used it, so.
I haven't either. I haven't been in the server for a while. Okay. And then this has to go.
Oh man.
It's getting more and more complicated. All right. Now. All right.
Oh, there we go. All right, excellent. All right. All right, go for it.
All right. All right. Thank you guys for inviting me. Stephen, thank you, and William for inviting me here to talk today. I'm also from the mechanical engineering department. I really meant it when I said I have really great colleagues, and happy to follow Bolin. I'm going to talk about a little bit of a different. I'm on the solid mechanics side of things. I do metals and ceramic matrix composites. I'm going to talk about some of the work we've been doing in experimental mechanics of materials and machine learning. But I kind of made this to be, when I was making it, some details on our projects, but also a lot of just like the questions we're running into and the kind of overarching things that we're struggling with a little bit as experimental mechanicians. We've been very lucky to work with some really great groups, including Professor Sam Carton's group in large language models at UNH, Manjuna's group here in electrical and computer engineering, and Trisha Pollock's group in material science. And I have learned so much from these collaborations. And I know in the morning we talked about how important it is for computer scientists to learn engineering language, and for engineering to learn computer science language, and to find somewhere to meet, like to run towards each other and just learn from each other. And I have learned so much from my colleagues. So in terms of machine learning and mechanics, we've seen some extremely rapid advances, both in experimental and computational abilities, that are kind of meeting the challenge of training ML for accurate predictions. And I just put a couple examples up so you guys could see the types of ways that machine learning is currently being used in mechanics. Shared challenges across, thermo, fluids, heat transfer, mechanics, solid mechanics, things like feature extraction, reduced order modeling, experimental data analysis, dimensionality reduction, image recognition, segmentation, and then control of systems, and generating and optimizing shapes and design of experiments. So this is where we're starting to see things come into mechanics. I would say mechanics is maybe a little bit behind some of the other fields in adopting machine learning, but there's tremendous potential in mechanics and in materials for the application of machine learning. One of the things I have been thinking a lot about, and this is a very forward-looking talk, I will talk a little bit about some of the work we're doing, is that when you, we're really good at figuring out different compositions that we could possibly have. You guys know all the things that are out there to do that. But the problem is you can have, for example, in the green box on the left, tantalum. And you can have tantalum with the exact same composition, tantalum, and the exact same atomic structure. And depending on whether you additively manufacture that tantalum or whether you do a conventional processing like a ROT, it's the same composition, it's the same atomic structure, the microstructure is different, it's the same component geometry and loading, it's a little thing that you're squishing, cylinder, and you can get wildly different properties. So the only thing that is different here, is that it's a different microstructure and it's a different processing. So the soapbox that I'm standing on is that the mesoscale really matters, and we are not paying enough attention to it. We have spent a lot of time, important time, valuable time in the composition space. We're getting pretty good at the compositional space, but the elephant in the room, the thing that's blocking forward progress at this point, is that we have no idea, once we get that element, what structure we should make our materials so that we get the properties we want. So this is the kind of the most straightforward example I could think of, which is, okay, it's one element, it's tantalum. And if you look at this difference in processing, you're talking a difference of like, I want to get it right, 70% of the additive is 70% the ductility of conventionally processed tantalum, and it has twice the yield strength. That is a very different material, okay? But yet, the vast majority of papers, over 99%, are really focused on the green box. And we really, I think, do need to pay more attention to the mesoscale and to the microstructural effects. So one of the challenges that we have with that is we have all this multimodal information that we're trying to put together because we need a complete picture. And not only is it multimodal, maybe you have images and text and you have some spectral data, and you have, anyone who's an experimentalist will be like, oh yeah, even a single test, you can have multiple forms. And I put some of them on the left. It's also across length and time scales. And so I just have length scales here from picometers to meters. But this is a very standard, in a single test maybe. You could look at the energy landscape, you could have spectral information, electron and optical imaging is very standard. Some sensor readings, maybe you're measuring temperature. Bulk property characterization, you have a macroscopic stress strain curve. And you have all of these pieces of data, and they're all coming at different length scales. They usually have a temperature dependence, an environmental dependence, a history dependence. A lot of materials are strain rate dependent or processing dependent, as we just saw. And then all the data comes in different forms. So in a single paper, you can have numbers and tables, plots, diagrams, you can have text, images, symbols, video. So how do you, we talk all the time about data sparsity. We don't have enough data, we don't have enough data. But even with the data we do have and the incredibly expensive experiments that are out in literature, we're not using those to the most of our ability. So I just pulled some examples of types of data just from our papers. I mean, I literally went 2 nights ago, opened up like 2 or 3 of our papers, and immediately found all these different forms of data. And it's not like we're a special group that way. That is just how experiments typically are. So, we did some work in composites, and we had some XCT data, images of the composite structure, and we used some low-lying image segmentation algorithms to go ahead and figure out what were fibers and what were matrices. This is basically a composite with fibers running like this, and you're just slicing it this way and building it up in a non-destructive way. We have a thing we do where we attach nanoparticles, and we track them with respect to each other. We pull, basically, we chemically functionalize a surface, we make nanoparticles, we drop them on the surface, we pull the surface, and we track the nanoparticles to figure out what the strains are. We actually track cross-correlation functions. So that's that. You can see it's about 2 microns, and that's about 50 million data points. Each data point has multiple components of strain, has underlying microstructure. Hey, I've got a lot of strain. I'm close to a grain boundary. I'm in this type of grain. I'm in a big grain. This is my orientation, right? Has all of that. So these are some examples of images. These aren't also, they're not like RGB images that we get from computer vision, right? You have so much that's been kind of developed in computer vision and RGB images, and we can use so much of that development. But CRML has different challenges, right? Like when you look at these images, they're not going to be the RGB structure that we're thinking of, and they're going to have specific physical constraints in them. I should have put up also an EBSD picture. For those of you very briefly who are familiar with electron backscatter diffraction, you can think of like crystallographic symmetries, right? Okay, so all sorts of stuff going on there. Textual data. We talk about, and I know we talked about this morning, hey, well, why can't we just have ChatGPT write our papers? Or why can't we just put out little handouts of figures? It is so important to have these papers, not only for the people writing them to work through their hypotheses and their arguments and their, their data, but there is a lot of information about materials and about our testing parameters that do not go into our figures. Hey, okay, and a lot of information about what we're seeing, right? So in one of the cases we're like, look, we see this, but it is not always the case that you're going to see this enhanced, functional fatigue with better structural performance. For example, go look at this paper. Okay, we saw something different here. This is a grain size dependent phenomenon. The mechanism changes. There's a lot of information like that inside of papers as well, and we need to consider those papers so that we can properly connect knowledge. Time series data. So, we have stress strain curves, and you can have them in uniaxial, you can have them in simple torsion, you can have them in all sorts of different modes. We do acoustic emission spectra. There's all sorts of time series data, and materials and mechanics of materials, they're temperature dependent, they're history dependent, right? So it depends not only on what you process them, but like how you're loading them. If you take a material and you pull it in tension and torsion, you will get a different response often than taking it in torsion and then tension. Okay. And when we use materials, we use them in complex modes, right? So computer simulations. We do a lot of work with computer computationalists. So this is an example of our little nanoparticles and tracking them. This is experimental data. I think these grains are about 70 microns, so that kind of gives you an idea. It's a couple millimeters. And we were working with computational finite element modelers to compare our fields of view. We have a whole nother set of spatiotemporal data, vectors, tensor fields, scalars coming from simulations. And how do we integrate that type of data? And then a big one that I think of, the big kahunas I think of are text, because we have so much information that's lost in text, and nobody can go ahead and read like 4,000 papers, right? You just can't. Maybe you can, I can't. So text is a huge one, and there is a lot of description in text. images. You know, when you have a paper, it is hard to get, and we talked about this a bit. Wait, oh, it's not coming up. That's so weird. It's not coming up there. Sorry about that. It is hard sometimes to get this data. This data may be lost, but in the paper it will be here, but it's only in image form, right? So it's not like we just, unfortunately, a lot of data is stuck in hard drives in someone's office, but the images are there. So I think of text, I think of image data, and I think of math. When you look at a paper, you have a lot of images, you have a lot of text, and you have a lot of mathematical formulations. Mathematical formulations constitute of equations that the authors are proposing, but also fundamental scientific constraints. So you're basically taking an extremely big manifold, and you got to narrow it down. And you can do that using known physical constraints. But how do you incorporate that mathematical knowledge into your models, and how do you do that? And not just from the loss function, but other ways too, right? The loss function is really powerful, but how do we do this in a way that's makes the most of what we know? So these are some of the challenges. Multimodal spatial temporal data is super diverse, and we want to incorporate the relevant physical constraints and symmetries. If we get an answer and it's not satisfying or it's not following physical constraints and symmetries, then it's garbage. It's a form of hallucination. So we need multimodal AI methods desperately in Sci-AI that are capable of physical and mathematical reasoning across scales. So to put these together so we can cross-compare also representations. And this was really me sitting the glass of tea a couple nights ago, just thinking, like, what are the big challenges from the experimental perspective that I'm seeing? And modalities, like accessing individual modalities. How do you access all the information that's stored in text? How do you access the information that's stored in a macroscopic stress strain curve, right? You have a picture of twins. How do you know where the twins are, and how do you relate it back to the EBSD? And combining them. And they may be at different spatial and temporal resolutions, and they may be at scale differences. Maybe you have a picture of a dislocation, and that dislocation is in a magnesium rare earth alloy, and hey, that's really affecting the forming of that alloy without cracking for lightweighting automotive components. These two things are related. One's at the nanometer length scale, and one is, here you go, right? We know they're related. How do you tell the computer scanning through 4,000 papers or more, hey, by the way, the macroscopic stress strain curve you're seeing on that formed component, you're going to want to also go look at that paper, right? How do you make those connections? Maybe their compositions are slightly different, right? But maybe it doesn't matter. Maybe one paper calls it WA43 and one paper calls it a rare earth magnesium alloy, right? With the composition, okay? And this core question of there are different mechanisms at different scales. Creep, right? So when I teach creep in class, I always go, oh, well, we're going to teach creep and it's important, and what is this? And one time a couple years ago, a student said, it's what the girls call me. And I was like, oh, God. Creep is, for those of you who don't know in mechanics, it's very straightforward. You hang a wire. It's constant load changing displacement. So basically, like what I do in class is I take a wire, I hang it on the doorknob, and I put a weight on it. And I measure it, and then I come back 10 minutes later, I measure it again. I come back 10 minutes later, and I measure it again, and we plot it, and you can see the wire is stretching over time. Now, the thing with creep, super important, right? I mean, you can think about it worse at high temperature, you can think about high temperature applications, close quarters, you really want to make sure you're not creeping too much. But the problem is with creep, and where a lot of students stumble, and where I stumbled the first time I saw it, was that the mechanism changes. It changes based on the stress you're applying, and it changes based on the temperature you're at. And so maybe what you think is, we talk all the time about you can't extrapolate this mechanism, it's going like this, and if you change right at this temperature, it's going to change its behavior. This happens rapidly accelerate or decelerate. This happens a lot in mechanics. Materials change based on temperature, based on strain rate, based on loading history. They will change their behavior. So how do we incorporate different mechanisms across different length and time scales as well? What we learn in one paper may not be true for the exact same material and the exact same loading at a slightly different strain rate. It's just another example of, in this case, nanotwins affecting heart stents and heart patches that you put into people's bodies. We have challenges, data sparsity. Materials, as we had talked about, experimental data tends to be expensive in both time and cost. It's very rich and detailed for the most part. You can get a lot of information on your test, but it's going to be very few locations in space-time. It might be, a certain environment. It's going to be a certain probably temperature, and you're going to be loading it a certain way. You take your specimen, you twist and pull it, then that's that specimen, right? Especially really critical things like how do materials behave under fatigue. Fatigue tests can take on the order of years. These are expensive tests. These are valuable tests. We really want to make sure we make the most of them. And usually you have to trade off between field of view and resolution of the experiment. Fluid mechanicians struggle with this, and they're using super resolution and generative approaches to try to, there's a Kunihiko Taira, I think he's at UCR now, is doing some really interesting stuff, taking a very small field of view of a turbulent field, and then using generative AI to scale it up to a bigger view of turbulence. That's really interesting, because usually we either can get high resolution at a very small field of view, or we can get lower resolution at a big field of view. But if you're trying to resolve details like turbulence, you are pretty constrained. And then you don't have enough information to really, you don't have a big enough field of view to really make statistically significant conclusions sometimes. So we struggle with that balance. And I think generative AI could be used to tackle this. Okay. So there's a lot of fundamental AI challenges. We do have a lot of data. We talk all the time about data sparsity, but we are not using the trove of data that we have, unstructured and structured information currently in the literature. So how do we start using and combining that information effectively to start guiding what experiments we need to do to fill in the rest of our missing knowledge? How do we train models on fundamental physical constraints? This whole thing is centered around just trying to get it to be more tractable, right? Figure out what we know that's already in the literature, figure out what we know in terms of fundamental physical constraints, fuse that into our foundational models, and figure out what we know from computational simulations. Those can also guide us. None of these are going to be perfect. We have to have something that's fault tolerant, because there are going to be papers that are completely wrong, right? And there's going to be fundamental physical constraints is better. And there's going to be computational simulations that may lead us the wrong way. But overall, if you're kind of crowdsourcing this knowledge, it will help guide us. And very quickly, I'll talk about, we've taken some very low-lying fruit right now in our group. These are two very quick examples. They're kind of both machine learning for high-throughput experimentation. One is to look at twins in this magnesium rare earth alloy, and one is to analyze spectral data. And it's just to show some of the power of ML. So in terms of this ML for high-throughput experimentation, we developed off of the original work of a group led by Mike Sutton at USC, who really did the seminal work for this. This technique called SEMDIC, where we look at basically nanoparticle patterning a specimen, and we track those images under the scanning electron microscope. We look at where all the dots go, and we can build up strain fields. It took a while to figure this out, but we can stitch many fields of view to get high enough resolution to look at twins. This is what affects formability of lightweight magnesium components. So you can see our macroscopic stress strain data. We're putting it in compression. It's forming those twins. Those are really important for the magnesium to be ductile, so that when you're forming a component, it's not going to crack. And we need enough grains that we can have some sort of stochastic measure of what the twinning is doing based on how the atoms are arranged. Okay. And so we were able to use in this case, just k-means, to segment and identify specific twin systems. There's like 1,500 grains in this particular test. And that was pretty straightforward. The grain strain fields on the left, the twin systems on the right. It was easy to say this is a twin and this is not a twin. It was much harder to say which twin it was for the material scientists in the room. So the way that we said which twin it was we looked at what we theoretically predicted the surface strains would be for the twin variants in that grain, and then how likely it was, something called the Schmidt factor, to kind of form these twins. We had a ground truth set that we were using to look at it. We looked if the twin grew under load. If the cluster, if we thought it was a twin, it should grow when you load it. And we used computer vision by encoding strains as colors. to say, well, does it look like a twin? And so we basically took different strain fields, like the deformation this way, the deformation this way, and kind of the shear deformation, put them into RGB color streams, broke them out by cluster, looked at how uniform the strain was, and looked at the lenticular shape to see if it was this twin that we were tracking for ductility. And so when we did that, we were able to get pretty good metrics on finding out different twin systems, and we could match it with the theoretical twin systems. What this let us do very quickly, and I just threw a bunch of them up here, was basically look at a bunch of statistics for twinning that was very interesting for processing considerations and also for modelers to see if they were matching what we were seeing and this type of approach for having this amount of high throughput data. So this was a really fun project, and I mean, once we had that data set, this type of information was very easy to pull out. So modelers could contact us and say, hey, by the way, do you know the grain diameter versus the twin area fraction? We'd be like, yeah, we'll get it to you later today. Or here's the data set. Do it yourself. Another way that we can get really fast data is through something like spectral information. And I like using spectral data as an example because for a long time, acoustic emissions are pretty powerful. You can stick, you're basically listening, you can stick piezos on a specimen and you basically listen to things breaking. We do it in composites. So you listen to them cracking, you listen to the fibers breaking, and depending on what's happening, it means that maybe you're in trouble. A really good example of this is the Titan that obviously imploded, and they were like touting their acoustic emissions safety feature, which does not make any sense. But sound has always been an indication that something is happening, right? Since, I mean, we have always used sound breakage as something happening. So we've been using this for a long time, but we haven't had enough computational power. And so what people do is you have these tens of thousands of, hundreds of thousands of acoustic spectra coming in, and you're like, I can't buffer them fast enough. I'm just going to take a scalar, peak to peak or something. I'm going to put over here, and I'm going to toss the rest of the fingerprint. If you were doing this for a very long time, we don't need to do that anymore. I think we're having a paradigm shift in a lot of our old engineering practices. This was just ingrained. It was like, well, of course we always take peak to peak, or of course we always take the center, because that's what we've done for 40 years. And you're like, well, yeah, but now we have GPUs, and we don't have to do that. We can keep the whole fingerprint, and we can analyze the whole fingerprint. And so we were actually looking at CMCs, which are part of a turbine component shroud that they're interested in using them for. So we took the entire fast Fourier transform of the spectra, and then we just basically took like a fingerprint of the spectra, almost like, actually, originally got the idea from looking at a seminar that was about DNA, and they had a DNA strand of an African elephant and a DNA strand of an Asian elephant, and they made these like heat maps by taking the fast Fourier transform of them as patterns, and I thought that was really cool. And you could see how similar those DNA strands were with little differences. So I'm like, well, why couldn't you do that for, this is basically the DNA of sound in a way. You normalize each bin because the matrix crack should sound like a matrix crack, and you basically put it in feature space. And you get shockingly good results. These are completely domain knowledge agnostic. Each one of these is something that has been fast Fourier transform, binned, and fingerprinted to either be a matrix crack or a fiber break, just from the acoustic spectra, nothing else. There's no knowledge at all about it being this particular type of material, but it follows very faithfully the deformation profile of this particular material to the point where like fibers start breaking right around here, and all, I mean, right around 82-85% ultimate tensile stress. They follow that characteristic curve. This is all very true to what we see in the domain science. And then also it's sensor independent and it's sensor location independent. So I don't know if you can see on the bottom left, there's like little yellow sensors and big gray sensors. So we stuck those on, we tested, and we were checking sensor location and sensor type, and it's independent of that as well. I'll stop here because I think I've gone too far. One last thing I wanted to mention is that for experimental mechanics, quantitative evaluation and benchmarking is really key. And it's sometimes hard to figure out good benchmarks. I think we're missing that as a community in order to do kind of quantifiable evaluation of the trustworthiness of what you developed, and also how extensible it is. I think there is the danger of finding frameworks that are very, very good for the specific material you have under the specific loading conditions and the specific temperature. You've basically done a really, really nice curve fit. And so I think that it is really important for us to have these types of resources going forward. So that's it. I'll just like to acknowledge all my collaborators in funding. My students do all the work, and I just get to stand up here and talk about it. And I'm very grateful for all the really good conversations I've had. One of the joys of being in academia is you get to learn like every day, and it's been really nice. So thank you.
Okay, maybe at the risk of William getting mad at me, let's just do a 10-minute break now. We can just chat with the speakers, and then you can set up. And okay, just give people some relief here. So yeah, so maybe come back in 10 minutes. We'll reconvene with the next speaker. Oh, William just came in. Oh, he heard me. He came to exact his vengeance. All right.
I know. I can feel it. My computer decided this morning was a good time to break.
I tried to teach this as a good robotics project, but I think they've been led down this path by biologists before, so it didn't work. So they computational researcher did the experimental learning? Nice.
Yes, I was there. So like I actually got my master's in management group and joined the student. Oh no, I didn't necessarily for the quantum materials as and now I am going to
So you did postdoc, oh, you finished your PhD, you did postdoc on some part?
I am not postdoc.
Okay.
I just like finished my PhD in the early summer in June when I started OpenAI and we are using your keynote paper a lot for that.
What are you doing for content?
Oh, these are all contractors, so that's what so like as a full-time I'll be more than that. Like for example, I am doing
I see. But OpenAI will like give you access to their code so you can.
Expert trainer for some domains.
Oh, I see.
I am not like a software engineer. So, for example, I am training the model for the specific questions in the quantum and the like I have the background research on that.
Okay.
Like from the large language modeling. Although like some of the projects is based on that, it's also I would like try to learn the process how they're actually know how to none of my on that part they're usually only or experimentalists.
Yeah, because you were so close, right? So we're just like on the road.
I don't have that path. And also like when you were explaining they were also doing the PhDs, we wanted to know more about that. Besides like all of my personal.
Yeah, absolutely. Can we go get coffee and talk? Yeah.
I know, like you have been
actually reduce those, if you reduce those and then add some close, that improve a lot. But then the principle is not on the mountain. It just because you have few these local density is not that small. It's always really small. Some are really small. You just very the scale is very different. When you raise it up in GPUs, so this is a discovery. So I reviewed the shop. It's great. I feel like I already
All right. Our next speaker is Mengyang Gu from the Department of Statistics and Applied Probability here at UCSB, and he's going to be talking to us about building cost-saving, uncertainty-aware cyber infrastructure to drive discovery. All right. Look forward to your talk.
Thank you. So So I'm going to talk a little bit on the building the tools, like cyber infrastructure, and then particularly on cost saving, and then answering your work. Because we sort of hear a lot that you need GPU, you need billions of parameters to get things done. You may need hundreds of thousands of samples. So those, how do you avoid? First, let me show you some graph. My background, I'm in statistics and applied probability at UCSB. So my background training is like statistics, probability, and applied math. So this is probably one of the best figure I make. So I use in different type of talk. I saw you all make much better figures. Maybe next time I will ask ChatGPT. Okay, so this is illustrating first. The first row is experimental facility, and then this many that can be quite parallel. Like you can see this, you can put many while play, and then do in parallel. Originally, this is very costly. But now, because of reason, the underlying piece also get very costly because of some computation. So the underlying piece is cyber infrastructure. So like, for example, how do you store the data? Like how do you process the data? I'm showing, I'm going to talk about this example, like microscopy video, how do you get the material property out of it? And then I'm going to talk about the surrogate model and simulation. We developed some of these tools. I didn't put that the dollar sign there. If I ask ChatGPT, maybe you will put some dollar signs, so just both part. But okay, what kind of tools? Let me talk about a few tools that you can use that we built. One is statistical surrogate model. We already hear quite a bit like surrogate model, predictive model. I really don't need to introduce too much on this slide, but just tell you a little bit on our tool. Our tool is we can handle really high dimension, both input dimension and output dimension. What I mean, it can go to up to like 10 to the 6 in a desktop, but you still can finish computing this in like seconds and only or several minutes. And have quantified uncertainty. I will show you what that means. And then it's accurate for small sample size. What I mean accurate is like 10, 20 sample, those for some cases you still can get it. And it's fast and linear to K. K is sort of dimension. And the tool, this tool is available in R, MATLAB, Python. I will tell you sort of like origin of this tool, and it's transferable to quite a bit of different application. And then not only simulation, we see there's wonderful tools for some of the simulation, and then experimental data also here, right? The noise part, how do we do it? We also have quite a bit example to show you. First, let me also show you one recently submitted paper with our collaborator. We hear lots of solid material. Let me just talk about some of the soft material. So these are hydrogel. So hydrogel is very important environment for us. So it's an environment for cell. These two hydrogels, so the gelation time is very important. So here we basically want to learn first of all the gelation time from, for example, pH, composition, temperature, nonlinear relationship, and then we'll also put the cell on top of it. So with slow gelation time, we can see this elongated, this fibroblast, this cell, and then when it's fast gel, it's sort of chrome like a ball like this. You can see from that image. So what we really demonstrate basically is, by the way, this you need a lot of, if you really do it, you need a lot of time, because to get one data point here, you presumably need to do lots of experiment, like each curve is one microscopy video, and people need to hand shift it. Now we developed tool. I'm going to talk about that specific tool. How do you avoid it? How do you automate it? But you don't want to do lots of experiment, right? So that's the point. So we don't need that many experiment. We can cross-link this. We can use this variable and then to predict the surface, and then this to infer what the cell shape is. So this is the out-of-sample sort of prediction on this, the shape, and you can see from the formulation from this variable to the shape is good, and then also you can predict the cell shape and get back to the gelation time. It's also good. So also tell you a little bit what we are doing. So this is a Gaussian process. We work on mostly like a Bayesian, almost all Bayesian way, integrate out the parameter, mean and variance parameter, and estimate just a few parameters in the kernel function. So the predicted distribution is the t distribution, and that's the uncertainty it can come from. It's you have all the confidence interval from that t distribution. And I should highlight a little bit, the Gaussian process is a really large class. I will show you that have quite a bit of flexible choice, like so-called product kernel, which is very useful for different meaning, different physics input, different scale, different meaning. We also have other like Euclidean distance, etc., isotropic kernel. So different type of Gaussian process. Have different use. This is another tool that originally is from geophysics. Let me tell you, this is a Titan 2D simulation. When I was a PhD, that's a sort of the first project. So it's kind of quite slow simulation. So each of it giving certain input, it simulate all the eruption. So it's actually time dependent, give you momentum, flow height. But here we only care about how the maximum flow height. So I'm going to show you this, like maximum flow height for the here Montestrel Island. And then if we directly do it, we need a 10 to the 6th round. Roughly 200 years, but I need to graduate like 3 to 4 years, so I cannot wait. So we have to develop something fast. So we develop this parallel partial Gaussian process. So by the way, this is a huge map because each simulation you have this is roughest grids, like 144 by 160 grid already give you 23,000 output. And then we develop this tool. It takes only less than 1 minute and only need 50 runs to train the model. So we have all the test data, and then they are pretty close. For example, this 1 meter contour, inside of it is larger than 1 meter, outside of it is smaller than 1 meter. This flow height, you can see they overlap pretty well. You only need 50 runs to get this good result of this. And by the way, you also have this uncertainty quantification here. For example, interquartile range from like 25% to 70% percentile. I will show you how we use it. And again, the assumption is very important. So we assume distinct trend parameter, variance parameter. So we have really 23,000 type of set of all these parameters. But the good thing is we actually hear this auto differentiation, which is pretty good, pretty fast, much faster numerical differentiation. Yes. And here in this scenario, we don't need to optimize all these things. We integrate by hand. So basically, it's closed form. We don't need to even optimize it. So it's an integral in closed form. So even we have this really lot of parameter, the only thing we need to numerically optimize for this, we use product kernel only 4 parameters. So it's very stable. Almost all optimization algorithms, well, most optimization algorithms will work. So I'll just highlight some of the things like stability, efficiency, and also uncertainty aware. So now turn to some more of maybe let's just talk about the interface, how you use it. This is in R, but the MATLAB Python also have it. One line trend model, okay, give input and output. And then second, you give some test input. This is a scalar output. This is vectorized, just like I talked about, like can be really large dimension. User can specify a lot, and then you all have default setting, what kernel you're going to use, but you can also change. You have different methods, like estimation method, etc. So there are quite a bit. Since that, we extend this tool to many different settings. So there are actually lots of neural network approach. For example, from function to function, this like large dimension to larger dimension. One that showed really well is this Fourier neural operator developed by Caltech. They can handle like 10 to the k to 10 to the, sorry, RK to RK, so input output dimension is the same. So like they are setting, and then it shows it's working better in some compared to other like DeepNet, etc. paper. But if you look at the comparison between ours, the blue line and their line, sure we don't have that many data, but this simulation is from their data. They basically show this tool like this. Convection and the Navy stock, this kind of is there in their paper. We basically use their setting, and if you look at it, we are really more efficient than theirs. That's the reason we don't have that many parameters, and then we don't need to numerically optimize that many. So small data, it's actually the GP for many cases are more efficient, and then this is a parallel partial Gaussian process. That means output is really high dimensional. And I'm just showing you this kind of for example, this paper we work on is Lawrence 96 model, and collaborating with EL, Diana Cho, we work on some of the GW, also the same paper published. It's like for forecast, the error will accumulate. So you will sort of break. But the model can tell you when you will break, and at that point, you don't have enough data, you can add more data to boost the performance. So that's the point. So you can see it's pretty good prediction, right? You identify, and then at some point you see the blue one is ours, and the truth you know, they have some error, you can see, but this shady area is 95 interval that tell you you're gonna break. So that's a good thing. The machine can sense the error. And then we have some force field prediction, predicting energy. I'm not going to talk about it, about some of the environments, the physical symmetry we're building. But this is a new collaboration with Berlin, Liao, also huge dimension. This is from this electron image to predict, for example, temperature, because this is quite important for building chip, building silicon. Those are the thing, but in experiment you may not be easily measure both. You may get the image. So here this is only simulation, but we only need like 14 observation to predict another one. You can see it's pretty good, and then like only like 1% of the error, and we also add the noise to it. The result is similar. Using one to predict the other, you can do both. And then I'm just quickly talking about the uncertainty. How do you use it? A few application. First application is this is classical DFT, which is pretty good on computing some of the thermodynamic property. This is on, for example, 1D Haro system. The total energy can be written as a few part, like identity part, excess part, and something related to the external potential, chemical potential. Typically, you need to solve this Euler-Lagrange equation by this and do, for example, conjugate gradient descent or Picard iteration. The thing is, we want to do prediction. The difficulty thing is this is a functional input. That means it's infinite dimensional. How can we do it? The space can be huge. Many papers that write it give you a small space generated from parametric class. So even this infinite dimensional, what the space is only a tiny space of it. But when it's really large, we develop the tools, we prove the bound, and then such that when users specify certain arrow bound you want to achieve, and then you want to say that this, for example, density larger than this bound is smaller than that, you want this achieved, we develop criteria based on the predicted standard deviation and those things from our model that we can show this can be achieved. So basically have that criteria, and then for the given like sequentially coming the test case, we're gonna predict. If we tell you you can predict, then we'll predict. If not, we'll go back to numerical solver. And then add to training data. And then you can actually see the result actually quite strikingly good compared to, for example, some of the random sample lighting hypercube or some of the active learning approach. The red one is ours, and yellow and green and blue is theirs. The thing is, you identified some few of the challenging scenario, but the other easier scenario that we can predict reasonably well, and you can see the density, and you really control the error. You can see when the error hit to the threshold, at that time we also already have, like for example here 95 of the sample already get it. So it sort of achieves the error control, like the probabilistic error control. So this is a paper already published, and some of the more recent paper with Craig Hawker, Chris Bates group. For example, people now can do experiment like this is SAX, this small angle X-ray scattering, the real data. Originally, this kind of experiment need to be weeks. Now they can do like in terms of hour and days, because they have this the new method that they can vary different like proportion composition like simultaneously. So you can get many data actually. And also this is with Biopacific Material Innovation Platform. It's a national user facility. Other people are using it. Other people send data, but if we need our scientists to look at all the data to tell you what phase, for example, like BCC-DRS, that's just too much work. It's not sustainable. So the algorithm we develop first using our another package we don't have time to talk about, that we can do like automatic filtering. What I mean is we combine the uncertainty, the noise from it, to identify mode. Mode can be lots of mode actually. Some have more than 10 modes. And then we from this curve we can pin down to some of the physics informed. Previously we talk about this physics informed, I guess, origin from John Carnidis on the doing more constraint, like using gradient to constrain those things. So here, physics informed really means on the polymer theory that we can sort of identify, like where the mode is, the ratio of mode, so we can get this feature. So from a curve, only a few features we can capture, and then what we show is using, for example, 3 different type of chemical identity and predict another new group. And amazingly, we achieve like quite good, like 95%. That's this. If you input the entire curve, and then to, for example, some algorithm like random forest that we are using it doesn't work because they are just too much noise. So the reducing dimension from the whole thing to this is a key part. Actually, that really make it work. And interestingly, we will check. We can use this uncertainty to tell you whether we want to re-examine some of the data. You see it here, if you cut like 0.5, 0.6, you examine like 5, 6 data, we actually find out a few human-made error that in the polymer phase. So that's a quite interesting thing when we go back to check and talk to the expert scientists there. Okay, quickly talking about not ongoing, finishing with a student sitting there, about another common scenario, I think is less studied. So in both experiment and simulation, there are this scenario that you have imbalanced cost of variable. For example, here we use self-consistency field theory simulation for simulating charge AB copolymer. The goal is to do this compatible polymer without solvent by installing charge. So this simulation can get slow when you change the architecture, polymer architecture. They are still valuable, but if you change others, it's pretty cheap. So that's also the scenario for experiment. If you set up the experiment, you can do lots of experiment. And for example, for those well-planned assays, the temperature typically you can't change. It's fixed. For composition, easily changes. So these are also pretty common scenarios. But with search literature, they are not much done in this place in terms of active learning. So here, the idea we have is to sample those slow, the expensive, we have E, the expensive one. We sort of integral again. So sort of all the talk you see this, I talk about integral. Compared to all AD, it's really innovative, really nice thing. This marginalization is a key foundation of Bayesian analysis, but not quite. People didn't use that much, but still pushing forward. So this we again by the students' idea, a very brilliant idea. We can integrate this out, and then you can use some of like maximal probability entropy to evaluate uncertainty by the algorithm. So that's the thing. So that gives you a certain ensemble measure of the uncertainty. Based on it, you can sample the data, and then we can see it's indeed better than some other method like a Lightning Hypercube, this type of method. I'm going to quickly mention the second part of the talk. So this is again an interesting thing on the thing we developed by learning. Again, I'm very happy to be at UCSB, so I learned. So this material research is really new to me, and I learned after I joined material and some of the physics theory. So analyzing microscopy is a very common task. This optical microscopy, but you can also apply. So I'm math, so we in my world we are unilist. So this similar tool you can also work on the in situ microscopy, electron microscopy. But the tool there, they want to identify some of the dynamical parameters. So this is microscopy video. The difficult thing is to segment the particle. Some of the particle like cell is elongated. Those are not easy to segment. So there are this tool in physics that you can analyze as a whole. I don't want to talk too much. Basically, do the difference and do Fourier transformation, do a square ensemble, and decompose to certain term like amplitude and something called intermediate scattering function. Okay, and then the parameter are from the intermediate scattering function. And then, for example, for isotropic process, this diffusion, and then you have this parameter. And this can be related to viscosity, particle size. And for other things, you can do, for example, there are other processes I can show, but then you can do approximation by Cumulin theorem that is related to mean square displacement, and you can use something like generalized Stark and Einstein to do this Stark and the loss modulus. But anyway, in any way, they're gonna minimize this function. The difficult part is they need to specify certain Fourier range all the time. And then they are different in experiment. These are really hard to choose. For example, I'm just showing you some simulation it's already hard to choose. If you don't know the truth, it's hard to choose which Fourier range you're going to look at. How do we solve this problem? And quickly just tell you, the problem we solve is I really dig into the, I and student, to dig into the theory, what this is really about, what physics is really computing. What I mean is what a probabilistic model. So we basically construct a probabilistic model. Again, I don't want to talk too much. These are like latent factor model, but construct by like Fourier complex conjugate of 2D discrete Fourier basis. The key is the intermediate scattering function is encoded in this latent the Gaussian process. So this is from the intermediate scattering function. And then the interesting thing is, after we construct, we can show what physics is doing. This they call image structure function. This right hand side, basically I can show that equal to this model and then expected version of this. This is the autocovariance, temporal autocovariance in the Fourier space. This, in statistics world, we understand what this is. So they basically minimize this temporal variogram in Fourier space. So then you need to specify the range, and it's really hard because AQ can be very different, and you don't know this parameter. So what we do, basically, again, integrate out and do something called maximum marginal IQ estimator. And then we also use tools like this is topless system because you typically take microscopy video is equally spaced in time. So we can compute pretty fast. But anyway, we use this estimator. We don't need to minimize that function, but use maximum marginal IQ estimator. This is the software we developed for simulation and experimental data. And then there are different settings. I guess I will just quickly go through the simulation. Simulation, when we show it, must work. But anyway, you see the parameter from this to ours. We don't need to specify the Q range. We use all Q basically by default and weight it automatically. And then we have uncertainty of it that covers the truth. That each you can see 61 and 64, so it's pretty close. But if you don't choose this good range for their method, like this the physics method, then it does not work. MSD I will skip. It's it basically overlap, and then it's just this real experimental data. When signal noise ratio is very low, we can still do it, and then it's all automated. It's like default type of weight by the all Fourier range. And then this, I think I will skip. This is the first callback from the first slide. How do we get this like automated the gyration point? Previously, they need to hand shift this to the different master curve. Now we have a certain way that we can automatically determine the gyration time. Everything is automated. Anyway, I'm gonna skip and then just quickly summarize and acknowledge. I don't have time to talk too much the fast algorithm. We developed some of the fast algorithm. I don't have time to talk about it. These are the old one, but you really avoid it. So speaking of the cost saving, this is a key. That these some of the great algorithm that directly computing is very slow, but it's fast. And based on this idea, we developed a few fast algorithms that improve the time. So I thank the collaborator and the student, and then the new NSF, like CSSI, Cyber Infrastructure Grant, and then MERSAC and MIP. Yeah, thank you.
Thanks. And last but not least for this session is Anton van der Ven, a professor in the Materials Department, who's going to give us an overview of stuff that goes on in his group. Let's see what the talk is. Give it a second. Voila.
All right. Oh, thank you. Thank you. All right. Let me maybe put on my pointer. Okay. I'm going to give an overview of the kind of research we do. First principles statistical mechanics and try to solve problems in material science. This is a kind of an overview slide of how we think about materials. So at the macroscopic scale, we've already seen there are a lot of great phenomenological descriptions, things like thermodynamics, free energies for phase diagrams, Fick's law for diffusion, other phase transformation laws, mechanical laws. They're all at the phenomenological level. And they depend on materials constants. And ultimately, we'd like to connect that to something more fundamental like the electronic structure. But because materials are so messy, temperature is always present, entropy, and like we saw, processing is also very important.
we have to have really a multi-scale approach, and a crucial connection between the electronic structure and higher level theories is statistical mechanics. So this is kind of putting that same flow chart kind of more quantitatively. So there's the starting point, the Schrödinger equation in some form, some way of approximating it. The workhorse is density functional theory. And we want to get to this level over here, where we're describing materials kind of at the engineering level, where we have all these differential equations with materials constants that describe the behavior at these length scales. And an important glue is statistical mechanics, which is basically accounting for all the thermal excitations. So what the Schrödinger equation does is it gives us energies, like we've seen already a lot today, of different structures and arrangements, and we have to sample energies over many different excitations. From statistical mechanics, that lets us connect to things like free energies, which we can use to calculate phase diagrams, and also lets us calculate things like diffusion coefficients, which is relevant to look at microstructure evolution. But the biggest challenge, or at least where we're focusing our efforts on, is connecting this quantum mechanics with the statistical mechanics, because we need energies here in this big sum, which is overall excitations, and this is astronomically large if we want to have accurate properties here, of the energy, which is a solution of these complicated differential equations, and this is very computationally intensive, so we need some kind of surrogate model, and there are a lot of talks today on that. The way we approach, so we focus on this and kind of in developing these surrogate models, and the way we approach that is kind of with a generalized cluster expansion approach, and kind of in terms of a menu of picking out relevant degrees of freedom and then constructing a surrogate model that accounts specifically for those degrees of freedom. So one is, for example, an alloy cluster expansion, and you talked about that earlier today, where the relevant degrees of freedom is just the chemical ordering or disorder on a lattice or on a crystal, where you can describe, so the energy will depend on how you decorate the crystal with different chemical species, and you can express that in terms of polynomials of clusters of occupation variables. So sigmas, which are, let's say, +1 if it's orange, -1 if it's green. And then in terms of this kind of expansion where you've got pair clusters, triplet clusters, and so forth, you can train these expansion coefficients to expensive DFT calculations and then extrapolate or interpolate in Monte Carlo. Another kind of cluster expansion is that for vibrations. In that case, your degrees of freedom are displacements, and then you have these expansion coefficients which you can train to DFT. There are generalized spin cluster expansions if you're dealing with magnetic degrees of freedom, where the magnetic moments are now you can think of that as unit vectors, and the energy of the crystal will again depend on the relative arrangements of these guys. Recently we developed a kind of Hamiltonian for molecular crystals, where you've got all these different orientations of molecules in a crystal, and you can represent that local degree of freedom with quaternions, and kind of similar to a spin cluster expansion for magnetism, construct a Hamiltonian like this. And so there's this very clean and rigorous math that allows you to kind of set up these Hamiltonians, and you have to kind of rely on symmetry to construct them. And in fact, it's that same math that led Ralph Draughts to kind of work out the atomic cluster expansion. It's kind of based on this formalism developed over here, which he showed is essentially sets up kind of a surrogate model that turns out to be an underpinning of all the machine-learned interatomic potentials. You can kind of recast those in terms of this atomic cluster expansion. Within our group, we develop a software package called CHASM, which algorithmically sets these Hamiltonians up, so you kind of have different degrees of freedom. You pick a crystal structure. If you're interested in some kind of chemical degrees of freedom, you can pick that. If you're interested in displacement or magnetic and so forth. And then the software package will spawn off a lot of DFT calculations for different excitations, which it will enumerate using symmetry, and also algorithmically construct these kinds of Hamiltonians, which you can then, using various machine learning approaches, train to the DFT data, and then it will set up a highly optimized Monte Carlo from which you can then calculate a large variety of thermodynamic and kinetic properties. So I want to kind of give a few examples, walk you through this. And so this kind of general approach allows you to kind of walk up a staircase of increasing sophistication if need be, where you might have the simplest kind of surrogate models at the beginning, and you can keep walking up here, collecting more and more DFT data to train those surrogate models as you're walking up the staircase, until you've got enough training data to actually parameterize a machine learned interatomic potential, and then you can kind of do very sophisticated but computationally still very demanding kinds of calculations. But before you get there, there's a lot that you can do with these simpler surrogate models. And so let me just give you one example here, which just focuses on configurational degrees of freedom. So this is a TIS2 Spinel crystal structure, and we wanted to explore, okay, how does magnesium intercalate? So this is a material that's been used for lithium-ion batteries. You can insert lithium into this thing, and you have a positive voltage. We wanted to explore about 10 years ago, can we use these materials for magnesium batteries? And so we calculated using these cluster expansion techniques the voltage curve that's shown in red. And so all we're treating is configurational degrees of freedom, just the disorder between magnesium and vacancies. And this was published in 2015. And then a year later, an experimental group, Linda Nazar, did the measurements. And you can see, so we weren't biased by any experimental measurements, but you can see the experimental measurements are very good qualitatively and even quantitatively. And all we're treating is essentially just configurational degrees of freedom. So if we had to use a machine-learned interatomic potential to calculate this, we'd have to train over a lot of more DFT data and do much more complicated kind of statistical mechanics simulations. So in this example, we're capturing the essence to describe the relevant physics in this case. Notice the experimental results kind of stop at 50%, whereas the calculations continue. That means you could, in principle, get more magnesium in thermodynamically. And so using the same techniques, but now with kinetic Monte Carlo, we were able to calculate the diffusion coefficient. And what you can see is the diffusion coefficient is more or less constant up to about 50%, and then it essentially crashes out, which means that it's very difficult to get magnesium in and out once you're past 50%, and that's essentially why the experiments were unable to get more magnesium into this compound. So again, this is then with kinetic Monte Carlo simulations using these simple surrogate models and making important predictions about kind of the kinetics. Walking up this ladder or this staircase, a lot of alloys have chemical disorder, but also magnetic disorder. And so this is an example where we had to combine the 2 degrees of freedom. This is for a Heusler phase where you have, this is kind of the crystal structure. So ruthenium are these beige atoms, tin are these light purple, and then manganese and iron can sit on this kind of reddish purplish sublattice, which forms an FCC sublattice. And there you have chemical disorder, but the manganese and the iron are also magnetic. And it turns out that if this crystal is full of iron, it wants to be ferromagnetic, and if it's full of manganese, it wants to be antiferromagnetic. But you can alloy the sublattice and have a mixture of them and kind of mess up the magnetic properties. And so, again, training to a lot of DFT calculations, then with Monte Carlo, you can calculate a phase diagram. This is a temperature composition phase diagram. And this is a chemical miscibility gap. These are ordered magnetic states with chemical disorder. So this is ferromagnetic, this is antiferromagnetic, and then these are chemical transition lines where if you heat above them, you get a paramagnetic phase up here where the magnetic moments are disordered. But the phase diagram is very sensitive to what kind of statistics you use. If you use Ising statistics, which is just spin up, spin down, the transition temperatures are much higher. Whereas if you use Heisenberg statistics, where the magnetic moments can have kind of any orientation, which is actually physically more realistic, the magnetic transitions are much lower, and that's because the paramagnetic phase is able to have a lot more entropy because of all the degrees of freedom. And that drastically reduces all these transition temperatures. And you can see that if you were to calculate, for example, if you're just interested in kind of the chemical phase diagram, not really the magnetism, you can see that if you ignore treating the magnetism explicitly, you wouldn't really get the right phase diagram. the magnetism is very important in actually determining the topology of this phase diagram. So that's an example of kind of coupling this chemical degrees of freedom with magnetic degrees of freedom. We can keep going up and let's say couple with strain explicitly. So we recently expanded these cluster expansion methods to explicitly account for strain, where you have metrics of deforming the crystal. So you can deform the crystal, and this is really important for epitaxial kind of growth, because there the free energies will change because you're changing kind of the strain boundary conditions, and so you can actually change an alloy that might be phase separating at constant pressure can become kind of forming a solid solution or form ordered phases when you grow it epitaxially, and that's because the strain alters the free energies. So this is a lot of math here, but anyways, this column here is just to show how you can rigorously account for strain, and then come up with symmetrized kind of basis functions in terms of both occupation degrees of freedom and strain degrees of freedom, train to DFT, and then calculate these free energies as a function of strain. So just to kind of summarize and recap and put it in the context of the broader machine learned interatomic potentials, all these kinds of surrogate models that are based on this cluster expansion approach, you start with kind of an atomic configuration with degrees of freedom at each atomic site, and then you've also got some geometric relationships, these positions, but you might also have magnetic moments, which are vectors or other kinds of objects. And then you've got chemical degrees of freedom, here shown in color. So these are kind of degrees of freedom that are then related to each other geometrically in three-dimensional space. And you want to be able to predict something like an energy as a function of all these variables, these geometric variables and these local chemical and magnetic degrees of freedom. And so the general approach of this is you have basis functions, kind of a whole set of them, and the analog in other fields is, for example, a Fourier series, right? But this is more general for three-dimensional space, including also these other degrees of freedom, which is kind of like a spectral decomposition of this environment. And so when you have this explicit environment, you plug it through this set of basis functions, a whole vector of them, you get some numbers for this particular environment, and this vector then of numbers serves as a fingerprint of this environment, and then you feed that into kind of a surrogate model. And so the cluster expansions I've described are kind of just these scalar products of learnable coefficients times the values of these basis functions. But you can also plug that into a Gaussian process model where you just feed in these guys as your variables, or neural networks, again, to predict the energy. So that's kind of the general approach of these cluster expansion approaches. Many of the more recent machine learned potentials uses message passing architectures. But in essence, these ultimately boil down to kind of the same thing as what I've been describing before. And there's this really nice paper, it's still on archives, but it has all kind of the big names in the machine learned atomic potential. So Drauds, who also worked out the atomic cluster expansion, Kaczynski for Anyquip, Chani, who developed SOAP, and then all their collaborators, Bautzner also. This paper is a very nice paper which kind of puts this in broader context and shows how these message passing neural nets, which a lot of people are now using, are actually just kind of one manifestation of this kind of general approach. Let's see. Okay, if I have a few more minutes, do I have a few more minutes, or should I stop? 2 more minutes? Okay. I probably don't have enough time to kind of go through this example, but just the essence of it. This is work that Derek Ober in my group has been doing, and that is, so what I've shown is we develop surrogate models so that we can do Monte Carlo and molecular dynamics and so forth very rapidly. We have to fit that to DFT, and so to do that rigorously, you can rely on a Bayesian approach. But you can sometimes have a very good fit, nevertheless make qualitative errors. So even though the agreement with the energies are very good, you might still make some qualitative errors which then completely mess up, let's say, your predicted phase diagram. So we've come up with Bayesian approaches where you can enforce prior knowledge about, for example, the ground states of a problem, and make sure that every model that you sampled from a Bayesian approach has the ground states that you actually want to impose on it. And then also afterwards determine what's the probability that those ground states were actually the correct ones that you should be working with. And we kind of illustrated this on a more simple kind of model, these toy models. This is looking at order disorder on a triangular lattice. At high temperature, atoms on a triangular lattice would be disordered. They interact with each other, and because of these interactions, they tend to order. There's many possible orderings, usually in small unit cells. But depending on the way they interact, they will prefer some orderings over other ones. So a subset of these will be ground states, other ones will not. They will be higher in energy. And if you treat those interactions with a cluster expansion, then which orderings will be preferred will be very sensitive to what these coefficients are. And it turns out that with a Bayesian approach, where you're basically sampling expansion coefficients from training data, T, so this is DFT training data, and this is kind of the design matrix, the matrix of your fingerprints. You can write that as a likelihood times a prior. And so here is where you can kind of impose prior knowledge about what you know about the ground states. And so this is kind of a picture for a toy model where you just have a nearest neighbor and a second nearest neighbor pair interaction. Let's see if this works. And so what I'm plotting is, okay, you can pick whatever, you can pick two numbers, a value for this guy and a value for this guy. And this axis here is the value for this nearest neighbor, and the vertical axis is the value for this neighbor. And we can go around and kind of qualitatively see what that model predicts in terms of energies. And so here, this is something like 100 energies for different orderings, and then this is the convex hull. And so let's see if this works. There we go. So if you rotate around, so you're picking different values for your model, you can see you're switching what are the lowest energy structures. And this is divided up into cones, and each cone corresponds to a particular type of convex hull. And if you're inside that cone, then you have a fixed set of ground states, and if you switch from one cone to the other, you pick another set of ground states. And this is very important because, as shown in here, this is kind of mean field phase diagrams, but you can then approximate the phase diagram in a mean field approach. And so if you vary the model, you can see when you go from one cone to the other, the topology of your phase diagram changes. So if you know what the ground states are, you want to make sure you're in the correct cone. And so the whole idea of this Bayesian approach is this is again in this toy model, just to illustrate this. You have these interaction parameters, the nearest neighbor and second nearest neighbor pair. This is the ridge regression kind of fitting approach where you have a prior. Your prior over here is kind of a Gaussian at the origin. This is your likelihood. So the training data tells you that your interaction coefficient should be around here. And then if you take the product of these, you get your posterior. And this is where you can sample from. And so the techniques that we developed, and so we have some Monte Carlo techniques to kind of sample models from these posterior distributions, is if you know that your ground states are in this cone, well, then you only want to sample from this cone so that you have a finite probability in this cone, but zero everywhere else. And so if you then multiply that with this likelihood, this is your posterior distribution, and you're only going to sample models that have the kind of prior knowledge that you are trying to impose on your model. So that's kind of the gist of it. More details over here in this paper that we just published. This is then applied. You can apply this to real systems where you have many more interactions and get uncertainty on the interactions themselves, and also uncertainty bounds on the order-disorder transition temperatures, which are not that large. And so I think this is kind of a rigorous way with which surrogate models can be developed where you can impose prior knowledge about qualitative behavior. And I guess this got screwed up. Anyway, but thank you.
Oh, okay. So with that, we're a little bit behind schedule, so we'll go ahead and just do our last keynote speaker, Una Kim. So Professor Una Kim is a professor of physics from Cornell University. And we have the good fortune of having her visit here often because she's a member of the advisory board for KITP. And as she mentioned earlier, she's a many-body theoretical condensed matter physicist who's been working in machine learning and AI techniques. And my group personally has used some of her tools, and it's very useful. So I look forward to her talk, and the floor is all yours. Yeah, William's probably the guy. Yeah, I think that's probably going to work. Does the laser pointer work, Wade?
Yeah, it works.
Oh, okay, okay. All right.
Yeah, laser pointer works, and now I need to connect my computer.
There you go.
Do I need to do something about microphone or something?
Yeah.
I hold this?
I think that's probably the best solution, yeah.
Okay, got it. All right. Okay. It's a pleasure to be here. It's been very interesting. I've learned a lot. And also, thank you for staying until the bitter end. Maybe it's an honor that I'm placed here. Somebody thought maybe that's a good idea. All right. So I want to talk about data-centric learning of quantum materials. And like I said before, I'm a quantum many-body theorist, and mostly what I have done before about 8 years ago was trying to make sense out of experimental data. So usually I try to, I look at experimental data and I try to figure out, is there some theoretical way to think about that experimental data? And how do I know my spherical cow models often have any bearing on reality? Well, I try to make predictions and see if I can go this way. And going back and forth between complex data and theoretical ideas have become more and more challenging as our the richness in data have increased. So since about 8 years ago, I've started trying to explore, are there ways that I can embrace machine learning tools so that we can do better in going back and forth between complex data and theoretical insight. Over the last couple of years, it has become clear that there is a whole new dimension of synthetic systems of quantum hardwares, and now it is in this space that I have been interested in exploring and trying to see what can we solve. So data revolution. This is tunneling density of states that's measured by. This is kind of a sketch of a setup. You have a material that you want to study, for instance, superconductor, and you put a insulating barrier in the middle. You apply voltage, and that's the horizontal axis is voltage, and you measure tunneling conductance macroscopically, and this is a plot. This is a famous plot that's near and dear to people who study superconductivity. In this reported here, we've been able to understand not only salient features of this plot, such as, the tunneling is very suppressed in this up to some threshold voltage, and then it peaks. Like, these are very outstanding features, but we've also been able to understand these little wiggles. And being able to explain this within the framework of BCS theory allowed us to declare victory. Now, fast forward to today, instead of having a macroscopic tunnel junction, we can form atomic scale tunnel junctions using vacuum as barrier. And then you get tunneling conductance not over the entire sample, but with atomic resolution. So this kind of going to scanning modality is something that has been occurring for various types of probes. And the problem is we don't have a way to forward model all the full richness of what the measurements can look like.
conversely, we also don't have good ways of reducing this rich information to some theoretical insight that we can then use to build. X-ray diffraction. This is actually Nobel Prize winning paper by Bragg and Bragg, the father and son. And their very first forward model for X-ray diffraction was trying to explain these 3 peaks. And they came up with this model where they said, okay, if the atoms form plane, and if the light wave is coming in and reflecting, and if there is interference, let me introduce one model parameter d, distance between the atomic planes, and then I would get this kind of interference condition. And from using this model, they were able to turn these 3 peaks into measurements of atomic scale distance between atoms. Obviously, this was a very successful model because we teach this in high school. But you fast forward to today, instead of having 3 peaks, our experimentalist colleagues at facilities such as Argonne National Lab and Brookhaven and worldwide would get 100,000 peaks. And now you have a lot more information, clearly, but we don't know what to do with that volume of data. Projective measurements. This is Planck celebrating Stern-Gerlach experiment, which when we learn quantum mechanics in physics, it's one of those things that you learn at the very beginning. It's showing the splitting is showing that there are particles with internal structure, Hilbert space of spin up and spin down. But inferring from these measurements and various other configurations of measurements, understanding what is the sort of internal vector space associated with spin half was what we are celebrating with this plaque. But fast forward to today, instead of single spin or qubit, Hilbert space of single spin or qubit, we're interested in Hilbert space of hundreds of qubits from projective measurements. And what can we do with this? So by now, I think it from the context of the summit, it might be becoming clear that the way that I am approaching these problems might be a little bit different from what many other people today have been approaching problems. There have been generally a lot of emphasis on trying to generate models or trying to generate calculations, predict calculations. So that kind of fits under from the machine learning perspective, it is sort of more generated modeling. What I'm interested in is perhaps more native machine learning realm, that is data mining. I'm interested in trying to mine data and turn that data into insight. Because I am a theorist, I always want to gain theoretical insight. For me, gaining new theoretical insight, even if it is not quantitative numbers, it can give me sort of a broader view on where I want to go. So that's what I would like to do. So first I want to talk about XTech, which is a versatile unsupervised machine learning tool for high-dimensional X-ray scattering data. And this is something that we have developed initially in collaboration with colleagues in computer science, and Andrew used to be at Cornell, now at NYU, and colleagues at Argonne National Lab, and students from my group and students from my colleague Killian's group have all worked together to make this happen. So what can you learn with X-ray? Here I am depicting a simple one-dimensional crystal with 2 sites per unit cell. So this is a unit cell, and I have 2 sites per unit cell. In this fully symmetric, undistorted state, if this is a real space positioning of the atoms, my X-ray is going to look like this. That is, X-ray is a Fourier transform of these positions, amplitude squared. Now I'm going to have this difference in the peak height between different Bragg peaks. this difference reflects the fact that I have two sites within the unit cell, but the distance, the positions of the Bragg peaks reflect what is the lattice constant. Now I can go through various distortions, which are symmetry breaking transitions, and that would manifest in X-ray in these different ways. If I go through charge density wave and increase the size of unit cell, that's going to mean that I am going to develop super lattice peaks. And these super lattice peaks are, the position of the super lattice peaks tell me about the unit cell size, the new unit cell size. But this shape is telling me what is the specific way in which this lattice distortion happened. The unit cell has doubled. Subtler thing that can occur is intra-unit cell order, which does not change the lattice constant, but there is change in the arrangement of atoms. And these kind of order would manifest in X-ray through subtle changes in the peak height. So compare this to this, there is a small subtle changes in the peak height, which is telling me that there is this intra-unit cell distortion. So clearly, to infer this, you need to look at multiple zones. Fluctuations would result in something even subtler, because these kind of fluctuations without definite ordering would give me diffuse peaks, diffuse signal that I would like to try to figure out. So the luxury we have is that we have evolution of this three-dimensional distribution over a range of temperatures. We got to this point of having this kind of rich data set with the improvements in the detectors and various investments that went into the facilities. The question is, how can I make sense out of this and learn something? What you can see immediately is that going from here at high temperature to here at low temperature, there seems to be more activities, more sort of frequent in space. That means there are new peaks showing up. The question is, can I find out where the new peaks are showing up when this is a three-dimensional distribution? And that's what we did. Discovering where the new ordering phenomena is occurring is something X-ray temperature clustering would do. So if I send this terabytes of data through X-ray temperature clustering, XTech, it's going to give me that it's going to tell me that there are two types of clusters. There is a cluster associated with that shows one type of temperature dependence, and there's another cluster that shows different type of temperature dependence. Once I get that result, I can I can interpret that to learn that this cluster was associated with charge density wave. So that's the order parameter that I can learn. So the way XTech works is to cluster the reciprocal space into distinct clusters of temperature dependencies, and we kind of treat it as we are looking at these as a population of peaks. And this is slide that I show if I'm giving talks. If I'm talking to a physics audience who may not know what Gaussian mixture model or clustering is and what unsupervised learning is, probably to this audience that's not necessary. But what I like to say is that these tool, the purpose of the tool is to accelerate finding the order parameter or the special point in reciprocal space that's associated with ordering. And it is something that is not impossible for human to do. So if a graduate student is to sit in front of the monitor and stare at the images one after another for years, he or she will find it, except maybe not. Why? I went through that exercise during COVID. So, frequently my kids would ask me, please find me that piece that I need for this particular project. They have the manual, it's all got jumbled, and my job is to find that piece. And in my early stage of being a COVID parent, I would open this bin and I would look at one piece at a time and look at it and is this the piece I'm looking at? Is this the piece I'm looking at? You miss something that's in plain sight. Why? Because human attention span isn't that long. So it's not only a matter of the fact that we cannot spend 5 years of graduate student life staring at one data set. Yes, that is impractical. But even if there is a graduate student who's willing to do that, and even if we can afford to do that, it's just really not a good use of human intelligence. Because I just miss things that's in my plain sight, and this is like true life experience. So then what do? Because I have to find that piece. Otherwise, the kid's going to throw a tantrum. Well, it kind of organically developed that I want to first sort. So I will sort into different colors. And then if I know I'm looking for a yellow piece, my daughter's favorite color, I will just look at the bin. This sorting is much more faster because I don't have to count the size and everything. So this staging my processing of data into first sorting according to some sensible criteria and then looking within the subset was a very natural and practical thing to do. So then the question is, what would be a good sorting criteria if nobody told me something, because nobody was approaching X-ray data this way? We realized that, well, if I'm interested in emergent property, that is, I want to know how the data is evolving as a function of temperature, because I'm interested in how free energy, that is, computation between energy or internal energy and entropy, is resulting in a specific configuration. I want to really look at the whole thing as a temperature series. And this is kind of an example of how trying to approach the problem at hand from a data-centric point of view led us to look at data in a way that was not looked at before. When I asked my colleagues, let's look at the entire temperature series associated with the intensity at a given reciprocal space point, they kind of looked at me looking like funny, like, I'm a weird person. How would you do that? Why would you do that? Well, but that's what we did. So what do I mean by TD dimensional space? If there are 20 temperature points that's been measured, I would assign 20-dimensional vector associated with a given reciprocal space point, and I'm treating this reciprocal space point like it's a population who's got 20 properties associated with it. And then we clustered in this space. And working in this 20-dimensional space allowed us to represent the entire data associated with one reciprocal space as a point, and the points can be clustered. So that's what we did. So this is, left-hand side is the raw data plotted as a temperature series. So each of these curves are associated with a particular Q point, and it's plotting the temperature series. Now, I took an example where you can kind of see with your eyes that there are groups. There is one trend that's doing this, another trend that's doing this, and then there's kind of a trend that is in the background. Now, when we put this through our XTech, which is Gaussian mixture model based, what you learn is that there is one group whose mean is this solid yellow, and this is uncertainty or standard deviation, and this is another group. And now, when I reduce this data into this Gaussian mixture model results, I have a representative behavior associated with a group that wasn't obtained by simply by hand ad hoc choosing assortment and averaging, but really trying to be representative of the distribution. Then the way this works, I don't think I need to go through how Gaussian mixture model works for this audience, probably. But at the end of the day, what I'm left with is the mean and the standard deviation for each cluster and assignment of a given Q point to a cluster. And using that, I can make discoveries about where the transition is occurring and what is the order parameter. And it's for X-ray data, it's been really productive. This is the first paper where we introduced the idea. And it led to a discovery of pseudo Goldstone mode. And it also allowed us to uncover subatomic scale distortion. It's tiny, tiny distortion within a large unit cell, which was previously missed. And we were able to make use of the diffuse signal to learn Goldstone mode. And we've had great fun working with Steven on the Kagome systems. And these are figures from our paper. So for X-ray data, it's been a really great fun. And what we were able to do is, because the model is very lightweight, it's fast. So we have now incorporated X-tech analysis to the data acquisition software at Advanced Photon Source, and it's also getting integrated at CHESS, which means users can go, while they're taking data, when they're done taking the data, they can press a button on their software that they are used to using, and then go get a cup of coffee, come back, and see that, oh, this is where some transition is occurring, and this is the region in reciprocal space that I want to look more closely. And they can go from data acquisition to analysis and getting some insight into where they want to study more during their precious beam time. But moreover, because this sort of principle is simple and it's kind of not so specialized just to X-ray, we were not only able to make discoveries like Bragg glass signature, which was reported in this paper, finally published this year, but also we were able to extend the utility of this approach to several other experimental techniques. Now, I don't know when I started. When did I start? 4:20, and I have, so about 17 minutes? Okay, all right. 17 minutes, okay. So I'm going to skip how the details of exactly how we used X-tech for this latest case of Bragg glass order, but just kind of talk briefly about how it is. We found it to be much more broadly useful beyond the X-ray data. So, no, this is not. That's skipping. Okay. Oh, is it advancing by any chance? Oh wow, it works. Okay. Should have known. Okay. All right. So yes. This is where I want it to be. Okay. So not only it was very useful to the X-ray data, we are finding it to be very useful in a more broad sense. First of all, this is in collaboration with Matteo Mitrano, who is looking at pump and probe. So pump and probe means you are going to use a laser to first pump the system, and as a function of time, you're looking at how that pumping influenced the system, and you're looking at that. So that introduces the new axis of time. So the data is no longer two-dimensional or three-dimensional in reciprocal space. There is now additional time axis, and you have video-like data. And it's not obvious how you can analyze that. But using X-tech to keep pushing the wrong button. Using X-tech to analyze this time-dependent X-ray data, we are able to uncover that there is this kind of two different regions in the Q space, where there is one type of characteristic signal and another type of characteristic signal. And then we have also been using X-tech for 4D STEM, or 4+1D. STEM is scanning transmission electron microscopy, which is really moving electron beam position and doing that diffraction experiment at each position. So your beam position gives you 2D because you're looking at it in a two-dimensional space, and the diffraction data gives you 2D, so that's 2 + 2 gives 4, and additional 1 comes from maybe a composition. So this is STEM data that we were looking at, and we were able to make use of XTech to once again find, now here we are identifying different positions over the field of view of sample, that there are transitions occurring at different temperatures. And if I just look at a macroscopic data, it will all be averaged over, but using XTech, we could say, identify, okay, this is a region that's showing this type of temperature dependence, and this is a region showing a different type of temperature dependence. Specifically, there are two different transition temperatures associated with charge density wave. We were then able to correlate this with structural stacking faults. So this is one kind of mode of trying to learn, trying to make the most of large volumes of experimental data in an exhaustive way. So what's been the modality before we introduced this idea? It's a little bit similar to what Sam was talking about when she had this spectroscopy data. She said people all took it for granted that you're going to look at two positions and maybe look at average and things like that. So with X-ray data, what people would do is you have this three-dimensional intensity distribution, but you cannot visualize 3D or track it. So you will pick a slice. You will pick a two-dimensional plane because 2D we can visualize. So you look at a couple of slices of hopefully insightfully chosen two-dimensional planes cuts through the data. And because graduate students have to graduate in so many years, you would discard the rest of the data, or essentially it won't be looked at. Yes?
Yeah, this is very interesting. The problem is can't resolve exactly what kind of, you say there are two kind of mode behavior, but what are those and what exactly you are looking for from that data?
Oh, so what we do is we try to, so in that time resolved X-ray data, what played the role of temperature in the equilibrium data was played by time. So then we are when the temperature dependent equilibrium data, by looking at different temperature trends, we identify critical temperature. Now when we are looking at time series data, by identifying different trends, we are finding there is one type of dynamical scale, time scale, and there is another type of dynamical time scale. And perhaps different regions in reciprocal space was showing one type of behavior versus another type of behavior. So that's what we were going after. And as a theorist, that it was a little bit of interesting additional interest in that when we do calculations, we talk about what's called wick rotation, temperature having to do with like imaginary time. That's kind of the sort of formalism, and I thought it was kind of interesting. When I look at data, I was able to also kind of do that rotation between temperature and time. Yeah, Stephen's appreciating it. Okay, somebody appreciated. Okay, so that's one type of how I try to learn from experimental data. Now, this is another type of adventure where we are now trying to learn from experimentalist intuition. It's been said a number of times today that experiments are expensive. So if what the experience of that expensive, precious experience of experiment does to humanity is it does two things. One, it has a chance of being documented in the form of paper. Not all the experiences get documented in the form of paper, but if it does get documented in the form of paper, we do want to make use of that documentation. Two, it affects the brain of the researcher, right? Because it's your life experience. I often talk about experience of being a parent, and it's really interesting and humbling to see how when the baby just comes out of mother's body, the baby can exactly do maybe one or two things. pee and poop. Some babies have difficulty even suckling milk, right? Even that has to be learned. So we all started there. And then we get to a different point and we learn different things. How do we learn? We learn by having experiences and thinking and processing our experiences in our mind. And experimentalists in their labs, especially growers, all experimentalists are like amazing to my eyes, but all of those people who seem most magical are growers, because it's kind of like alchemy, I guess, a little magical. And people have these gut feelings, intuition that they develop by going through that experience. And the question is, how can we harness that? That's not necessarily documented in the form of paper. And that's what we've been interested in. So this was through collaboration with Leslie Shoup, a chemist, quantum chemist solid state chemist at Princeton, and her group, and with Andrew and my group members. So what would we like to be able to do? We want to predict material properties from data or experiences. And we want to have synergy between human intelligence and machine. Because some things humans better and some things machines are better, especially like doing repeated things, machines are much better. Now the question is, can we be predictive? But can we turn our empirical experience into some insightful, organized structure of data? We call it descriptor. And we are far from being first to want to have descriptor. Perhaps the most successful human endeavor in turning empirical knowledge into organized structure was the periodic table. Mendeleev, without knowing the quantum mechanics of atoms, was able to propose this table by organizing the empirical experiences. So can we go from atomistic properties to predictions? Obviously, there will be, if at all, we can go anywhere, it's not going to be all the way. I will not be able to make quantitative predictions for specific properties because I'm starting with very crude set of information. But if we can go anywhere, that could be very powerful because periodic table is very cheap. And most experimentalist growers, they just magically have it in their heads. So that's sort of people know that, well, if I mix silicon with something, it's going to do blah. How can I capture that? So in order to start capturing this, what we thought was that there was an interesting paper that Leslie wrote where she sort of articulated her intuition that was developed by looking at a collection of materials and their band structures, and she kind of formed this logic and she kind of spelled it out. And I thought that was really interesting because if something can be spelled out, experience and empirical observations can be spelled out, perhaps we can subject machine, some algorithm to the same experience and see if it will infer same kind of insight, and perhaps it will infer more. So that's the exercise we went through. And in order to do that, we wanted to have reliable data that's experimentally measured data. That's where ICSD enters, because often DFT predictions depends on how careful the calculation was done, and when it is done through a high throughput, there is danger that it may not be really reliable at a detail. Another thing that we needed was to have that human insight that we can benchmark. So the guinea pig problem that we picked was the problem of square net materials, and this was the set of materials that Leslie had the intuition. And this experience was kind of interesting because I think also it was Sam who mentioned that one of the wonderful things about being in academia is that we have a joy of learning. In doing this project, first of all, I learned chemistry better than I've ever learned because I didn't love chemistry in high school. Also, I learned how GP works, and I needed to learn both of these to do this project. And one of the interesting things about learning chemistry from Leslie was that I realized as a physicist, I always think about band structure because we can calculate band structure, which is in k-space basis. And we think in type binding model that we can calculate the band structures with. Of course, there's a DFT which gives you the spaghetti, but it's hard to think about the spaghettis. Or so, I think. Now, chemists think about bonds. So chemists think about bonds and the orbitals. Of course, these are just two different starting points of looking at the same material. You can think in the position basis or momentum basis. But thinking about bonds is kind of more simplifying, and it directly ties to the periodic table. So even if it is not quantitative, it gives you that very quick and cheap insight into what you're looking at. So what Leslie realized is that this family of materials called square nets have this property that there is this square net, and these are all materials with the p orbitals on the square net. And she thought these p orbitals that are shared, and some in the configuration where there's 1 electron per atom, might be behaving kind of like how electrons behave in graphene, which gives you the Dirac semi-metal. So she thought that if I just think about the square net and think about what would that mean for type binding model for p orbitals, she could kind of see that if your unit cell gets double, that there is going to be this crossing point. So looking at this broader set of materials, she thought maybe she can understand these whole class of materials by thinking about how square net-like are they? How much are they dominated by square net? So how do you quantify how much they are dominated by square net? She just thought, well, maybe I just look at the distance. This distance versus this distance. And that's how she came up with this notion of T ratio. So if you just look at this T ratio, which is very cheap, because it is just the structural property. And the structural property for these materials are all known. She could she could look at the T ratio for each of the materials in the SquareNet database that they have painstakingly curated. And then look at the carefully calculated DFT structure or obtained the known band structure from experiments. And what you see is that large T ratio, a small T ratio, which means it is much more SquareNet-like, generally gives you a reasonably good prediction for TSM, so that is a okay descriptor. But you see that there's a whole range where they're overlapping. So then what we were after was to see if we can give the same kind of information and the label to machine learning architecture and see if it will reproduce something like the T ratio, or it will maybe tell us more. So the actual mechanism that we used was a Gaussian process, and we wanted to learn interaction between the original features that are fundamental features. There were 12-dimensional fundamental features. We wanted to see if there are two features that are interacting with each other and becoming more important as a result of that interaction. So correlation. So that's how we designed the kernel so that it is minimalistic, but still it is able to give us non-trivial coupling between the fundamental features that we started with. And this design was guided by the need that the total number of material was just a few hundred, and we wanted to get somewhere learning from few hundred data points. So what are the fundamental features? The sort of bare features that we used were some were structural and some were atomistic. And for a compound, there will be multiple atoms in a unit cell. In such cases, we would take maximum and minimum for electron affinity. Clearly, this is a simplified view, something that we are now working on improving upon. So this is the curated database that Sebastian took pains to put together. And the result was that when we look at the correlation matrix after training our GP model, we were able to identify that there were some combination of features. These are the 12-dimensional fundamental features. Combination of features together became important. This is symmetric, so I'm showing only the lower half of the triangle, and we are not looking at the diagonal because we are interested in when two features combine. And the result is that, first of all, our GP sort of rediscovered the T ratio without being told to look for it. But it also discovered a new descriptor. And by having additional descriptor, we were able to separate what was overlapping before into nicely separated group. And like as the previous speaker mentioned, in this process, we also were able to find human errors in the curation of the database. Even if you're trying to curate mere just like few hundred materials, looking up each material and documenting it by hand, there were some mistakes that were made, and those were identified by looking at what the machine did and trying to look at like, oh, these are sort of out of distribution, what's going on. So that's another set of effort. That this is the line of effort where we are trying to leverage the accumulated, curated databases that are increasingly becoming available. Now, in my remaining, probably not much time, I'll just flash quickly yet a third way of how we are trying to make use of accumulated human endeavor, that is the literature. And this is, can we make use of the use of LLM to assist in theoretical research, sort of as agentic workflow management. So what we are trying to do here is, I don't know what this slide is. Oh, okay. So this is saying like there are these different efforts trying to use LLM for problem solving. And most of this is already now very old, like last year. All this benchmarking often are asking for sort of a one-line answer to a one-line question. Is model getting the right answer to a question that is, a homework problem or an exam problem, maybe a math Olympiad problem, but it is one problem with one answer. What we wanted to see was the prospect of, can we get to the another step? Because in what we do, often there are some calculations as a theorist that are very formulaic, like well-defined set of steps that you go through. So the technique itself is not sophisticated or novel, but it is a very useful thing that we often do. For those things where I can really specify that this is step 1, this is step 2, like in a manual, can we automate that? And that's what we wanted to try. So what we did specifically was, I don't know what these texts are saying. What we did specifically is this. This is the paper that you can look at. This is arXiv, Hartree-Fock mean field theory. Hartree-Fock mean field theory, as it is used in quantum many-body setting, is a little different from how it's used in chemistry. In chemistry, there is the Hamiltonian, which is, everybody's interacting through Coulomb interaction, and there's kinetic energy, and you just try to do the mean field theory on that. But in sort of quantum many-body context, we go to what kind of looks like the surrogate model, as it was referred to previously, and we try to explore different symmetry breaking possibilities in those simplified models. So these are how we looked at all the papers using Hartree-Fock mean field theory in the arXiv from 2010 to 2023, there are this many papers using Hartree-Fock mean field theory, these many in the condensed matter, and these many are not including bosons because we were only looking at fermions, etc. And we kind of came down to a smaller set that we thought we could manage. And then we spelled out what is the process that's involved in doing Hartree-Fock mean field theory. In order to work towards automation, we have to first articulate what are the steps that we are going through. This we say as an insider, as expert, we say to each other, oh, it's obvious. When we talk to a graduate student, we say, why don't you go do Hartree-Fock mean field theory? We don't spell out the steps if the graduate student is advanced. But if the student is not graduate student or maybe undergrad, who's smart and willing to work hard and learns quickly, we would have to spell out the steps. And if we spell out the steps, the student might be able to come back with the right answer. So that's what we went through. We spelled out what are the steps that we have to go through to arrive at the mean field theory self-consistency equations. And then we wanted to see whether we can design the prompt template that can be dispatched to all of the Hartree-Fock problems. So we designed the templates based on our understanding of the structure so that for a given problem, we just have to switch in the problem-specific pieces that will give us a template, the prompt that we can use for a given paper. And in order to extract those problem-specific pieces, we also use LLM. This was with ChatGPT end of last year, where we would ask LLM to extract those key information from abstract. So the vision we had was how close can LLM get to sort of, beginning graduate student. If I can tell a graduate student, here is an interesting problem, some transition metal that you call chalcogenide material, I think this and that symmetry breaking can occur. Why don't you go do Hartree-Fock mean field theory? That's probably as much as I will tell the student, which is essentially an abstract of a paper. So we were exploring whether that can be done. I'm out of time, so long story short, you can find more details in the paper. But we looked at these 15 papers, and we tried to see if we can reproduce them. And we did various analysis of the result. And the sort of the summary is, so there are two things that we learned. First of all, reading the papers to fill in the template. That was the first thing that we had LLM do, is hard. So reading is harder than we give it credit, which is kind of interesting. Another thing that we learned is executing the calculations, executing these derivations was actually very doable. So ChatGPT, it's not even the latest model, this is just as of last November, was very good. Let me be quantitative with my very good. It was very good at doing the many-body derivation. It will spit out LaTeX, for different tasks that we make it do. And this is our scores of how well it did in different steps. First, it had to build a Hamiltonian given the information, which was verbally given. And then it had to often kinetic energy would be given, like say some type binding model that you have to Fourier transform. You have to choose your basis. If it is momentum basis, you have to Fourier transform. And then you have to use Wick's theorem, which is how you turn these operators into making a mean field approximation, turning interaction into an effective field. And then it has to define what the order parameter is so that there is a self-consistency equation. So these are the scores, and usually it did pretty. It was good at doing sort of rigorous. Almost pretty rigorous, pretty correct calculations. Executing calculations, it was really good. where it struggled was interestingly in working in a multimodal sense, not in image and the language, but mathematics and language. That bridging was where it struggled. What we didn't do in that work that is on arXiv was getting to the next level of generating code, which is what we are working on now. But there are these 3 steps. First step is to go from a problem statement like abstract to self-consistency equation, which for an advanced student would take about a week. For undergrad, first year graduate student, would have to first take a many-body physics course in order to get there. So more than a week. And then once you have the self-consistency equation, then you want to solve it iteratively. And you want to write a code that will solve it iteratively, and then you want to explore the phase space. So these are 3 steps, and we're exploring, completing each of those steps with LLMs. And that whole experience has been kind of interesting in telling us that how close we are in being able to automate well-defined tasks. And I think the students of the current generation, or maybe a year or 2 from now, would have very different experiences being able to carry through multiple calculations and coming up with a conclusion. So with that, let me just conclude. I talked about these 3 different ways in which we are trying to use machine learning models from, like, can I get insight from data? XTech was how we were analyzing large volumes of data in high dimensional space, and we are also working on trying to go from curated database to insight, learning trends. And this is the space where we're now working on learning meaningful, trying to uncover if there is something meaningful that can be learned from database of all the known superconductors. And finally, I talked about agentic workflow through the example of Hartree-Fock. With that, thank you for your attention, and thank you for staying until the very end.
Questions, Bruno?
So for the XSEC, if you, well, maybe I should ask as a question, do you have to control for coefficient of thermal expansion and like sort of adjust for where your Bragg peaks are going? Change temperature, that is.
So we don't control where the Bragg peaks are.
Sure.
And we don't specify where the Bragg peaks are. So what we do is, so this is what we do. X-ray data is intensity at every point in reciprocal space. So we treat each reciprocal space to have a series of intensities at different temperatures. And we shove the whole thing through XTech. And it's going to say some of the Q space points, reciprocal space points, show one type of temperature dependence. Other points show different type of temperature dependence. So we're just sorting the reciprocal space points. And when we go through that, we will discover that we end up with clusters, and one of the cluster would correspond to Bragg peaks. There will be other clusters corresponding to diffuse signal. There will be other clusters corresponding to some ordering peak. But we didn't say where in reciprocal space these Bragg peaks have to be. We just find it by analyzing data.
But the approach is sort of compatible with those Bragg peaks moving in reciprocal space due to thermal expansion?
No, it isn't.
Okay.
Yeah. Because we are treating each Bragg peak to be something having a meaningful identity that is maintained throughout the temperature, right? Okay. So if we go through a lot of thermal expansion, there will be a problem. Yes.
Yeah, maybe following up on that question. Yeah, I mean, so like, I guess the data is typically just indexed already, so then it's kind of accounted for a little bit.
Yeah. Right.
But like, I guess one question I was going to ask is like, I mean, more of a suggestion. Like, so X-ray diffraction, especially synchrotron X-ray diffraction, like measuring an order parameter, is like a real pain. And it's super slow, and it takes a lot of like patience in a traditional way. So X-Tech, I think one of the boons, I mean, in addition to just finding new things that you might have missed in these parametric data sets, and also being able to sample all these zones simultaneously, is just the time saving.
Absolutely, yeah.
And so
yeah.
I wonder if like Jacob or somebody could just like quantify how much money that saves them in terms of operating, right? In terms of beam time days, right? It's a real like, I mean, like it would take.
You know,
a solid day to do something.
yeah, it's funny. So some AIP publishing, somebody is writing some piece about AI for science or something, and she's been interviewing me and asking questions. I told her about X-Tech, and she asked me, so how much time would it take to analyze the data that you've analyzed with X-Tech with human researcher? And I could only say that, you know, because nobody would manually analyze 3 terabytes of data, I don't know that. But what you're asking is I mean, I agree with you. We should try to quantify this, because that will be really helpful with any proposals, especially.
Yeah, especially like, you know, X-rays.
Yeah, yeah.
Moves, you have to realign every temperature.
Yeah.
So I have a quick question about the third part. I found the third part the most interesting, and from the result, it seems like that the Hartree fog, the reasoning process still might be a little bit too easy for language model at the time. Is that the correct interpretation, or?
I wouldn't say it's too easy. It's kind of like just about possible, but like, so one of the complaints by the referee is that our prompts were super long. It is like super handheld, and the point is, this kind of comes back to like, how do we prevent hallucination, right? Because we need to get the answers to be correct, and so what we did was we would make sure that so like the orders of questions prompts also matter. We will first make it specify why it is doing what it is saying it is going to be doing, and we broke down every step, and we put in a lot of care in making sure that there are checks in there that prevents it from making mistakes. And even then, the kind of mistakes that LLM made, at least as of last year, that was kind of interesting is, as a physicist, we would put a tremendous value on a superscript of operator. So if we have C representing electron, whether it's C or C dagger, makes a world of difference. One is electron, the other is hole. But LLM didn't care, right? So these are the kind of things that it's not like, I don't think doing this just like this at a press of a button is not possible. I think the technology is there. But the question is, how do we make sure that, the things that are very important to us that were not necessarily told to be important when you train these generic models are, put in place. Another thing that we are finding really interesting is, as we try to do the automated code writing, when somebody gives you a piece of code and it, lo and behold, even executes, right? It compiles and executes. How do you know it is right? Right? Because you're not going to read it. It's even worse than my Lego problem. Like, if you read it line by line, would you find that there was some mistake if it's executing? So how do you make sure it is right? So maybe you can put in a lot of effort into annotating to say this is what the correct code looks like, but it's a really, really big space, right? So what we thought we would do is to come up with sanity checks. And we made it, because it is probabilistic, right? So it gives us a code and it runs. Then we do a sanity check on, like, what is the non-interacting energy? Does it have the right symmetry? Like, if it is certain system which is known to have threefold rotational symmetry, it should have threefold rotational symmetry. And so what we do is we make it go through these checks. And if it fails in one of those checks, we tell it to do it again. And so I think like this Hartree-Fock problem for us is a kind of like a problem that is not just one line answer, like a single piece of answer kind of problem, but never, and it is non-trivial enough because there is a huge industry of doing Hartree-Fock calculation. Like in this Moray field right now, you go 3-layer, 4-layer, 5-layer, and like everybody's doing Hartree-Fock. So it is useful, although those Hartree-Fock calculations are much more sophisticated. But it's the same framework, so it's kind of like useful, slightly non-trivial, and just around the corner, but not like, you know, something that can be easily done with generic models. And so by trying to make it work, because we can kind of see that with thoughts and cleverness and effort and you know, babysitting, we can make it go in the right direction. So it's motivating and interesting, and it kind of helps us develop the strategy of how do we work with this beast. And what I find personally really interesting is I try to interact with LLM sort of in a way how I interact with students. Like, you know, sanity check. Like, we don't check every line of student's calculation, but student comes back with the result, we will go through some sanity checks, right? So that's kind of how we are approaching this. And how do we make sure student doesn't make mistakes? We say, okay, are you working with dimensionless quantity? Like, you know, these are the guardrails that we put in, and that's also what we are trying to do. It's a very interesting age that we live in.
Yeah, so we're already pretty late, 5:30. So again, just very quick, thanks everyone for coming, and really appreciate the speakers for the event, and we hope to see you in future years. Thank you.